Welcome to your learning journey in this deep learning with Tensorflow. Now, in this 6 hour long video, we'll be diving deep into this deep learning and understand how to create the neural network, work with the convolutional neural network, build everything from scratch. So, stay with me till the end. I'm confident that you'll be able to master the deep learning by the end of this video. If you have got any questions, let us know in the comment section. And if you're enjoying it, do check out our website for other courses. So, happy learning.
Hey everyone, welcome back to our YouTube channel. Now in this video, we'll have an introduction to deep learning. So as we progress in today's session, we'll understand what is deep learning, what is the need for deep learning, various use cases of deep learning, and how you can get started with deep learning with minimal effort. So we are going to learn each and everything in detail as we progress in today's session. So if you are new to us, ensure that you subscribe to our channel so that you can get the latest updates around deep learning, data science, and machine learning. Okay, so let's start by the first question. What is deep learning and why do we have to be concerned about this deep learning? If you look at this diagram, you can clearly observe this deep learning that you see over here. This is present within the machine learning, and machine learning is present within the artificial intelligence. If I want to explain this overall hierarchy, on top I have an artificial intelligence. Now artificial intelligence is a system which has the ability to analyze, and along with this analyze, it also has the ability to take an action. So we would say artificial intelligence is a system which is capable of taking the decision and also taking the action, and that is the beauty of this artificial intelligence system. Now we have a machine learning. Now you can clearly observe from this diagram, this machine learning is a subset of artificial intelligence, which means it can do only a part of what my AI system can do. Now, talking about this machine learning is a subset of artificial intelligence which will analyze the data. That's it. It will just analyze the data for us. And while performing the analysis, here it will make use of statistical models. It is based on statistical models. Now, our deep learning, which we are interested in learning today, so this deep learning is a subset of machine learning. So even this deep learning helps us in finding the pattern for a given data set. But to find the pattern, instead of using the statistical model, we make use of a special structure that's called as artificial neural network. And these artificial neural network are the structures which are inspired by our human brain. And that is what this deep learning is all about. It's actually a structure where I'll go ahead and I'll create this structure to analyze my given data set. Using this artificial neural network structure, we'll understand the data, we'll find the patterns present in the data. Just like we can perform the classification, regression, and other activities, we can perform the same using the neural network, and that is what deep learning is all about. If I talk about this deep learning, as I mentioned, deep learning is made up of artificial neural network. It's composed of series of layers, and these layers are connected together to form an artificial neural network. And this artificial neural network, it actually forms the core of my deep learning. And the best part about this artificial neural network is it is powerful, it is versatile, and more importantly, it is scalable. It is scalable, which means I can apply it on a very large data volume as well. As a result of this, we find the use cases of deep learning in various scenarios like Google Images. Whenever I want in Google Images in classifying the image data, Amazon Alexa while responding to the human commands, and we've got Netflix. Netflix actually uses deep learning in order to recommend the contents for their users. So these are some of the applications of deep learning, and we see this application present in each and every domain. So here these three things are just an example. Apart from this, I can say this is being used in each and every domain. Now you might be wondering why deep learning is getting popularity these days. It is true that this concept of deep learning was actually not new to us. Frankly speaking, guys, this concept was actually present in the 19s itself, like 1920, 1940. In those years itself, we had this conceptual understanding of deep learning. But why are we seeing this deep learning getting popularity these days? One main important reason is the explosion of the data, that is explosion of big data. With the digitization come into picture, many companies they started storing the data in a digital manner. So as a result of this, accessibility of the data and storing the data became cheaper and cheaper, and more importantly it is now available in a digital format. So that is one reason. And the another main reason is hardware. Just think about the cost of CPU right now and think about the cost of CPU 10 years ago, or just compare between the size of the memory of, let's say, 8 MB of floppy drive with 32 GB of pen drive that you have right now. It's so simple, isn't it? It has become quite economical for getting the accessories on and for getting this hardware, and it has become cheaper and cheaper. And also the advancements that we have done in terms of hardware, it's huge. And over on top, in order to use this amazing hardware that we have, we've got amazing software libraries like PyTorch, TensorFlow. Using this PyTorch and TensorFlow, we can make use of powerful hard drive and run it on top of them so that we can efficiently process this big data and find the analysis and find the pattern on those big data. And that's the best part, and that is the main reason we see a lot of progress in the field of deep learning. And more importantly, with the open source in the picture, we see a lot of active community in terms of GitHub and other communities, ensuring that we've got a lot of learners who are interested, and we've got a lot of researchers working on this domain. So because of all these factors, deep learning is gaining the popularity these days. Now, if I'm using something, it should actually give me an advantage over the other things, isn't it? Now, let's talk about why do we use deep learning and in which scenarios, and what is the improvement that we are going to get over machine learning. One major improvement that we get over machine learning is here it is going to help us in reducing the curse of dimensionality. As you might have experienced, when it comes to machine learning, if I have more number of dimensions, let's say if my dimension grows, let's say 100 or 1000 or more than that, we see that machine learning models struggle when it comes to prediction. And even those machine learning models, since they are being statistical in nature, they don't have the ability to make use of GPUs and to increase the parallelization and increase the computation. So that is where machine learning lags. But that is where the deep learning shines, because the deep learning will be able to work well even if I have more number of features. And one of the major tasks that we face as a data scientist is extracting the important features. And that is a manual work, even though as much as we hate it, we still have to do it. But when it comes to deep learning, we don't have to worry about feature engineering. Feature engineering will be done automatically. At least majority of the part will be taken care by the deep learning itself. And that removes one more barrier for us. And with the more amount of data, traditional machine learning algorithms is going to become stagnant. But with the deep learning techniques, we have observed that the performance of the deep learning model increases with the increase in the data. Because of all this reason, we see a lot of interest among the community for deep learning. So this is a trend which talks about how the deep learning worldwide such topics would look like. See, you can clearly see in the past few years we see a lot of increase, and the growth is it's going in a tremendous manner over the last few years, especially in the topic of deep learning. Now, I'll just give you an idea about a use case of this deep learning in a social media. I'm sure everyone is aware of social media, so I'll just give you a relatable example and how deep learning is being used in social media. So I can say in social media, if I take an example like Facebook. So In social media, deep learning is being used for face recognition. Not only that, deep learning is also used in suggesting the potential friends, suggesting the relevant post, suggesting the advertisement. See, all these things which we experience day in and day out with our social media application. So all these core things are being run by my deep learning model. And you tell me which is the one which is being most popular. That's correct. That's deep learning. So I hope you now know why deep learning is getting the traction these days and why it is in great demand. Now you might be wondering, if you're someone who is into deep learning and who wants to learn deep learning, how to get started with deep learning. Since I've just talked about multiple things in this video, we've got artificial neural network, and using that we are going to process the data, and we have various libraries. Well, don't worry. To help you progress in the learning journey, we have created a playlist in our YouTube channel. So this playlist contains the complete deep learning course using TensorFlow. You can just check the link in the description, follow along with me, and I'm sure you're going to have fun with the hands-on learning with this theoretical concepts that you will be required to learn. So I hope you guys will check out this tutorial, and I look forward to seeing you in the class 1 of this deep learning tutorial. Alright, so thank you so much for watching. Now stop wasting the time, start learning now. I look forward to seeing you next time.
In the class 1, we are going to understand what deep learning is. Now, I want to begin this class by asking you a question. Can computers learn like humans? Yes, this is a valid question, right? Because from the past decade, we are trying to build a system as intelligent as human beings so that the computers can perform the actions better than humans, isn't it? And if you look at the applications which we are using in the past few years, the way we are interacting with them has drastically changed. For example, if I take a simple example as Facebook, yes, I know you have experienced this. Your friend uploads your photo from his account. Then suddenly you receive a notification saying that, hey, your friend has uploaded your photo, do you want to review it? Now, how does that Facebook application knows your photo? Does it mean like someone in Facebook is writing a code saying that the Sam will look like this, and if his face pops up, then I should notify him? Is something happening like that? No, there is something larger than traditional programming is taking place inside these applications. And it's not just Facebook, like even we see in different applications as well. Apart from this facial recognition which we see in Facebook, the other important aspect which we come across recently is machine translation. Yes, let's say if someone posts some update in a particular language, say let's say local language, and when you click on the C translation button, it will be translated to English in that instant itself. In this example, this person says बहुत खूबसूरत नज़ारा है. And when you click on the C translation button, it will be translated as very beautiful view. It's not just related to a national language, even it applies to regional languages as well. In this example, the Deepak says Adbhuta, ನೀವು ಕಾಂಬೋಡಿಯಾಗೆ ಯಾವಾಗೆ ಹೋಗಿದ್ದೀರಿ? It's a regional language of Kannada which is spoken in Karnataka state of India. And when you click on the C translation button, it will be translated to English in a perfect way, guys. It says, awesome, when did you go to Cambodia? Now, these kind of intelligence systems are all derived from what we call as deep learning. What is deep learning? We'll understand this in the future part of this section. So, moving ahead. Even the newsfeed, the ads which we see in the Facebook are all based on deep learning. And if I want to name other applications, we have self-driving cars, text generation, recommendation engines, chatbots, fraud detection, many more, guys. Many more are the applications of deep learning, and the way we are interacting with these applications is completely different from what we used to interact from past 10 years ago. With this introduction in place, what are we going to cover in this class? As a first step, we are going to understand what is deep learning. And when I say it as deep learning, I know most of you will have a question as, if deep learning is this, then what is machine learning? What is artificial intelligence and what's the difference between them? So I'm going to take up that question as to understand what is the difference between these three, that is machine learning, deep learning and artificial intelligence. Once we have learned the difference, we will deep dive into deep learning and understand the concept of artificial neural networks. And after that, we are going to end this session by understanding how model learns in deep learning. So let's get started. What is deep learning? The deep learning is a subfield of machine learning which is concerned with algorithms inspired by the structure and function of the human brain. And this structure and function which are inspired by the human brain are called as artificial neural networks. Got it? The deep learning is a subfield of machine learning. And the way this works or the technique works is, it is based on the structures and algorithms which are inspired by the function of human brain, and these are called artificial neural networks. Now, if deep learning is this, how is this related to artificial intelligence and machine learning? So let's understand that. Now, if I want to represent this artificial intelligence, machine learning and deep learning in one diagram, I can represent it like this. We have the artificial intelligence as a whole like this. And inside the artificial intelligence, we have machine learning. And since deep learning is a subset of machine learning, deep learning is present inside the machine learning like here. Got it? Okay, so let's understand what is artificial intelligence. The artificial intelligence is a study of how to train the computers so that the computers can do the things which at present humans can do. And we want to make sure that this artificial intelligence system should be able to do better than what we humans do. That means in case of artificial intelligence system, we want the system to analyze the data and take the action. It can also be like a driver. So if a robot or an artificial intelligence system is driving the car, then we expect that artificial intelligence system to scan the outside surroundings and take the necessary action so that it can drive better than human. So that means in case of artificial intelligence system, we want the system to analyze the data as well as take the action so that it can do a better job than humans do. Moving on, machine learning. Now, this machine learning is a subset of artificial intelligence. Using this machine learning technique, what we do is we analyze the data and we find the patterns in them so that when we get a new data, we will be able to predict the outcome. That means the learning part of artificial intelligence system is done via machine learning. If I want to say it in a single sentence, I can say as machine learning system produces the prediction. So if I want to take an example of the self-driving car or the artificial intelligence driver, let's say the artificial intelligence system looks at the surroundings. And if you see a traffic signal, the computer doesn't know whether it's a traffic signal or a light post or a real person, anything. It can be anything. So this artificial intelligence system will understand what these things are by making use of machine learning techniques. Hence, the learning part of artificial intelligence system takes place through machine learning. That means it finds the pattern and helps us to produce the prediction. Moving on, next is deep learning. As I said already, the deep learning is a subset of machine learning. It is one of the way to realize the machine learning. And in case of deep learning, the technique of learning is inspired by the information processing patterns found in the human brain. So, in case of deep learning as well, it will produce only the prediction and not the action, guys. And like I said already, it is a technique to realize the machine learning. Got it? Yes. So, we have now understood the differences between artificial intelligence, machine learning and deep learning. We have also learned that this deep learning is a technique which are inspired by the information processing patterns found in the human brain. So, to understand more about this deep learning, let's understand how we human beings process the information. We know that we human beings process the information through our human brain, isn't it? And this human brain is made up of complex of network of cells called neurons. And these neurons are connected together to process the information. This is what we had studied in our biology class, isn't it? Now, if our human brain are connected with neuron cells like this, then what does a single neuron look like? A single neuron will look like this. Each individual cell of our human brain has three important parts: nucleus, dendrites, and axon terminals. Nucleus is the place where the information gets processed. And through dendrites, the cells receive the information from other neurons. And through axon terminals, the processed information are passed on to next neuron or to next action point which we require in the human brain. Now, here's the important point. I'll give you a simple example as how our human brain works. Let's say you are scared of snakes. So if a snake appears in front of you, what will you do? You'll run away in that particular instant, isn't it? So what has happened? You saw a snake. And you saw a snake through a sensory organ, that is through eyes. Now, this information of snake has passed down to the brain through this complex structure of neurons, isn't it? Now, let's consider a single neuron. Since the dendrites receives the information, let's say this particular information has been received through this particular neuron. Now, once the information is reached here, the nucleus processes the information saying that, hey, I can see a snake in front of me. So the next action is run away from this. So the nucleus processes information of the snake and sends the information to axon terminal as run away from that particular place. Isn't it? Now let's take another scenario. Now this time, instead of seeing the snake in real, you see the image of the snake in the computer screen. Now the same input goes to your system. It goes to the dendrites and says to the nucleus as, hey, I can see a snake. Since the image of the snake is in computer screen, your brain will not give you any information to run away. So what you will do? You'll not take any action and you'll simply sit and do your work, isn't it? Now this action, that is whether to trigger a response or not, are controlled by neurotransmitters. The nerve signals triggers the release of neurotransmitters which carry the signals to next neurons. Got it? Yes. Now, using all our understanding of the human brain, let's understand how the deep learning system will look like and how does it work. So, this is how a typical deep learning network will look like. I know this sounds little confusing if you're seeing it the first time, but let me explain one by one. Just like we human brain, we have sensory organs to receive the input from the outer world, we have the input layer in the deep learning networks to take the input. See, this A, B, C, D are the input layer through which the deep learning system, that is the deep learning network, will receive the input. So you can think of this as a sensory organ, guys, for the deep learning network. Now, to give you an example, if I'm building a system for image classification just like we see in the Facebook, the input can be images of the faces. It can also be text if I'm building a system for machine translation. It can also be video if I'm building a system for video detection, and so on. Depending on the application, the data can be anything. But the core thing is, the deep learning system will have an input layer just like we human beings have the sensory organs. Moving on, just like we human beings have the complex structure of neurons which are connected together to process the information, the deep neural networks will have the same structure, but we call them as artificial neurons. That's it. And in this particular example, these red dots, green dots and blue dots which we see here, these can be called as artificial neurons. Can you see the lines over here, here? These lines represent the connection between many neurons. So, just like our human brain is consisting of network of connections between the individual neurons, in deep neural networks, we have the connection between artificial neurons. That's it, guys. Now here is the important part. Inside these neurons, the computation takes place. You can also think this like a nucleus of the neuron. So, just like the biological neuron will be able to process the information inside the nucleus, all the processing in the deep neural network will happen inside these artificial neurons. And we call them as hidden layers. Got it? So what this hidden layer will do is, it takes in the input, that is through sensory, in our case input layer, and process the information. And once the information is processed inside these hidden layers, it will be provided as the output to the output layer. Got it? If you want to connect this to a human biological neuron, you can think of axon terminals as the output layers, and you can think of dendrites as the input layer, and the individual nucleus represents the individual artificial neuron in the deep learning network. Now this is very important, guys. we have another concept called activation function in case of deep neural networks. Now, just like we human beings decide whether to react to a particular situation or not, in case of deep neural networks, we have something called activation function. Using this activation function, it will be able to decide whether a neuron should be activated or not. We make use of this activation function because, in real sense, that is in biological sense, we don't know what is happening inside our human brain. But to be able to reproduce it mathematically for our computation purpose, we are going to make use of mathematical functions called activation function. And using this, we'll be able to decide whether to fire a particular neuron or not during the information processing purpose. We'll understand more as we go along in this course. For now, just be with me, guys. If I want to show you as how the activation function looks like, these two are the different activation function which we commonly use in most of our courses. The first activation function is called sigmoid activation function, and the second activation function is called hyperbolic tangent function. Now, just be with me and look at this diagram. We'll understand its computation and its implication in the future part of this course. For now, just be with me, guys. As I said already, the activation function decides whether a neuron should be activated or not. That's it. Let's say the output from your activation function has got around 0.5. That is, for this hyperbolic tangent function, you have the output has 0.5. Since the range of the tangent function is between -1 to 1, since the 0.5 is close to +1, you'll say as activate a neuron. Now, if the output of the activation function is around -0.5, since -0.5 is close to -1, we'll say as don't activate a particular neuron. That's how activation function works in deep neural networks. Now, if I want to explain the same in case of sigmoid activation function, if we see the sigmoid activation function, the value ranges between 0 to +1. So, let's say if I have the value of sigmoid function as 0.6, that is here, then since 0.6 is more than 0.5 or it is close to 1, then I'll say as activate a neuron. Or if the value of sigmoid function is around 0.2, since 0.2 is close to 0, I'll say as don't activate a neuron. That's it. You'll understand more when we implement in a program in the future part of this course. So moving on, this is what we have learned in deep neural network. We have understood that just like we human beings has a sensory organs, we have the input layer to receive the data for the neural network. And just like the nucleus, we have the artificial neurons. And these neurons are connected together in the form of complex network. And they are stacked one next to another. And these three layers, that is red, green and blue, represents the hidden layers in deep neural networks. Inside these hidden layers, the information gets processed. Now, during the information processing, we make use of the concept called activation function to decide whether to fire a particular neuron or not. Now, using all the information which we get from these complete hidden layers, it will be transferred to the output layer to bring up the information that we got from the neural network. Are you clear with me here? Yes, that's how simple the deep neural network means. Now, using all our understanding, let's get a visual intuition as how deep learning works. So this is a simple deep learning network which we are seeing on the screen. We have an input layer that is here, and we have a single hidden layer, and we have an output layer. Now, this input layer is receiving the image of dog. The input received from the input layer is transferred to the hidden layer. Inside the hidden layer, the information gets processed and transferred to the output layer. Now, using the value which we receive in the output layer, we will be able to decode as whether the output received is a picture of dog or whether it is a picture of cat. In our case, our deep learning neural network is able to classify as dog. Now, how this classification happens, what are these input layers, what are all these output layers, how does this hidden layer works, everything is a black box as of now. We'll understand in detail in the further sections of this course. For now, the basic idea is this. The deep learning neural network will have three important layers: input layer, hidden layer and output layers. The input layer receives the input, the hidden layer processes the information, the output layer will give the output. Are you clear with me? Yes. Now in this particular simple example, I can say as we have 3 neurons in the input layer, and we have 4 neurons in the hidden layer, and we have 2 neurons in the output layer. That's how simple it is to work with deep neural network, guys. So we now know as what deep learning system means. Now let's look at the different applications of deep learning. Some of the applications are automatic colorization of black and white images, guys. So previously, before the deep learning, when you wanted to colorize a black and white image to color photograph, it was taking a lot of human effort. But with the use of deep learning, we are able to colorize the black and white photos very easily and very effectively. And the another example which I want to point out is that automatic machine translation. I have explained already in the start of the lecture as Facebook machine translation. And in this example, it says like Morak chocolate, and when it is passed through deep learning system, it is able to convert as dark chocolate XL cookies. That's how powerful the deep learning system is. And apart from this, the deep learning systems are used in object classification and detection in photographs, which we see here. Like this is an image of dog with a hat, and the deep learning system is able to classify the image correctly. So it is able to draw a box around the dog and say it as dog, and it is able to draw a box around the hat and say it as hat. And along with this, one of the other applications which we see are the automatic image caption generation. So here in this image, it says like man in black shirt is playing guitar. Construction worker in orange safety vest is walking on road. Now in all these examples, we did not explicitly tell the system as, hey, this is what a person means, this is what a black shirt means, this is what a guitar means. We did not tell them. The deep learning system learned automatically using all the data which we have been provided to the deep learning system. Now if you're really interested to understand the power of deep learning, I recommend you to watch the Google DeepMind's AlphaGo movie on Netflix, guys. You'll understand the true power of deep learning system. Now using the deep learning algorithms, the AlphaGo, that is the computer system, was able to defeat the Lee Sedol, who was the champion of Go. I recommend you to watch it. It's superb, guys. With this, we come to the end of this class. On the next class, we are going to understand the basics of machine learning. You can reach out to me at instructor@manifoldailearning.in, and for corporate inquiries, you can reach us at support@manifoldailearning.in. I look forward to see you in the next class. See you guys.
Hey everyone, welcome to the class 2 of Deep Learning 2020. In the last video, we have learned about the differences between deep learning system, machine learning system, and then artificial intelligence. In this video, let's have a quick understanding as what it means by machine learning system. So this is what we had learned about the machine learning system. We learned that machine learning is a subset of artificial intelligence. And we use this technique to understand the data and find the patterns in it so that we can take an informed decision. So this is the simple definition of the machine learning. Now we can classify this machine learning system into many ways. And one of the way we classify the machine learning systems are with the way the data is used. On the basis of data used, I can classify the machine learning system into 3 types. They are supervised machine learning system, unsupervised machine learning system, and semi-supervised machine learning system. In case of supervised machine learning system, the data expected by the machine learning system is input data as well as output label. Let's say I'm building a machine learning system which looks at the X-ray images and tells us whether it is a cancer image or not. That means my machine learning system has to look through the image data and tells me whether the region that has been captured by the X-ray image contains the cancer cells in it or not. Then in that case, to be able to use inside the supervised machine learning system, then my data should have the input data, that is the image data, as well as the output data, which is nothing but the information which says whether it is a cancer image or not. Got it? Or to give you one more example, let's say I'm building a sentiment classification machine learning system. So what it does is, it takes the text from the user and tells us whether it is a positive text or the negative text. Or in other words, to make it very simple, let's say I want to classify a particular tweet, that is tweet which we see in Twitter, into whether it says a positive or the negative. Then in that case, in case of supervised machine learning system, then the data which I'll be using for a supervised machine learning system would be the input data, that is the tweet data, which is in the form of text, along with the data of the output, which says whether it is a positive text or the negative text. So to summarize, in case of supervised machine learning system, we expect the data to have both input labels as well as output labels. Now moving on, the next different type of system which we have is unsupervised machine learning system. Now this is the special type of system. I call it as special because in case of unsupervised machine learning system, we simply pass the data to our model, but we don't know what is the output that we expect from the model. So it's like a black box. So to give you an example, let's say I have the shopping data from a particular website, let's say Amazon.com. Now I pass all the login information of the website to my machine learning system. And what I expect from my machine learning system is my machine learning system should analyze the data and gives me the pattern and gives me the insights from it so that I can use it for my business. The insights can be saying that the user logged in after 6 p.m. will tend to buy more, and the users between the age of 20 to 30 will prefer to buy the gadgets. Now, in case of unsupervised machine learning system, the data which I give to my machine learning system will contain only input data. And the thing is, I don't know what is the output that I should expect from this data. To give you one more example of an unsupervised machine learning system, let's say I have a daily sales data. So this is the data which displays the daily sales made by a OnePlus showroom. So on 1st of January, it has made around 25 units of OnePlus 8. On 2nd of January, it has made sales of 30 units of OnePlus 8. And in the same way, on 3rd, it is 45, on 4th, it is 50. So this is the data that I have. Now, using this data, what I'll do is, I'll pass into my unsupervised machine learning system and I'll ask it to forecast. That means find a pattern in all these data and then help me in predicting the next outcome. That means the sales on the 11th of January. So to summarize, in case of unsupervised learning, I'll only give the data and the system predicts a pattern automatically. To explain the concept of supervised learning, let's say I have the data like this. So the data looks something like this. I have the patient information, his age, sugar, and whether he has a BP or not, and whether the operation was successful or not. Now, for patient 1, it says his age is 25, he has sugar, and he has a BP. And the data says whether the operation was successful or not. For this patient 1, the operation was successful. In the case for patient 2, he has 30 age and he doesn't have sugar, he doesn't have any BP, and the operation was not successful. Now using this data, since if you observe here, we have both input as well as output. Now using this data, we will train the supervised machine learning model. Then after the training, what we will do is, we will pass the new data. That means we will try to predict the outcome of a situation. So in this case, let's say we will try to predict what will be the outcome of the operation if a person who is of age 30 and who has a sugar condition and who has a blood pressure, whether his operation will be successful or not. So in case of supervised machine learning system, the data which we send to our machine learning system will have both input features as well as output labels. But in case of unsupervised machine learning system, we only send the data to the machine learning system and we expect the machine learning system to gain the insights from the data and give it to us so that we can use it for our business development. So this was about the differences between supervised learning and unsupervised learning. Now the another type of classification in machine learning system with the perspective of data is semi-supervised machine learning system. In case of semi-supervised machine learning system, the data that we send to the machine learning system will contain the labeled information as well as unlabeled information. So one way you can think of is like you can think of the Google Photos app. So if you have uploaded a group of pictures, let's say 100 pictures of yours, if you label on one of the data, then the same label will be applied to your other 100 photos as well. So that is an example of a supervised machine learning system. So to summarize, I can classify a machine learning system into 3 types: supervised, unsupervised, and semi-supervised.
In case of supervised machine learning system, my data will contain both input labels as well as output labels. And in case of unsupervised machine learning system, I'll only be sending the data. And in case of semi-supervised machine learning system, I'll have a few label data, that means few data which contains both input label as well as output label. So with the use of learning algorithms and loss functions, we would be able to arrive at the specific values of the parameters of the model such that the relationship between input and output can be established. Now, after we establish the relationship between input and output with the use of machine learning model, we will evaluate the model to understand how our machine learning model is performing. Now, coming to deep learning, instead of a single model which we see here in case of machine learning, we will have series of neurons, and these series of neurons are connected together in the form of network. And all the other parts of the deep learning will stay the same. That means even in case of deep learning, we'll be having the data, and based on the data that we have and based on the task that we want to achieve, we'll be building the neural network, and based on the task, we will specify what will happen in the output layer. And even in case of deep learning, we'll have the learning algorithms and the loss functions. So with this introduction in place, in the next video, let's understand and build the first neural network using the Tensorflow, guys. If you have any questions, shoot me an email and I'll respond to you. So I'll see you again next time. Thank you. Hey everyone, welcome to the class 3 of Deep Learning 2020. In this video, we are going to build our first deep learning neural network. Now, recalling from the last video, we have learned that there are 5 parts in any machine learning model. So we have learned as the 5 parts are data, task, model, learning algorithm and loss function, and then evaluation function. Now, based on the data, we will be deciding the task that we are going to perform. So in our case, we are going to make use of MNIST dataset. To begin with, I'll start by importing the necessary library. In this course, I'll be making use of the TensorFlow 2.0. So I'll start by importing like this. So I'll write as import TensorFlow as TF. So this will import the TensorFlow. I'll display the version of it. So I can write as tf.version. So the version that is available to me is 2.2.0. Okay, we have imported the library. Now, as a next step, what we have to do is we have to decide on the data. As I said already, we are going to make use of MNIST dataset. Now, what is this MNIST dataset? So this is the page of official MNIST database. So it says it is an MNIST database of handwritten digits, and it has a training set of 60,000 examples and has a test set of 10,000 examples. So if we open the sample images of MNIST, it will look like this. So these are the samples of MNIST database. It contains the handwritten digits. So as you can see, we have the handwritten digits between 0 to 9. So this particular column shows the 0, and this has 1, 2, 3, 4, 5, 6 up to 9. So the task for us is, I'll have to identify whether this particular image, in this case, if I select a particular image, let's say this one, then my task will be, if I have this particular image, then I'll have to classify this image to be belong to the class 0. In the same way, if I have been given the task to what is the classification of this particular digit, let's say this particular image, this one, then my task will be to identify to which class this particular image belongs to. In this case, it is 6. Similarly, if I have been given to find what is the classification of an image which belongs to this, that is, which looks like this, then my task will be assigning the value 4 to this image. So if I come back to this slide, the 5 parts of machine learning program, I have the data as MNIST dataset. Now, by looking at the data, I can say the task that we are going to perform is classification, because I want to classify the output label into one of 10 labels. See, the 10 labels are 0 to 9, and I'll have to classify each image into one of 10 labels. So the task is classification.
Now coming to model. In case of machine learning, we'll be selecting a single model which says linear regression, random forest, or any other model. But in case of deep learning, as we have learned in class 1, deep learning contains a series of neurons which are connected together in the form of a network. It will have an input layer and it will have the hidden layer as well as it will have an output layer. The input layer takes the input, the hidden layer processes the information, and output layer will give the output from the neural network. So let's build a neural network and understand more about this particular data set. To begin with, let's start by loading the data. So I'll load the data like this. This particular MNIST database is available inside the Tensorflow itself. So I'll write it like this. So to import, I'll write as from tensorflow.keras.datasets import MNIST. So this will download the MNIST object, and then okay, there's an error. Okay, this has loaded the MNIST object. Now I'll separate the training images and the test images like this. So I'll write as train images, comma, train labels, then test images, comma, test labels is equal to MNIST dot load underscore data. So this will download the data and assign the training images and the training labels to these two elements in the tuple, and assign the test images and the test labels to these two variables inside the particular tuple. So what we can do is, let's verify the size. Okay, so I'll write it like this. So train images dot shape. So the shape of the training images is 60,000, 28, 28. That means each image is of the size 28, 28, and I have 60,000 such images. To give you more clarity, so if you see this particular example, I have around 100 images. So like this 100 images, in our training set, we have 60,000 different images. If I display an individual image, so let's say train images 0. So this is the first image from the data set, and shape. So I have the output as 28, 28. That means each image is of the shape 28, 28, and in train images, I have 60,000 such images. If I look at the train labels which are associated at index 0, then the value is 5. That means the image which is at first position in the train images is having the label of 5. So if I print as length of train images, so this is 60,000 and length of train labels is 60,000. That means each image has a single label. Got it? Cool. Now moving on to the test data. So if I display the shape of test data, so test images dot shape. So this is of shape 10,000, 28, 28. That means we have 10,000 images in the test data, and each image is of the size 28, 28. So in the same way, the length of test labels will be 10,000. See, this is 10,000. So what we have done is, we have imported the TensorFlow STF, and to load the datasets, I have made use of tensorflow.keras.datasets, that is MNIST object. And to load the dataset, I have called the function load underscore data. And then I have performed the split between train and test data. And actually this is not the split. I just separated the training data and the test data. And after separating the training data and the test data along with its images and the labels, I have the resulting shapes of train images as 60,000, 28, 28. And the train, that is individual images, is of the size 28, 28. And in the same way, I have 10,000 images in case of test images, and each image is of the size 28, 28, and the length of test labels is 10,000. So we have loaded the dataset for our working. np.max. So this time I'll give as train
images 0. In the same way, I'll give as np.min train images 0. That means I'm checking what is the maximum value that each image has, and I'm also checking what is the minimum value that each particular image has. Since this is a black and white image, I have the values between 0 to 255. Now what we will do is, as per data pre-processing, we will divide the entire train images and the test images by 255 such that the resulting values would be between 0 to 1. We are doing this because, see, if you see here, like we have the values ranging between 0 to 255. Then like when we apply the deep neural network which has many number of neurons, then in that case the values may simply go high. To avoid that, what we will do is we will normalize it by dividing by 255 such that the values would range between 0 to 1. So to do that, I'll just write it like this. So I'll write as train images is equal to train images dot as type float divided by 255. In the same way, I'll write as test images is equal to test images dot as type float divided by 255. So I'll just set it as float 32. Okay. This has been completed. Now if we check the minimum and the maximum in each particular image, I can see the maximum is 1 and the minimum is 0. That means all the values are normalized for individual images. Now another pre-processing step which we do when we are applying the deep learning is converting the images which are in the form of matrices into a single long vector. To do that, we know already we can make use of the reshape function. So since we have 60,000 images, I'll reshape the 60,000 images like this. So this time I'll write as train images is equal to train images dot reshape 60,000 28 multiplied by 28. In the same way, I'll write as test images is equal to test images dot reshape 10,000 comma 28 into 28. Okay, this has been done. Now if I print the shape of the first image, that is train images 0 dot shape, this is of the shape 784 comma blank. That means this is a single dimensional vector, that is single dimension array, which is of size 784. Got it? That means the entire train images is of the size 60,000 comma 784. This is because the individual images which was of the size 28 comma 28 has been reshaped into a single dimensional vector. Hence here I have mentioned as 28 into 28. Okay, so we have pre-processed the data by dividing it by 255 so that the values would range between 0 to 1, and then we have reshaped the data into 28 into 28. That means we have converted individual image which are in the form of rows and columns, that is which was in the form of matrices, into a single long vector. Okay, now let's do the another pre-processing step for the labels column. Now what I'll do is I'll write it like this: np.unique train labels. So if I give as np.unique train underscore labels, we can see the labels, the different labels which are present are 0 to 9. In the same way, if I write as np.unique train test underscore labels, we have an array which has the values between 0 to 9. That means my train label and the test labels has the classification labels as 0 to 9. As a part of pre-processing step, what we will do is we will convert these labels into one hot encoding. Now what it means is, like, let's say if I have the columns like this. So this is an example of the classification problem. Let's say if we have the column labels as red, yellow and green. As you can see, the red has repeated twice. So the red has repeated twice, and we have an yellow here and yellow here, and we have a green here. So this is an example of a classification problem. Now what we will do in case of one hot encoding is that we will put all the unique values in the output labels as individual columns in a matrix, and then
whichever the value is present for that particular line, we will mark as 1. If you see here, in first case, the label is red. Hence, if you see in the first row here, on the red value is marked as 1. In the same way, for the second row, we have it as red. Hence I have marked as 1 in the column red, and rest I have marked as zeros. And on the third row, I have the value as yellow. Hence, in my one hot encoding box, I have mentioned as 1 for the yellow column. In the fourth row, I have the value as green. Hence, in my one hot encoding, I have mentioned as 1 for the green column, and remaining all the columns as 0. Now to convert this particular label data which we have into the categorical vector, we convert it with the use of inbuilt toCategorical function. So I'll write as .keras.util import toCategorical. So after importing the toCategorical function, we will just convert the train labels and the test labels into one hot encoding vectors like this. So I'll write as train underscore labels is equal to toCategorical in the same way. I'll write as test underscore labels is equal to toCategorical test labels. So what this will do is, this will convert the train labels and the test labels into one hot encoding vector form. Now after converting it into one hot encoding form, if I write as train labels of 0, then we have the one hot encoding vector like this. As you can see, we have 10 zeros. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is of length 10. Now we have a value of 1 for one of the index. So let's check that index number. So the index is 0, 1, 2, 3, 4, 5. So for the fifth index number, we have the value equal to 1. That means the label which is referring is to the value 5. To verify this, I'll open the screen which I had already opened. So if you see here, yeah, I had displayed the train label which was at index position 0. So it had the value of 5. Hence, this value 5 has been converted into one hot encoding vector of the form like this. So all the values equal to 0 except for the value at index position 5, which is equal to 1. Got it? So we have done two things as a part of data preprocessing. So first is, we have normalized the data and reshaped it, and second is, we have converted the output vector into one hot encoding vector. Okay, so with this, we are done with the two important tasks of the machine learning or any deep learning, that is data and task. So the task we have is the classification, and the data which we are using is an MNIST database, and it is a classification problem, and we have pre-processed the data as per our requirement. Now as a next step, let's build our first deep learning neural network model. So to create the deep learning neural network model, I'll write it like this. As a first step, I'll import the models and layers as from tensorflow.keras import models. In the same way, from tensorflow.keras import layers. So this will import the models and layers from tensorflow.keras. And then I'll instantiate the model as network is equal to models.sequential. So what it means is, like, I'm trying to create a model which is of sequential pattern. That means which are stacked one next to another. So if you see the diagram here, I have the layers which are stacked one next to another. So I have the input layer, and this is stacked with another hidden layer, and this is stacked with another hidden layer, and this is again stacked with another hidden layer. Hence, I have written a neural network which says models.sequential. And then after defining the models as sequential, I'll add individual layers. For the first layer, I'll write as network.add. That means I'm adding an individual layer to my existing sequential model. So network.add layers.dense, and inside the parenthesis, I'll write as, here see,
The first parameter is units. For the number of units, I'll write as 5. For activation, I'll write as ReLU, and then I'll input the input shape as 28 into 28, which is a single dimensional vector. Got it? So here what I'm doing is I'm adding a new layer to my sequential model, and this is of the type dense. Dense means fully connected deep learning network. If you see here, can you see like the red dot is connected to all the green dots, and each individual red dot is connected to individual green dots. In the same way, each individual green dot is connected to all the blue dots which are in the next layer. That means it is in the form of dense. So that is what I'm saying here. I'm saying as layers.dense, and then for the number of units, I'm mentioning it as 5. That means I'm having 5 units of neurons in this particular layer. And this takes the input, which is of the shape 28 into 28. That means 784 comma blank. That means a single dimensional vector which is of shape 784. Why? Because this is same as the individual shape image that we have. Got it? So after adding this first layer, I'll add a new layer as network dot add layers dot dense. That means I'm adding one more dense layer, and this time it has 10 units, and this time it has the activation as, let's say, another ReLU. And after this I'll add one more network. So this time I'll write as network dot add layers dot dense, and for the I'll consider it to be a last layer. So for this layer I'll write as number of units to be equal to 10, and activation is equal to softmax. Now I'll stop here because I have defined it to be an output layer, and I have set the number of units in output layer to be equal to 10. This is because I want to classify each input that I have, that is in case of each image which is of the shape 784 comma blank, that is 784 items. I want to understand the values present in each image, and I have to classify into one of 10 classes. Hence in my output layer I have mentioned as 10 units. So I'll repeat this again guys, because this is very important. First, I'm initializing my network to be of sequential. After initializing my network as sequential, I'm adding the individual layers. In my first layer, I have added 5 units, and this has the activation as ReLU. And for that, I have also specified the input shape to be equal to 28 into 28. That means 784. I have added a dense layer with 10 units and activation function as ReLU. And in the final layer, I have added 10 neurons. That means 10 units of neurons, and with the activation as softmax. The reason I have added softmax because the output that I get from the softmax activation function will be the probability distribution between 10 values. Since the output layer has 10 neurons, I get the probability distribution of 10 values. So in my case, if I input the image presented index position 0, then in that case, I get the probability for the value 5 as highest. So with this, we have defined a neural network. So this particular third part is complete for the deep learning. Now the next step would be defining what will be the learning algorithm, loss function, and the evaluation metric for my deep learning network. To define that, we will make use of compile function. So to compile a neural network, we will write it as network.compile, and inside the parenthesis we will define the parameters. So for the first parameter learning algorithm, I'll write as optimizer is equal to, I'll write as RMS prop, and for the loss function I'll write as categorical cross entropy, and for the metrics, that is evaluation, I'll write as accuracy. So with this, we have defined 5 parts of any machine learning model. So I have the data, and I have decided the task to be classification, and I have defined my neural network with 3 layers. So the first layer has 10 neurons with the input shape as 28, 28, 28 into 28, activation as ReLU. And in second layer, 10 neurons with activation as ReLU. And in my final layer, I have 10 neurons with activation as softmax. So I have defined my model, and the learning algorithm is RMS-prop. Loss function which I'm using is categorical cross entropy, and the matrix is accuracy. Got it? Now I'll compile my network. Now I'll fit my model. So for that, I'll write as network.fit, and inside the parenthesis, I'll write train labels. So first train images, that is for X it is train images, Y means train labels, batch size I'll give as 64, and epochs I'll give as 5. So train images, and the Y I'll write as train labels, and for batch size, like I said, I'll give 64, and epochs I'll give as 5. Okay, I'll execute this. Okay, this will take some time based on the system performance. Oh, awesome guys. Okay, it's performing well. Okay, the execution has been completed. So now let's perform the evaluation on the test data. So I'll write as test underscore loss, test underscore accuracy is equal to network dot evaluate, and I'll pass the test images, test labels. Okay, this is done. I'll print the test accuracy is okay, we have the test accuracy as 86.59%. Well, with the first deep neural network that we have built, I think this is one of the best guys. So we'll try again, and we'll learn more as how to perform better and how to get the more accuracy in a deep neural network. But I hope you now have an idea as how to build a deep neural network using TensorFlow. To summarize, what I've done is I've first imported the TensorFlow as TF, and I've just verified the version, it is 2.2. And then I have loaded the dataset MNIST. After loading the dataset, I have separated the train labels and the test labels along with its images. So I have separated train data and the test data. And while splitting between training and test, I have also splitted as images and labels the images of the shape 28, 28, and total we have 60,000 images, and we have 10,000 images in test. And we have done some data pre-processing. So the maximum value is 255 and the minimum was 0. Hence we divided the entire training data and test data by 255 such that the value would range between 0 to 1, and we could verify it here. And after that, we have reshaped into a single long vector. So that means each individual vector which was in the shape of 28, 28, and we have converted into 60,000 into 784. That means we have converted the image which was in the form of 28, 28 into 28 into 28. That's it. And after that, what we have done was we have created one hot encoding of the output vector. So in our case, we had the unique values as 0 to 9 in case of both training labels and the test labels. So what we have done was we have made use of two categorical function which was present inside the tensorflow.keras.utils, and we applied the two categorical on training labels and the test labels. And after that, we could verify that the labels, that is each training labels and test labels, has been converted into one hot encoding vector. So we can verify it over here. So if I give as train labels dot shape, so this will have the shape as 60,000 into 10. See, this is because each individual value which we had previously has been expanded into a vector which is of size 10. So the individual value which we had before was 5, and this is how it looks like after converting into a one hot encoding vector. And after that, we defined our model. So we have defined our model to be sequential form, and we have added the network. We have added the dense layers. In the first layer, it had 5 units and activation is ReLU, and input shape is 28, 28, sorry, 28 into 28. And the second layer 10 with activation as ReLU. On the third layer, I have 10 neurons with activation as softmax. After that, I have defined the learning algorithm to be RMS prop, loss function to be categorical cross entropy, and the matrix is accuracy. And after defining all the model and the compile, that is all the necessary parameters in any machine learning model, I have performed the fit on our data. So I have specified the train images and the train labels for the training, and I have fit for 5 epochs with the batch size as 64. After performing the fit on training data, I have performed the evaluation on the test labels and the test images. So the test accuracy was 86.59%. So this was about our class on building the first deep neural network, guys. So if you have any questions, you can reach out to me at instructor@manifoldailearning.in. For any queries on any of the subject, just reach out to me on this email. Thank you guys. I'll see you next time. Hey everyone, welcome to the class 4 of Deep Learning 2020. Now in the last video, we have learned as how to create a neural network. So what we did was we instantiated a model as sequential, and then we stacked one layer next to another. So in the first layer, I had specified as 5 units of neurons, and this had the activation as ReLU. And this takes the input of the shape 784. That means it takes a single dimensional vector with the shape of 784. And in the second layer, I have specified as 10 neurons, and that will have the activation as ReLU. Now in the third layer, I have mentioned as 10 neurons with the activation as softmax. So what I'm currently doing is I'm defining my model as sequential, and I'm stacking one next to another. That means I'll define a layer and then I'll stack that layer with another layer. Now to build more intuition as how we build this particular network, now let's consider this particular deep neural network which we see on the screen. So as we can see, this takes 4 input. So the input size, I can say it has 4. And in the first hidden layer, it has 5 units of neurons. And in the second hidden layer, it has 4 units of neurons. And in the third hidden layer, it has 3 units of neurons. And in the final layer, I have a single output neuron. So using our understanding from the last video, let's build a deep neural network which looks like this. So if I'm defining a deep neural network which looks like this, then I'll have to write it as, so this time I'll write as network is equal to models dot sequential. That means it's a sequential model. And then in the first layer, so I'll write as network dot add layers dot dense. That means it's a fully connected dense network. And layers dot dense, as we can see in the first hidden layer, I have 5 neurons. So I'll write as 5. And then even for this time, I'll mention as activation is equal to ReLU. That means it's a ReLU activation function. And this will take the input of shape. As we can see, we have only 4 units as input. So I'll write as 4. Got it? I have defined my first layer in my deep neural network. This takes 4 inputs and my hidden layer has 5 neurons. So this has been completed. Now I'll add in another layer. So for the another layer, I'll write as network.add layers.dense. And in the second hidden layer, I have 4 units. So I'll write as 4 and activation as ReLU. And on the next layer, I'm having 3 units of neurons. So I'll write the same. So network.add layers.dense 4 instead of 4, I'll write as 3. And on the final output layer, we have a single neuron. So what I'll do is instead of 4, I'll change it to 1. And instead of ReLU, I'll write as sigmoid. So what I'm doing is I'm defining my model as sequential model, and then I'm stacking layer next to another. In the first layer, I have specified the input of the shape 4, and this has the activation function as ReLU. And in the second layer, I have mentioned as 4 units with the activation of ReLU, and in the third layer, I have mentioned the activation function as ReLU with 3 units. And in the final output layer, I have specified the number of units of neuron as 1 with the activation as sigmoid. Okay, so I'll just execute this. Okay, now if I display the summary, See, so it says in the first layer I have 5 units of neuron and the total number of parameters is 25. And in the second layer I have the 4 units and the total number of parameters is 24. And in the third layer I have 3 number of units and the total number of parameters is 15. And in the final layer I have a single neuron and the total number of parameters are 4. Like, now you might be wondering how this number of parameters will be calculated, isn't it? Well, to answer that, you need to know one important thing. The thing is, you should know what happens when a data is passed into a deep neural network. Now, whenever a data is passed into a deep neuron, let's say a particular single neuron, two things takes place. One, linear operation, and two, activation. Now, let's take step by step. Now, when I say it as linear function, what it means is like multiplication of weights vector with the input values added with bias term. So it is Wx plus C, where W is weights, X is input, and C is bias. To give you more clarity, let's say I have an input like this. So to demonstrate this, I'll write as input numpy as np and x is equal to np dot random dot rand int, values as 10 20 10, and let's say I have the weight matrix which is of the form w is equal to np dot random dot rand n, and this is of shape 10. So after creating, if I display x, it looks like this and w would look like this. So x is an numpy array which is of shape 10 and this has the random values distributed like this. Now when I say it as linear operation, what it means is like it will multiply the weights vector with the input vector and then it will add the bias term. For that understanding, let's say I have the bias term C as 3. Now the way this resultant value will be calculated is like this. So to just give you the clarity, I'll write O is equal to, I'll do the list comprehension. So I'll write as W in multiplied with X in plus C for X in comma W, sorry, for W in comma X in zip of W comma X. So what I'm doing is I'm getting the individual values from W and X, multiplying it each other and then adding the bias term. In this case, bias is C. So after this, if I print the value of output, so this is the output that I get once I perform the linear operation. Now after performing the linear operation, the next step which I perform is activation. So if you see the deep neural network which I have mentioned, in the first 3 layers, I have mentioned the activation as ReLU. What it means is like the ReLU activation function would look like this. It just takes the maximum of 0 and the value. So if the value that I have is more than 0, then I'll consider that particular value as the output. If it is less than 0, then I'll consider it as 0. That's it. So if I want to write it in a hands-on way, so for that I'll write a function which looks like this. So I'll define ReLU and this takes an x and this would return np dot maximum 0 comma x. That means it will just return the maximum out of the particular value which I'm sending to this particular function. So if I pass ReLU on my output value, so this is the output that I get if I pass my input into the neuron. Got it? So what it does is it will perform the linear operation followed by activation. In this particular example, I have performed the ReLU activation function. If I want to perform the sigmoid activation function, so the sigmoid function would look like this. So it is calculated as 1 over 1 plus e power minus z. So in the same way, if I want to implement the sigmoid, I can write it like this. So def sigmoid of x, and the way it will return is return 1 over 1 plus np dot exp minus x. So this will return the sigmoid value of the output. So now to calculate the sigmoid output, that I can simply give as sigmoid, and then I can pass the value that I get from the linear operation. In this case it is O. Okay, so I'm getting an error. Okay, I'm getting an error because the data which I'm passing is I'm getting this error because the data that I'm passing into this particular sigmoid function is a list. So I'll just convert it into numpy array before passing. So I'll just write as np dot array. So I'm passing it as, I'm converting it to numpy array before passing to sigmoid function. So this is the value that I get if I perform the sigmoid activation function. So what it happens is, whenever I define any particular deep neural network, when the data is passed into the deep neural network, in each layer it will be performing linear operation and then activation function. Linear operation is nothing but multiplying the weight matrix with the input vector plus adding this bias term. So I can say as wx plus c, where w is weights, x is input, and c is bias term. Got it? So we have now understood as what is the mathematical operation that takes place inside each neuron. Now let's understand these values that we have here. If you see here in my first layer, it says that total number of parameters is 25. Why is it? Let's calculate it. So if you observe here, in my first layer, I have the input shape as x. That means in first layer, the number of x, that is number of inputs, is 4. And since the number of inputs is 4, then the value, that is the number of weights, will be 4. And in my first layer, I have 5 units of neuron. Since 5 is the number of neurons, each neuron will have its own bias. Hence, 5 is the number of bias term. So, total number of parameters is equal to number of units of neuron multiplied with number of units of input. In this case, number of units of neuron is 5 and the number of value in the input layer is 4. That is, I'm sending the value of the length 4. So 5 into 4 plus 5. Hence, the resulting value in the first parameters is 25. 5 into 4 plus 5. That is number of units in the first layer multiplied with length of the input, that is 4, plus 1 bias term for each neuron, that is 5. Hence, I have the total value as 25. In the same way, if I calculate it for the second layer, the total number of parameters I can say as, see, in the second layer, the number of input layers will be the first layer, isn't it? So if you see the input, the number of values or the number of input units is 5. So 5. So the number of units of neuron in the second layer is 4. So 5 into 4. So because the number of units are 4 in the second layer, then the number of bias terms will be 4. So the total will be 5 4s are 20, 20 plus 4 is 24. In the same way, for the third layer, the second layer, that is the number of units in the second layer, will act as the input for the third layer. So in this case, it would be 4 into 3 plus, since I have 3 neurons in this particular third layer, 3 will be the number of bias terms. So this will be equal to 4 into 3 plus 3, then 12 plus 3, 15. In the same way, for the last layer, the number of units in previous layer is 3 and the number of units in this particular layer is 1. So 3 into 1 plus the number of bias terms will be 1. So 4. I hope you now know as how the number of parameters are calculated in a deep neural network. So we multiply with number of inputs with the weight matrix plus we will add it with bias terms. Got it? Awesome, guys. Now let's come down. So if you come down here, yeah, after performing, that is after defining the network, I am performing the compile operation. Now inside the compile operation, I am mentioning three parameters: optimizer, loss function, and metrics. Optimizer is nothing but the learning algorithm, and the loss here in this case I have mentioned as categorical cross entropy. I have made use of the loss function categorical cross entropy because this is a multi-class classification. If I'm using a binary class classification, then in that case, the loss function which I'll be using would be binary cross entropy. So depending on the task that I have, I'll be making use of the respective loss function. Now the way that I'll be reaching at the best value of parameters is by minimizing the loss value. So in this case, I'll be reaching the values of best parameters by making sure that my loss will be minimized. So these are some of the basic concepts in deep neural network, guys. I hope you find this video helpful, and in the next video, let's build some more deep learning network and work on other types of problem. And again, I'm telling you, if you have any questions, reach out to me on this email ID, instructor@manifoldaIlearning.in. Thank you so much, guys. I'll see you next time. Hey everyone, welcome back. So we now know as what is deep neural network. So a deep neural network will contain majorly four important things. They are input layer, hidden layer, activation, and the output layer. The input layer receives the data given from the outside world, and the hidden layer gets the data from the input and then process the information, and based on the activation that is present on each neuron, it processes the information and sends the output to the output layer. So this is what we know. But the question is, how does it actually work? That is, how an input that I send to my input layer, how does it get processed inside this deep neural network which you see here? So how does it gets processed inside these layers, and how can I get an output? So since analyzing this whole deep neural network is little confusing for the first time, let's do one thing, guys. So let's get a single neuron and let's learn from the single neuron as how it receives the input, how it processes the information, and how it produces the output. Once we analyze as how a single neuron works, we'll increase the complexity and understand as how this deep neural network works. Okay, so to begin with, let me consider a single neuron. So let's say I have a neuron which looks like this. So I'll call this as a neuron N. And this single neuron takes two inputs. I'll call them as X1 and X2. When I say it as neuron, what it normally will have is like, when it receives the input from the input layer, it will normally perform two important things. They are summation and the second one is activation. And whenever it is performing this summation and activation, so it will also have one more component that is known as bias. Okay. Now, when I say it as summation, what it means is like it is a weighted product of the inputs plus the bias term of that particular neuron. So if I say it as summation, what it means is like, let's say if I have the weights as W1 for X1 and W2 for X2. So the summation part means W1 X1 plus W2 X2 plus B. So here B is nothing but the bias term. And once this summation operation is done, we'll perform the activation on this particular summation. So if I have a activation function as sigmoid, so if I have an activation as sigmoid, so this is nothing but, after performing the activation, it is nothing but sigmoid of sigma. So in other words, if I represent this in the sigmoid equation, this is nothing but 1 over 1 plus e power minus of W1 X1 plus W2 X2 plus B. So this is what will be the output of a single neuron with the activation of sigmoid. So if I want to represent in my original neuron representation, so this will have an output which is nothing but y hat. So here I can now say as y hat is equal to 1 over 1 plus e power minus of w1 x1 plus w2 x2 plus b. Now I'll repeat this again, guys. Whenever an input passes through a neuron, two things takes place. First is summation and second one is activation. In my case, I have chosen a neuron with sigmoid activation. So as a first of summation, what it does, it is nothing but the linear operation. So what is linear operation? Linear operation is nothing but weighted product or weighted product of inputs plus the bias term. So that is nothing but w1 x1 plus w2 x2 plus b. And second step is activation. In my case, since I said that this neuron is having the activation function of sigmoid, that means whatever the value that I get as a summation, that summation will be used as 1 over 1 plus e power minus of w1 x1 plus w2 x2 plus b. If I want to represent the sigmoid in an equation, I can say as 1 over 1 plus e power minus z. So here z is nothing but the value that I get after I perform the linear operation. Got it? Now to give you a better understanding of this, so let's say if I have a input, say x1 as 1 and x2 as 2, and let's say I have the w1 as 10 and w2 as 20, and let's assume the b term as 1, then y hat is nothing but 1 over 1 plus e power minus of w1 x1 plus w2 x2 plus b. In other words, I can write as 1 over 1 plus e power minus of w1 x1. So w1 is 10, x1 is 1, so 10 plus w2 x2, 20 into 2, 40 plus b term is 1. So this is nothing but 1 over 1 plus e power minus 51. So if I compute it, this is the output of my sigmoid neuron. So since I'm using the sigmoid function, that is sigmoid activation, the output will fall between 0 to 1. Now this operation, that is finding the y hat, so that is finding the y hat from weighted average, and then this activation is known as forward pass. And if I change or if I adjust the parameters of my particular model during the training with the use of gradients, then we'll call them as backward pass. So don't worry about these terms, that is forward pass and backward pass. We'll come back to these concepts again in the future videos. For now, I want you to understand this basic concept. So to summarize of this today's class, I can say as if I consider a single neuron with two inputs, a single neuron or in any neuron, basically two things takes place: summation and activation. When I say it as summation, it is nothing but weighted product of input plus bias term. So when I say it as weights, so each feature of the input that we receive will have each weight, and individual neuron will have a single bias. Okay. And when I say it as summation, so it is nothing but linear operation w1 x1 plus w2 x2 plus b. And when I say it as activation, we will just apply this, or we will just use this linear term and use it in my activation term. In my case, I have the activation as sigmoid. Hence, I have written as 1 over 1 plus e power minus of w1 x1 plus w2 x2 plus b. Now you might ask me, so what happens if I have a ReLU activation function? So if I have a ReLU activation function, so suppose if I call z as w1 x1 plus w2 x2 plus b, then we know that the ReLU means if the value is less than 0. So if the value is 0 or if the value is less than 0, then at that time the output will be 0. If the value is positive, then at that time the value will be positive, right? So I can represent it something like this. It will be 0 if z is lesser than or equal to 0, and the output will be, it would be z if z is greater than 0. So I'll represent this again, ReLU of z. So if we instead of sigmoid, if I have a ReLU activation function, it is nothing but ReLU of z is equal to, it would be 0 if z is less than or equal to 0. It would be z if z is greater than 0. Got it? Don't worry about various activations, but the core thing I want you to remember is this. So when we pass an input through a neuron, two things takes place: linear operation and activation. Okay? Cool. So I'll see you in the next class, guys. Hey everyone, in the last video we have learned as how a single neuron will predict the output. So what we have learned is, whenever an input data is passed through a neuron, two things takes place, that is summation and then activation, isn't it? Now let's do one thing. Let's improve the complexity of a neurons, and then let's predict how the output will be predicted by a deep neural network. So let's consider this time. So let's say I have two neurons like this. So I have a neuron and I'll call it as N1, and this N1 is connected to another neuron as N2. Now just like before, I'll have two inputs for my neuron N1, X1, X2, and this N1 is connected to the N2 neuron, and finally the output will be predicted from my N2 neuron. So I'll call this as a Y hat, which is nothing but the output. Since X1 and X2 are the input, I'll call W1 and W2 are the weights with respect to the inputs X1 and X2. Since each neuron will have its own bias, I'll call B1 as a bias of N1 neuron and B2 as a bias of N2 neuron. Okay. Now, when I say that this is N2 neuron, the input of this neuron is the output from the first neuron. So I'll call H1 as the output from the first neuron, and let's say W3 be the weights with respect to the input which is being received from N1. So W3 is the weights and H1 is the input for N2 neuron. Now, how does this particular Y hat will be calculated? So this is the question. Don't worry guys, the concept is very simple. It is just like what we have learned before. So when a data passes through the neurons, two things takes place: summation, and second is activation. First, let's find the output of H1. So to find the output of H1, okay, as I said already, we need an activation function as well, right? So let's say I have the activation of both N1 and N2 as sigmoid activation. So let's consider the activation as sigmoid. So if I say it as sigmoid, it is nothing but 1 over 1 plus e power minus z, where z is nothing but the value that I get after I perform the linear operation. Okay, so this is the activation function that I have for N1 and N2. Now let's predict the Y hat. So to predict the Y hat, first I have to predict the output of N1. So output of N1, as I said, it is H1. So predict the output of N1. First I have to find the value of summation, which is nothing but I'll mention as N1. So for N1, linear operation. So I'll write as linear operation. So when it say it as linear operation for the N1, it is nothing but weighted average of the inputs plus bias term. So I can call as Z1 is equal to X1 W1 plus X2 W2 plus B1. So this is the value that I get after I perform the linear operation on my neuron N1. And the second step, that is activation. So after I perform the activation on this, I can call something as H1 is equal to 1 over 1 plus e power minus Z1. Okay, so H1 is
1 over 1 plus e power minus z1. Got it? Now let's do one thing. So we have found the h1. Now to find the value of the output of n2 neuron, so I'll write as n2 over here. Now to find the value of output of n2 neuron, two things takes place. Linear operation. So when I say it as linear operation, so I have the h1 as input, w3 is its weight, and b2 is the bias. So I can write something as z2 is equal to h1 w3 plus b2. So this is the resultant of linear operation on the neuron n2. The next thing, what is it? Activation. So activation. So if I perform the activation, what I get? I'll get the y hat, right? So I can write as y hat is equal to 1 over 1 plus e power minus z2. So this is the value of the output of my this entire neuron. That is, this is the value of the output for two neurons. So y hat is equal to 1 over 1 plus e power minus z2, where z2 is nothing but h1w3 plus b2, where h1 is equal to 1 over 1 plus e power minus z1, where z1 is equal to w1 x1 plus w2 x2 plus b1. So this is how we compute the value of a series of neurons which are connected together. So I hope you are clear with this concept, how we find the value of a collection of neurons which are stacked together. So guys, if you have any question on this topic, so please feel free to post it in the comment section. I'll be happy to help you, because this concept, that is linear operation and the activation, are very important parts in deep neural networks. Okay? Cool. So now let me do one thing. So let me increase the complexity. So this time, let's say I have a deep neural network or a network which looks like this. So I have two neurons or two inputs, x1 and x2, and this x1 and x2, this time it is connected to two neurons. I'll call them as n11 and n12, and these two neurons are connected to one more neuron. I'll call as n2, and from this n2 I'm having the output as y hat. So if I say this as a dense neural network, so n11 is connected to n2, n12 is connected to n2, and both x1 is connected to n1 and n12, and x2 is also connected to n11 and n12. So the weights which are connected to n11, I can call them as, let's say, w1, w11 and w12. So for this I can call them as w21 and w22. So these are the weights, and as we know already, each neuron will have its own bias. So I'll call b11 as the bias term for the n11 neuron, and I'll call b12 as the bias term for n12 neuron. The output generated by n11 neuron, I'll call it as h11, and the output generated by n12 neuron, I'll call it as h12. The weights of h11, I'll call them as, let's say, w21, and let's not call that as w21. So I'll call it as, let's say, w3, and h12 weights as w4. Okay, so we have a dense neural network like this. So I have two inputs, two neurons in the first layer, and on the second layer I'm having a single neuron, and all these neurons is having the activation as sigmoid. Okay, so this is just to keep it simple, and when I say it as sigmoid, I'll write it over here again, 1 over 1 plus e power minus z, where z is nothing but linear operation. Okay, cool. So now let's find the value of this y hat from our neural network. So let's start with finding the value of the output for the neuron n11. Okay, so here n11, so n11, as I said, linear operation. So If I call Z11 as a linear operation, it is nothing but W11 x1 plus, what is the other one? W21 x2 plus B11. Okay, and if I find the value of output, so the value of output from N11 neuron is H11. So I can write as H11 is equal to 1 over 1 plus e power minus of Z11, where Z11 is equal to this value. Okay, cool. So now let me find the value of output for N12 neuron. So if I say it as N12 neuron, two things takes place, that is linear operation and activation. So linear operation is nothing but Z12, let me call it as Z12. So the respective weights are W12 and W22. So I'll write as W12 x1 plus W22 x2 plus bias term is B12. And if I perform the activation on this Z12, so it is nothing but H12 is equal to 1 over 1 plus e power minus Z12. Okay. Now what is the output for this N2 now? So for this neuron N2, I'm getting two values. So two values are H11 and H12. So let me open it. Yeah, H11 is the input, H12 is the another input. So I'm getting two inputs, and this itself will have one more bias term. So I'll call it as B2 in this case. So this is the B2 is the bias term. So if I want to compute the value of output for N2, so for N2, I'm getting two inputs, H11 and H12. So I can say as Z2 is equal to H11 plus, what is the weights? Yeah, W3 plus H12 into W4 plus B2. This is nothing but the bias term. So y hat is nothing but 1 over 1 plus e power minus Z2. Okay. So in this way, we find the value of the output of a series of neurons which are connected together, guys. Now, if I want to update the value of any of the parameters, let's say H1 or W3, W4, B2, or W11, W21, W12, B11 or B12, we'll find the value of the gradients with respect to each parameter from the loss function. So let's dig more into this mathematical concepts in the upcoming videos. For now, I'll stop the today's class here. Let's continue more from the next video. Hey everyone, in this video, let's understand how we can find the total number of parameters in a deep neural network. So for the sake of understanding, I have taken the same deep neural network which we have seen in the last video. So in this case, I have two input, so x1 and x2, and this x1 and x2 are connected to two neurons, n1 and n2 in the first hidden layer, and on the second hidden layer, I have another single neuron which is called as n3, and the output from n3 neuron is the y hat, which is nothing but the output from my deep neural network. Now, let's do one thing. So whenever we are training any deep neural network, one of the important thing is we have to find the right parameters for the given input. So before we begin or before we find those parameters, let's understand as how many parameters will be there in a deep neural network and how we can compute the total number of parameters in a deep neural network. So as we have learned already, in any deep neural network, two things takes place: activation and summation. So now for a single neuron, how many parameters does it have? Well, for a single neuron, it will have the weights equal to number of features of input. So if I have, let's say, two features, then in that case, I'll have two weights. And for each neuron, I'll have a single bias. That means one neuron, it will have one bias term. In my case, for the N1 neuron, I'm getting two inputs. So two inputs are x1 and x2. Since I'm getting two inputs, the total number of parameters are, it will have two weights plus one bias term, isn't it? So this is the total number of weights for the neuron N1. Similarly, for the neuron N2, it will have the same. So the neuron N2 will have 2 weights since it's getting 2 inputs and 1 bias term. Now I'm coming to N3. For N3, N3 is receiving 2 inputs from N1 and N2. So the inputs are H1 and H2. Since it is receiving 2 inputs, so I can say 2 weights, and this N3 will have its own bias term. So in total, I can say as this is 3, this is 3, this is 3. In total, I am having 9 parameters for this entire deep neural network. Now, if I want to say it in a common way, I can say as number of parameters is equal to number of input features multiplied with number of neurons in that layer plus number of neurons in that layer, because let me write it first and then I'll explain you. Number of neurons in that layer. Now using this formula, if I want to find the number of parameters in the hidden layer 1, using this formula I can write as how many input features I'm having. In my case, I'm having the number of input features as 2. And how many neurons am I having in the first layer or the first hidden layer? I'm having the 2 neurons, right? So it is 2 plus 2. And what is the total number of neurons in that layer? It is 2. So in my hidden layer 1, I can say I'm having, so 6 is the total number of parameters for the hidden layer 1. In the same way, using the same formula, I can find as total number of parameters for hidden layer 2. So for hidden layer 2, so for the hidden layer 2, how many inputs is it receiving? It is receiving 2 inputs. And so how many neurons is it having? It is having 1 neuron plus 1, which is nothing but number of neurons in that layer. So it is 3. So in total, including hidden layer 1 and hidden layer 2, I am having 9. Let's create a deep neural network like this in a TensorFlow and display the total number of parameters to verify our understanding. Okay, so since we'll be making use of TensorFlow in our class, so I'll access my TensorFlow. So I'll start by importing my TensorFlow like this. So I'll write as TensorFlow.keras. I'll import layers. I'll also import dense. I'll import model. I'll import models. I'll not import that dense will inside the models itself. So I'm importing layers and models. So to begin with, I'll start by writing as network is equal to models dot sequential. Okay, and then I'll add the layers one by one. So I'll write as network dot add layers dot dense, and I'll specify as number of units. So how many number of units am I having in hidden layer 1? I'm having 2 input neurons. So 2 activation is equal to, I'll write as sigmoid comma input 2. So this is the input that my neuron receives, and on my second hidden layer I'm having a single neuron. So network that odd layers dot dense, I'm having single neuron as an output. So let me keep this activation as sigmoid. Okay, so I have built my deep neural network. So I'm sorry, so it is nothing but input underscore shape, I think. Yeah, okay, I have constructed my deep neural network. So let me print this summary of my deep neural network. So if I write a summary, see, it says on my hidden layer 1 I'm having 6, and on my hidden layer 2 I'm having 3 neurons. So if we compare to what we have found out mathematically, so this is what we have found. In the hidden layer 1 I'm having n1 and n2. So
3 plus 3, it is 6. So if I see here, see I'm having 6 over here, and on my hidden layer 2 I'm having 3. Okay, so formula is this: number of parameters in a layer is equal to number of input features into number of neurons in that layer plus number of neurons in that particular layer. For hidden layer 1, 2 into 2 plus 2, 6. Hidden layer 2, 2 into 1 plus 1. So this is done. Okay, now let's do one thing, guys. So let me instantiate one more network. So to begin with, I'll write something like this. I'll write as network is equal to models dot sequential. Okay, and then in this case I'll write as network dot add layers dot dense, and in my this layer I'll say it as 5 units of neuron. Let's say activation is equal to sigmoid, and this takes the input of, let's say, yeah, this time I'll have 10 inputs. Okay, and for the second layer I'll simply copy this. Okay, and for the second layer let me put some more neurons, let's say 5 neurons, and this will have the activation as sigmoid. And on my third layer I'll put 2 neurons, and on my fourth layer I'll put a single neuron. Okay, so this is how I'm building my deep neural network. I'll just execute this. Now let's do one thing, guys. Let's find out what is the total number of parameters in this each layer, and let's verify it by printing the summary. Okay, so I'll copy this and paste it over here so that we can compute it mathematically. Okay, so this is how it looks like. So I have started by defining my models as sequential. Sequential is nothing but stacking one layer next to another. Okay, so for the first layer I'm specifying it as 5 neurons. So that means I'll have 5 neurons in my first layer, and the input shape is 10. So let's start by, I'll call this as layer 1. Okay, I'll call it as layer 1. I'll call it as H2, H1, H3, and I'll call it as Y hat. Okay, so let's start by finding the number of parameters in the hidden layer 1. So for the hidden layer 1, number of input is 10 and the number of neurons is 5. So 10 into 5 plus, how many neurons am I having in this layer? I'm having 5 neurons, so 5. So in my hidden layer 1, I will be having 55 parameters. In the same way, let's calculate the H2. For hidden layer 2, how many input is it receiving? So the total number of input that it receives is equal to number of neurons in the previous layer. So for the hidden layer 2, the number of neurons in the previous layer is 5. So 5 is the number of input multiplied with 5, which is nothing but number of neurons in that layer, because 5 is over here, plus number of neurons in that layer is equal to 5. So this is nothing but 30 parameters, because 25 plus 5 is 30. And for the hidden layer 3, that is H3, let's calculate the total number of parameters. So how many inputs does it receive? So since I'm having 5 units in my previous layer, so this receives 5 input, and the number of units in this layer is 2. So 5 into 2 plus number of neurons in that layer is 2. So 5 2s are 10, 10 plus 2 is 12 parameters. In the same way, Y hat, or the final output layer, so how many input does it receive? It receives 2. How many neurons does it have? It has 1. So 2 into 1 plus 1, which is nothing but 3. So if we calculate the sum, so this sum is nothing but 15. 15 plus 30 is 45. 45 plus 55 is 100. So the total number of parameters in this deep neural network which I have instantiated is 100. So let's do one thing. Let's execute the code and then verify whether it's correct or not. So I think there's a mistake, guys. Instead of network, I have written as metwork. So let me correct this. Okay, I hope everything is correct. I'll execute this cell and now print a summary. See, the total number of parameters in my deep neural network is 100. So it has 55 in the first layer, 55, 30, 12 and 3. So if we compare to it here, 55, 30, 12 and 3. In this way, we find the total number of parameters for a deep neural network. So formula is number of inputs does it receive, so number of input features into number of neurons in that layer plus number of neurons in that particular layer. So this takes care of weights and this takes care of bias. Okay, got it? Cool. So this was about finding the number of parameters in a deep neural network. In the next video, let's dig deep and understand more about the deep neural network. See you guys. Continuing in the path of our deep learning, in this video we are going to perform the task of binary classification on the text data. To start with, I'm importing my necessary libraries. So I'm importing my Tensorflow library, NumPy as well as Matplotlib library. After importing my necessary libraries, here I'm downloading my dataset. The dataset which I'm going to use in this video is IMDb text dataset. And this dataset is available inside the TensorFlow library itself. Hence, I have written as from tensorflow.keras.datasets import IMDb. And after importing this IMDb object, I am loading my data. I am loading the data as imdb.load_data num_words is equal to 10,000. So what does it mean? Let's go to the official documentation, guys. So I'll just click on this URL. Okay, so this takes me to the official documentation of this load_data method. And if I come over here, it says num_words. Yes, it says the data type will be integer or none. Words are ranked by how often they occur in the training set, and only num_words, most frequent words, are kept. So what it means is, when I load this dataset, the number of unique words from my dataset that will be collected from this IMDb will be 10,000. If I leave it as none, it will take the maximum available of unique number of words. But if I specify as num_words as 10,000, it will only take 10,000 most repeated words. Okay, so let me just execute this cell. This will download the data and it will save as train data, train labels, test data, test labels. And if I display the shapes of training data and the test data, the shapes are 25,000 and the 25,000. So what it means is, in total I have 50,000 rows of data, out of which I have 25,000 rows as a training data set and the remaining 25,000 as a test data set. Since it's a single dimensional vector, what we can think of it is like, it would be something like this. So training data, it will be a single column and it will have the values which goes like this. And in each row, I'll have some text values. So this is how my data set will be. If I display the shapes of training labels, so it is also a single dimensional vector, which is of the length 25,000. Let's display the first instance on my training data. If I display the first instance of my training data, see, can you observe it? It is in the form of a Python list, and in this Python list, it contains integer values. So what does it refer? Yes, these integer values refer to the index of the word which is actually present in that particular instance of that row. So let me show you what that particular index means. So if I want to get the word index, I can make use of the method getWordIndex. So here I have written as word index is equal to imdb.getWordIndex, and if I just execute this, this will show the complete word index of this particular IMDb dataset. Can you observe it? So here the word affords has the value as 17641, word concert has the value as 3249. So these are nothing but the integer encoding of the individual unique words in my dataset. So if I go back to my first instance that I got just displayed, see, the training data 0 has the values as 1, 14, 22, 16, 43, 530, 973 and so on. So what does it mean? It is referring to the respective words that are present in that first instance of the data. So that is how my dataset is currently structured. Now I have a question for you guys. Can I use my dataset as it is, just like I have in the form of encoding? No, isn't it? I cannot use the encoding as a form of representation for my machine learning model. I have to come up with some sort of upgraded method. So one such easy method can be something like one-hot representation. So let's see how to perform that. Now before we go into the one-hot representation of my text data, let's look at the value present at the first instance of my training labels. The first instance of my training label has the value as 1. So that means the data which I had earlier displayed for training data, that represents the positive sentiment sentence, or in other words, review. And if I display the train labels 1, that is the second instance on my training data, it has the value as 0. So that means it's a negative sentiment sentence. Okay, we have now understood about the dataset, and we have understood that in case of training data, I have the words which are encoded in the form of integers. Since I cannot use the integer representation or on this integer encoding as a direct input for my machine learning model, we are going to perform the text transformation. To perform the text transformation, I have written a function as one-hot representation. This one-hot representation function takes two inputs, sequences and the dimensions. And inside this function, I have written as results is equal to np.zeros len of sequences comma dimension. So that means inside this function, I am instantiating a matrix, and this matrix is filled with 0 values. So all the values will be filled with zeros, and this will be having the shape of length of sequences, which is nothing but the total number of instances present in my input data set. Suppose if I'm sending my training data, then the length of sequences will be 25,000, isn't it? So the length of sequences will be 25,000, and the dim by default it is 10,000. The reason I'm sending as 10,000 because if you remember, while we were importing the dataset, we have specified as num underscore words as 10,000. So that means by maximum, I'll be having the 10,000 unique words. So how does my input matrix will be? So my input matrix will be something like a matrix which is of the dimension 25,000 into 10,000. So this will be the dimension once I perform the one-hot encoding with this function. So let's see what it is performing over here. Here, after instantiating my results matrix, I have written as for I comma sequence in enumerate sequences, results I comma sequence is equal to 1. So that means wherever a particular integer value is present, then on that specific index, I am marking it as 1. And finally, I am returning that specific vector. In other words, I am returning specific that particular transformed matrix in the form of one-hot representation. I know this sounds very confusing if you're seeing it for the first time. So for the explanation purpose, I have written one more function, and instead of dimension as 10,000, I have written as dimension as 8. And inside that function, I have written the functionality just like I had written before, guys. So I'll just execute this. And after that, I have instantiated a Python list. And this Python list has the values as 1, 2, 3, 4, 4, 5, 6, 2. Now let me explain as what happens if I send this particular Python list into my one-hot representations text function. So when I send this Python list into this function, that is one-hot representations text, as a first step, it would generate a matrix which is of the shape of length of sequences. So what is the length of this particular Python list? 1, 2, 3, 4, 5, 6, 7, 8. So it will be having the 8 rows and the number of dimensions is 8. So I'll be generating a matrix which is of the dimension 8 by 8. After creating my matrix which is filled with zeros of the dimensions 8, 8, I'm going to transform each row like this. Here I'm going to loop in for each of the values in this particular Python list, and wherever that particular value 1 is present, in this case, let's say for the first instance, I have the value as 1 present over here. So what I'll do, wherever I have the index column as 1, at that time I'll mark as 1 over here. Okay, rest everything will be 0 as it is. And if I take the second instance, here I have the value as 2 over here. So what I'll do, wherever I have that value 2 over here in the column, I'll mark as 1. Remaining everything will stay as 0 as it is. And in case of 3, I'll mark as 1 over here. Remaining everywhere, it will be zeros as a default because I had instantiated my matrix of np.zeros. Similarly, 6. So if I have a value like this, 6, I'll have zeros everywhere except the column 6. So in this way, I'll be performing my one-hot representation of my integer values. So if I have 1, 2, 3, 4, 5, 6 integer values like this. Each integer values is now represented in the form of one-hot representation, which is a linear algebra method of representing the vectors. Okay. Now let's send this and let's execute this. So once I send this particular Python list into this one-hot representation text, see, I have the output just like I had explained. In the first instance, wherever the column index is 1, only at that place I have the value as 1, rest everywhere I have it as 0. And for the second instance, I have the integer value as 2, hence wherever the column index 2 is present, at that place value 1 is filled, rest everywhere 0 is present, and so on. And if I look at the final instance, at the final instance I have the index value as 2, so on that index value I have the value as 1, rest everywhere it will be zeros. Okay. Now the next question is, what happens if I send my entire training data? So what does it do? So when I send my entire training data, what it will do is, let me execute this and let's analyze from the shape that we get. So if I send my entire training data, I'll be getting the resulting shape of 25,000, 10,000. In case of our training data, each row, or in other words, each instance of my training data will have multiple values. The multiple values can be something like this. So it will be a Python list. It will have some multiple values like 23, 45, 10, 100, and so on. So I'll be having a multiple values in my Python list. And when I send this Python list which has the multiple values, for each row, what it is going to do is, it is going to create a one-hot representation vector, and this will be having the length of 10,000. And wherever that particular integer value is present, in this case let's say 23, at that integer, that index value 1 will be filled, and 45 at that index value 1 will be filled, 10 at that value, at that index position value 1 will be filled, 100 at that index position value 1 will be filled, rest everywhere it will be filled with zeros. So instead of having a Python list with values filled with integers, we'll be having a one-hot representation which are in the form of binary, and each instance will have the equal length, that is 10,000. Okay, so that is what it does. So we have transformed our training data as well. Now once we have the training data ready, we are going to apply it to our deep neural network. To start with, I'm importing my models and layers from keras module. So from tensorflow.keras, import models.layers. After loading my models and layers, I'm instantiating my model as sequential, and after initializing my model as sequential, for the first layer, I have set the number of neurons as 16 and activation as ReLU, and the input shape is 10,000. The reason because each instance on my training data is transformed into a one-hot vector of the length 10,000. Okay? And in my second layer, I have the dense layer. It has 16 neurons and the activation is ReLU. And on my final layer, I have set the activation as sigmoid with single neuron. And after that, it's same guys, I'm going to compile my network. So for compilation, I have made use of optimizer as RMS propt and the loss as binary cross entropy, and the metrics is accuracy. And after that, what I'm going to do is, here I'm transforming my training data and the test data and saving in the variables of xtrain and xtest. And from this training data, I'm splitting it again for the validation data and the training data. So from my training data, I'm again splitting into two parts, that is validation data and the partial train. So I'm going to train my machine learning model, in this case deep learning model, with the partial training data, and I'm going to test my accuracy with the validation data. And on the basis of this model functionality, I'm going to find the evaluation on my test data. Okay. I'm going to execute this. After this, I'm going to perform the fit using x partial train and y partial train, and number of epochs as 15, batch size as 512, and the validation data as xval, yval. So I'm going to execute this. Okay, so the system is executing. Can you observe the output, guys? So after the third epoch, I can see that the validation accuracy is decreasing. So on my third epoch, the validation accuracy was 89%. And from the fourth, it started decreasing and on the fourth, it became 88.99, and on the fifth, it became 86.81, and sixth, it became 88.41, and so on. So what it is doing? After third epoch, it is performing the overfitting. Let's create a plot and analyze as how the plot looks like when we plot validation accuracy versus normal accuracy on the training data. So to get these values, we make use of the object of history. So I'm writing as history underscore dict is equal to history dot history. So this would result in a dictionary which has the keys as loss, accuracy, validation loss, and validation accuracy. So I'm going to write as history dict is equal to history dot history, and after this I'm extracting my value of the accuracy as history dict and specifying my index as accuracy, and in the same way I'm extracting my validation accuracy, loss, and validation loss. And if I plot my training loss versus validation loss, see, if you observe the output, until the third epoch, the validation loss is getting decreased along with training loss. But after the third epoch, the system starts overfitting, and we can observe the same over here. So after the third epoch, the validation loss didn't improve, and even it became worse at the fifth epoch. So that means my model is clearly performing the overfitting. Now, how to counter this overfitting, we will look in detail in the future videos. But one of the easy method to counter this particular overfitting is with the help of early stopping. The early stopping means we will stop wherever the validation accuracy starts degrading. In our case, the validation accuracy starts degrading after third epoch, isn't it? So as a next step here, what I have done is I have run my network.fit with epochs as 3. So once I do that, I'll get the required accuracy. In this case, the maximum accuracy my system was able to reach on the validation data was 0.86. And on this trained model, I'm going to perform the evaluation on my test data. Once I perform the evaluation on my test data, I am getting the accuracy as 85.27. So in this video, we have learned as how to perform the one-hot encoding on my integer values, and using those one-hot encoding representation, how to perform the binary classification. I hope this video has been useful to you, and if you have any requests to cover any other topic, do let us know in the comment section, and I look forward to see you in the next class.
Hey everyone, we have now performed two different types of tasks in deep learning, that is multi-class classification and binary classification. In this video and in the next few videos, we are going to perform the task of regression. In case of regression, the target output for which we are trying to predict is in the form of real numbers compared to the discrete values in the case of multi-class classification, or binary values in case of binary classification. And to do this task of regression, we are going to make use of Boston house prices dataset, which is available as part of sklearn library. So to start with, let's import the dataset. Here, as a first step, I'm importing my necessary libraries. I'm importing my Tensorflow library, NumPy library, Matplotlib library, and Pandas library. I'm going to execute this cell. Okay, all the necessary libraries has been imported. And I'm going to display the version of my TensorFlow that has been imported. So the version that I'm using is 2.3.0. Now as a next step, I'm going to import the dataset. As I said already, this dataset is available inside the sklearn library itself. Hence, I have written as from sklearn.datasets import load_Boston. And to load the dataset, I have written as Boston is equal to load_Boston. This load_Boston is a function. When I call this function, that is load_Boston, this is going to generate an object. So this object I am naming as Boston. Okay, I'm going to execute this. So this will load the dataset from my sklearn library. As a next step, I am going to display the description of my dataset that I have just loaded. For that, I have written as boston.desc. Let me just execute this cell, guys. Okay, I have the output that looks like this. The description says Boston house prices dataset, and it has 506 instances. That means I'm having the data for 506 instances. In other words, 506 homes. And the number of attributes are 13. Here 13 refers to the number of columns. So for each instance, I'm having 13 column details. And as the last column is called as MEDV, which refers to median value of owner occupied homes in $1,000. So this is the output column for which we are trying to generate the predictions. And we are going to generate the predictions based on the 13 columns. The 13 columns can be CRIM, which refers to per capita crime rate per town. and the RM refers to number of rooms per dwelling. See, it says average number of rooms per dwelling. Likewise, in total, I'm having 13 columns as the input data, and the last column, that is MEDV, is the target variable for which we are trying to generate the predictions. Okay, so this is about the data set that we are going to work with. Now to get the data from this data object, that is Boston, I'm going to write as x is equal to boston.data. I'm just going to execute this. So this will transfer all the input data to my variable x. And as a next step, I have written as y is equal to boston.target. So once I execute this, this will transfer all the target values into the variable called y. As a next step, I'm creating a data frame. For creating the data frame, I have written as df is equal to pd.dataframe x, columns is equal to boston.feature underscore names. If I simply call this value, that is boston.feature underscore names, let me create a cell and execute it and show you guys. Here I'm writing as boston.feature underscore names. If I just execute this, see, this will display the list of feature names that are present in my data set. So what it means is create a data frame with the values present in X. Here X refers to the values for the input data. So with the values present in X with the column names as feature names. Okay. And if I just execute this, so this will create the data frame. If I display my data frame df, so df.head, see, this has created a data frame with 13 columns and the feature names as the column names. Now for this data frame, I'm adding one more column as target and I'm setting the value of y. So let me just execute this. And if I display my data frame now, see, the column target has been added to my data frame df. So this is how it looks like. Okay, we have the data set ready. Now as a next step, I'm going to perform the split between training data and the test data. For that, I'm making use of train test function, which is present inside the sklearn.model underscore selection. Hence, I have first imported as from sklearn.model underscore selection, import train test split. After that, I'm performing the split as train data, test data, train targets, test targets is equal to train test split. And I have specified my input data as well as my target data. If this is confusing, what you can do is, instead of writing the logic like this, you can simply specify it as x, y, because x contains the input data and the y contains the output values. So you can simply write x, y, test size is equal to 0.3 and the random underscore state is equal to 42, so that you get the same split as I'm getting just now. Let me just execute this. Okay, so this has performed the split between training data and the test data. If I display my training data, it is in the form of NumPy array. And if I display the shapes of my training data and the test data, training data has the shape of 354, 13 and the test data is having the shape of 152, 13. That means 354 instances in my training data and 152 instances in my test data. If I display the type of my training data, this is obviously in the form of NumPy array. And if I display the training targets, so the training targets are nothing but the value of the output target. If I just execute this, the training targets is also a NumPy array which contains the value of the houses in $1,000. For example, 28.7 refers to $28,700 of that particular house. And if I display the test targets, this is how it looks like. Okay, so we have the data set ready with us and we have also split the data set as training data and the test data. Now the next step that we are going to do is data normalization. Now why should we do that? Don't worry, I'll explain shortly. Now let me call the describe method on my data frame df. If I call the describe method on my data frame df, okay, this has displayed the statistical description of my data set. Now observe the column CRIM. That is the crime rate. Here it says the minimum value is 0.006320 and the maximum value is 88.976. Now observe the value of CHIS. It is having the minimum as 0 and the maximum as 1. So if you take the other column of tax, minimum value is 187 and the maximum value is 711. If I come over here, the minimum value is 0.320 for the column B and the maximum value is 396. So what it means is each column has a different range in which values are present. So that means if we want to perform the linear regression task effectively, we have to perform the normalization on my entire data set. Here, to perform the normalization, I am making use of standard scalar function which is available inside the sklearn library. Hence, I have first imported my standard scalar. So from sklearn.preprocessing, import standard scalar. And after this, I'm initializing my standard scalar and transforming, that is fit and transform on my training data. And then using those learned values on my training data, I'm just performing the transform on my test data. So let me just remove it because it's not necessary for now. Okay. And if I just execute this, okay, my transform training data and the transform test data are now having the same shape, that is 354,13 and 152,13. Now let's look at the result of this normalization. Now whenever we apply the transformation using standard scalar on our data, what it would do is it would transform the data such a way that it will have the mean as 0 and standard deviation as 1. So let's test whether we have the same values or not. Here what I'm doing is I'm calling the mean along axis is equal to 0 on my transform train data. If I just execute this, see, this transformation has resulted in the value of each column with mean as 0. Can you observe it? Each value is close to 0. Hence we can say as the mean is equal to 0. And if I compute the standard deviation for each of the column, the standard deviation for each of the column is 1. So what I can say is we have performed the transformation on our data set such that we have the mean as 0 and the standard deviation as 1. And to do this, we have made use of standard scalar function which is available inside the sklearn library. Okay. And if I display the transform train data, I now have the values like this after performing the transformation. So I'll stop the video here, and in the next video, let's build a neural network and apply this transform data. Hey everyone, in the last video we have performed the transformation on our training data and the test data with the help of standard scalar which is present inside this sklearn library. Now after we perform the transformation, if we observe the shapes of our input data, that is training data and the validation data, the shapes are 354,13 and 152,13. That means I'm only having 354 instances of my data for training my deep neural network. Since the number of data is very less, what we do is we make use of the concept of k-fold validation. In case of k-fold validation, what we do is we split our data set into k parts, and we are going to train our data set on k-1 parts and test it with the help of 1 part. Suppose if I'm splitting into 4 parts, then I'm going to train my deep neural network with the help of 3 parts and test it on my 4th part. Now to perform this k-fold validation, I have written a code like this. So to understand the concept of k-fold, here I have created a numpy array x is equal to np.random.randint 0, 1000, 12, 6. So if I display my x, my matrix x is having the shape as 12, 6. That means 12 rows and 6 columns. And on this matrix X, I'm going to perform 4 split. So in each split, what it will do is, if I'm performing the 4 split, then in each split, it will have 3 rows, isn't it? So when I perform into 4 split, then I'll be training on my first 3 splits and I'll be validating on my last split. But let's understand as how we can perform this k split. In other words, 4 splits. As a first step, I have specified my k is equal to 4. And I have defined as number of value samples is equal to length of x divided by k. So that means I'm dividing the length of x, that is matrix x, divided by k. Here I'm performing the integer division because I want the values in the form of integers. Okay. And in my case, I'll be getting the number of value samples as 3. And if I display my x, I'll get the value of x. And after this, observe it guys. Here I am creating the for loop, and this for loop runs for the range k.
And after that, I am printing the fold number. And for each fold, I am creating two sets, that is validation set and the training set from my entire matrix X. In the first iteration, the X validation data will have the first 3 rows and the remaining 9 rows will be having with this X train data. And in the second iteration, my X validation data will have the values between 3rd row to 6th row, and the first 3 rows and the last 6 rows will be in the training data. So this would repeat the same for each of the fold. Let me do one thing, guys. Let me just execute this cell and then we can analyze from the output. Okay, we have got the output like this. Here I have printed the value as array, this is the output for array X, and after printing the output for array X, I have defined my fold 0. So let me do one thing, guys, to help with our formatting. Let me add the print statement. So I'll print like this, print, and let me add print statement for this X as well, and let me just execute this. Okay, we now have the necessary output. Here 3 refers to number of samples for each split. Okay, so this is how my matrix X looks like. Now for the fold 0, the validation data with fold 0 will be the first 3 rows. Can you observe the values? It starts from 906 till 161. So that means this refers to the first 3 rows from my X matrix. If you look at the training data with fold 0, it will have the remaining 9 rows from my matrix X. And now as we move on, observe the value for the fold 1. For the validation data with fold 1, I'm having the values from 748 to 626. If you observe it in my original matrix X, 748 appears here and the 626 appears over here. And the remaining values, that is the remaining values are 906 to 161 and 939 till 931. So these are the values will be present in my training data. Got it? So you can verify the same over here, guys. See, 906 to 161, 939 to 931. The same goes on for each of the 4 splits, that is fold 0, fold 1, fold 2 and fold 3. Now in this way, we perform the data set into k number of splits. Now in the same way, whenever we are training the deep neural network, the expectation will be train a deep neural network on the training data on the particular fold and validate with the remaining validation data, and repeat the steps for each of the fold. Now to do that, what I have to do is I have to instantiate my model each and every time. So what I'll do is I'll create a model as a function. Here I have defined a function as def build_nn, and inside this function I have written as network is equal to models.sequential, and in my first layer I have specified the neurons as 64 and the input shape as transform train data dot shape of 1. That means the number of columns present in my transform training data. And in the second layer I have specified the number of neurons as 64 and the activation as ReLU. And in the final layer I am using a dense layer with a single neuron, and here I don't have any activation function because the output that I want is in the form of real numbers. Okay, and after adding the layers to my deep neural network, I have compiled my model with the optimizer as RMS prop, loss as mean squared error and metrics as mean absolute error. And I'm using this mean squared error and the mean absolute error because this is a regression task. Finally, I am returning my network. Okay, let me just execute this. Okay, now after this, I have used the previous code which I have already written, and then along with that I have defined one more Python list as all MAE histories is equal to a blank Python list. And on this blank Python list, I'll be appending the mean absolute error at each epoch. Okay, here inside the for loop, what I'm doing is I'm performing the split of my data set into 4 parts. So when I say 4 parts means k will be equal to 4. For each of the part, I am creating the validation data and the validation targets. Similarly, I am creating the partial training data and the partial train targets. Here I am making use of this concatenation function to perform the necessary mathematical operation of concatenation. Okay. Now after performing the split, I am defining my model. So model is equal to build_nn, and then I am performing the fit on my deep neural network, that is model. And on this model, whatever the values that I'm getting for value, that is validation, mean absolute error, I'm saving inside this all MAE histories Python list. Okay, so let me just execute this. Okay, the processing has been completed. For each of the fold, we have performed the training on the 3 parts and we have performed the validation on the remaining, that is 4th part. And we have did the same thing for each of the particular part, guys. And as a next step, here I'm computing the average MAE history. So here I'm computing the average MAE history for the each epoch. So let me just execute this. Okay, so this would compute the average MAE history. And after this, I'm creating the plot, and this plot contains the validation mean absolute error. So let me just create the plot. Okay, if we visualize the plot, this is how our validation mean absolute error looks like. As we can see, there is a quite a bit of variation over there in our plot. So let me just smooth it so that we'll get the better understanding as how my model is performing. So if I smooth it, so this is how our model is performing, and I can say that around the epoch of 43, I'm getting the good number of accuracy. So what I'll do is I'll create a fresh model and I'll run for, let's say, 43 epochs and then perform the evaluation on my test data. So once I perform the evaluation on my test data by running for 43 epochs, the test MAE score that I'm getting is 2.3204. So that means whatever the prediction that I'm generating from this deep neural network, it would be just off by 2320 USD dollars. So that's pretty much good model, isn't it? I hope this video has been helpful to you, and if you want me to cover any of the topics apart from the deep learning series, do let us know in the comment section, and I look forward to see you in the next class.
Hey everyone, this is Kavya again. I hope you guys have had a good learning from the last few videos. So let's have a quick review on our learning progress and understand how our learning will be in the upcoming videos. So we actually started our learning journey by understanding about the deep neural networks and its various parts. So guys, let me summarize the things quickly here. Okay, a deep neural network will basically have an input layer through which it receives the data, wherein these hidden layers will process the information received from the input layer. And if we consider the output layer, it actually presents the processed output. Here, each processing unit of a deep neural network is called as a neuron. And each neuron can be thought of as an independent machine learning model which has its own parameters, and it receives the input from the preceding layer and provides the output to the neuron in the following layer. And all the neurons are actually interconnected to form a dense network structure. So the way this neuron actually processes the information is based on the activation function that is present in it. Okay, so after that, we have learned about the various activation functions that are available in a deep neural network, as well as how to calculate the total number of neurons in a deep neural network, and also what happens when a data is passed into a neural network. Henceforth, by using all our theoretical knowledge, we have actually built our own neural network with the help of the deep learning framework, that is Tensorflow, using Keras API. So now, let me just quickly list some of the important steps to create a neural network. First, we have to import the necessary libraries and then initializing the models as sequential. And after that, we start adding the layers as per our requirement. And while defining each layer, we specify as how many neurons it will have and its respective activation function. And here, worth noting is, depending on the shape of the input data, we specify the input shape of the first layer. Fine. And after that, depending on the type of output data we are dealing with, we will have its matching activation function on output layer. So guys, moving ahead. So till now, we have completed 3 different types of tasks. First is multi-class classification on MNIST image data. The second task we have completed is binary classification on the IMDb text data. And after that, we have completed the regression on Boston housing data. So if we consider the first task of multi-class classification, so during the working of this problem, we have understood as how to pre-process the image data by reshaping as well as scaling the values. Okay, and we have also made use of the criteria as categorical cross entropy and a softmax activation on the output layer. And on the second task of this binary classification on the IMDb text data, we have actually learned representing the text data in the form of one-hot encoding, thus enabling us to work with as numbers instead of unstructured text. Okay? Now, coming to our latest videos, that is in our previous video, we have learned as how to write a function to perform k-split on our data and to perform the k-fold validation using our deep neural networks. And while performing all these tasks, we have made use of the regularization technique of early stopping, that is, limiting the number of epochs when the validation errors start increasing. So this was our learning till now in the path of deep learning. In the upcoming classes, we are going to learn as how to use the deep learning for computer vision tasks with the use of convolution neural networks. You are as excited as I am, and I look forward to seeing you in the next session. Now, before that, I want you guys to complete the assignment which we have provided along with this video. And for that, please do check the description box and continue your learning. Do share your assignments by uploading on GitHub and we will review it. Okay? And of course, you know the drill, that is like, share and subscribe to our channel for more learning. Till then, take care. Bye-bye. Hello guys, welcome back. And this is the second module of Deep Learning 2020. So from the last section, you now know as how to use the deep neural networks for various tasks like binary classification, multi-class classification and regression. So in this section, we are going to learn as how to perform the task of computer vision using convolution neural networks. So let's start by understanding the term computer vision. And here, first let's take this term, that is vision. The question is, what is a vision? Yes, the question is simple. What is a vision? Now, what is the answer for this? It is also very simple. Vision means ability to see. So, in simple sense, computer vision means giving the computers the ability to see. Understood? Now, in recent days, we have seen many global firms making use of this field of computer vision across the domains, like from autonomous driving and retail to healthcare. Yes, they are doing it. That is because to improve their business operation and enhance the productivity of the employees, which is enabling the companies to give the best customer experience. But the question remains the same. How can we enable any computer to see the outside world? It is a very non-living being. Yes, it is a non-living being. And how can we enable any non-living being, or say our computer, to see this outside world? So now, to understand this, what we have to do is, we have to analyze as how we humans, being living beings, we humans see the objects in the outside world. And guys, what I'm going to tell now is something very much basic from the biology of high school, but still we have to know this at this point so that we can clearly get the idea about this computer vision. Okay? So now what happens here is, when a light falls on an object, it actually reflects back to the eye. And the photoreceptors in the eye turn the light into electrical signals. And these electrical signals travel from the retina to optima nerve in the brain. And the brain processes the images. Beautiful, right? So, as you can observe, here we have got 3 events which are taking place. Wherein the first event is light is falling on the object and reflecting back to our eyes. And wherein the second event, that is the light signals, are getting converted into electrical signals. And if we talk about the third event, that is the electric signals are getting processed in the brain. So now, if I talk in terms of our computer science, I can say as data is actually getting captured from the outside world, which is as same as light falling on the object and reflecting back to eye. And in the second event, the data is getting transformed, which is as same as the light signals are getting converted to electrical signals. And in the final event, data is getting processed, which is nothing but the signals processing in the brain. Got it? Now, if I want to give the same abilities to our computer, what we have to do? We have to give the three main abilities to computer to see the outside world. That is, I should give my computers the ability to capture the data, transform the data, and also the analytical ability to process the data. So now, let's see as how we can give these abilities. Okay, so first is the ability to capture the outside world. Now, we can give this ability with the use of the hardware, something like webcams, HD cameras like DSLR and many more. And even the mobiles in our hand have the ability to shoot the high quality images or the videos. So with this, the first requirement of the capturing the data is satisfied. So the first ability is gifted to the computers. Now coming to the second requirement, that is data transformation. For this, we have a great range of softwares which allows us to convert the image or the video data which has been captured from the hardware into the required format as required for the computer processing. That means we are satisfied with the second requirement. That is, we are also gifting the second requirement for the computer to enable it to see the outside world. Now, last but not the least, that is the ability to use the transform data in making the decisions. Now, to do this, we make use of our deep learning architecture. Yes, to do this or to give this ability to computer, we make use of deep learning architecture called convolutional neural networks. Okay? So as this is a new word than what we have come across, so let's understand this convolution neural network, this word in detail. So let's start by understanding the term convolution. So what actually this convolution means? In mathematics, this convolution is actually a mathematical operation on two functions, that is f and g, which produces a third function expressing how the shape of one is modified by the other. So in the image processing, we can call the convolution as its manipulation of pixel values of an image. Guys, if you're hearing this term for the first time, you might think this is something very highly complex, most advanced term where only selective few can understand and use. No guys, it's not that way. I'll tell you, everyone is using this convolution operation in a daily life. Yes, we are using it every day. So I'll start by asking you a few questions over here. So the first question is something like this. So what do you normally do when you click a photo? Please do answer me in the comment section. I want you to pause the video here and please do answer it in a comment section. Done? I'm sure guys, most of you would have answered in this way. It is like sharing on a social media, Insta handle, Facebook, anything, anywhere where you can share it with your friends and family. But now, before sharing, yes, I'm speaking something about before sharing. Now, before sharing, what are the common things that we will be performing? See, we will be making sure that the pic looks good in all the angles, that too by applying various beautification techniques, that is adjusting the lighting, brightness, crop, rotation, many more things. Yes, many more things with the use of our mobile apps. Isn't it? Yes. Yes guys, this very act of changing the properties of the image by applying the various effects and filters is what is known as convolution operation on images. Got it? Now guys, just observe the image that is presented on the screen. So in this image, can you just identify as how many water sources are present in the image? Yes, we can actually identify one water source at the bottom of the photograph. Okay. Now look at the same photograph but by adding the various effects on it. Okay. See, can you tell me as how many water bodies do we see in this image? Oh yeah, we can actually now see two water sources in the image. Guys, why I'm showing you all these things? Because This kind of similar operation will be performed in convolution layers of deep neural network, where my network tries to learn more of the features in the image by performing the convolution operation. Got it? Now the question is, how does it actually work? So I can make the convolution operation with this representation. We will have an input image onto which we will apply a filter which is of the form of matrix, let's say 3 cross 3. And by applying the filter on top of our image, that is input image, we get the transformed output image. So guys, for now, you can just think of this input image as a color image, and a filter can be thought of a special filter that you use like converting to grayscale. Okay, and once you apply this, your image will be converted to grayscale. And this is the intuition behind convolution operation. Understood? Now the question arises over here is how it actually performs and how I can get the output in the required manner. And guys, that and all will be discussed in our next video. So guys, please do subscribe to our channel to get more such informative videos, and if you want, you can obviously share it with your friends for spreading the knowledge. And guys, I look forward to seeing you in the next video. Till then, keep learning and take care. Hello everyone, and this is Kavya. So guys, at the end of last video, I have said that the convolution operation can be represented like this. Correct? Now, before we go further on this convolution operation, let's get the basic understanding of the type of the data that we are dealing with for the task of computer vision, that is images and video. Okay? Now, whenever we are storing an image on a computer, the image is broken down into tiny elements called pixels. What is it? Pixels. Here, a pixel is nothing but a short for the picture element, which actually represents only one color. Fine? Suppose if I have a grayscale image, then the grayscale image has a single color. So to give you an example of a grayscale image, see, this is how a grayscale image looks like. Okay? Now for each pixel to represent its color, we represent by a pixel intensity. What is it? A pixel intensity. Guys, suppose if the dimension of an image is 50 by 50, then to represent the color intensity of each pixel, we can actually represent it with the help of a matrix of dimension 50 by 50, where each element represents the pixel intensity with the numeric value. Understood? Wherein the minimum and the maximum value, each pixel can have a 0 and 255 respectively. Guys, this is important, so I'll just repeat it once again so that you get the clarity on this. See, if the dimension of an image is 50 by 50, then to represent the color intensity of each pixel, what we do is we can represent it with the help of a matrix dimension of 50 by 50, wherein each and every element represents the pixel intensity with a numeric value, and the minimum and the maximum value each pixel can have is 0 and 255 respectively. Got it? So what actually this means? See, in a grayscale image, 0 represents the black color. What is it? 0 represents the black color and 255 represents the white color of the image. Got it? So guys, I hope you now know as how an image is represented in computers. This is very much important. Okay. So now the next question is, how does a color image is represented? So we talked about the grayscale image. Now it's time for us to know as how this color image is represented. So in a case of color image, each color image is made up of 3 color channels, that is red, green and blue. Guys, we see various colors as a result of this combination of 3 color channels with various intensities. So if we want to represent it mathematically, I can say as this color images can be represented as multi-dimensional array. Suppose if we have a color image with the dimension of 50 cross 50, then to represent this image, we can take the help of multi-dimensional array object of shape 50 cross 50 cross 3, wherein this 50 cross 50 refers to the shape of the individual image and this 3 refers to the number of channels in the image. Okay, understood? So I hope you are now clear as how grayscale as well as color images are represented in computers. So now let's look at the representation of videos from the perspective of computers. Now the question is, what are videos? Yes, what are videos? It is very simple. Videos are nothing but a collection of images where each image is called as a frame. Suppose if I have a 5-second video with the video size of 50 pixels by 50 pixels, which is actually shot at 24 frames per second, then its representation in mathematical terms would be something like this. That is 50 cross 50 cross 3 cross 24 cross 5, which is actually a multi-dimensional array object. So to give you a clarity here, see 50 cross 50 cross 3 actually represents a single color image, and this 24 refers to the number of images per second, which is actually nothing but frames, and this 5 refers to total duration of video. As you can see, working with the video data is no different than working with image data. But guys, only difference is here we will be working with a lot of data. That too, with the growing of duration of video, the data grows exponentially. Got it? So this was about handling the data for computer vision. So now let's move ahead and understand as how we perform the convolution operation on the image. So if you observe the input here, what do you think will be the type of the image? Is it a color image or black and white image? Yes, it's a black and white image because the number of channels in the image is 1. Now, when we are applying a filter on the image to perform the convolution operation, we will be using a small matrix, which is nothing but a kernel or weight matrix, and then we perform the mathematical operation like multiplying the weights with the pixel values and summing it up to get a constant value. Okay? Now, before we explore more about these operations, let's see as what happens when we apply a filter of size of 3 cross 3 with the values filled like this. So, if you observe this, we have got zeros everywhere except this second row, wherein this second row consists of -1 and 1. Now, when I applied this filter on the image of Taj Mahal, can you just observe the resulting image output over here? Yes, we can see that the edges are actually highlighted when we applied this particular filter. That means with the new image that we have got as an output can now serve as a new input for my computer. Yes guys, this can serve as a new input for my computer. Now, if we compare both the inputs, this old input and the new input, we can observe that our new input is very much efficient. Why? Because the computers can now efficiently learn about the edges of the Taj Mahal which was not present in the previous input. Got it? Yes. Now, moving on, it's time to understand as how to perform this operation of convolution. Guys, this animation shows the intuition of the convolution operation. The way we do is, we place our filter on top of our image and move horizontally from left to right and top to bottom by moving a pixel at a time. And see, you can observe the same in our animation. Observe it carefully. See, you can observe the same in our animation. Here, it starts with one position and then moves on one pixel at a time by placing the filter completely on the top of our input image, and after that it generates the output image. And guys, this is a basic idea as how convolution operation works on images. So this is something very important, so I'm just repeating it once again so that you get the concrete idea. Okay, here it actually starts with one position and then it moves on one pixel at a time by placing the filter completely on the top of our input image, which actually results in our output image. Got it? So let's take up an example here. For that, what I'll do is I'll just pause the animation over here. Okay, so like I said already, here we are moving our kernel from left to right as well as top to bottom. And now this highlighted part refers to the kernel position on our image. So now to transform the pixel values in the input image, what we have to do is we have to multiply the kernel values with the respective pixel values, and then we have to add it together to get the transformed output. So let's do the same, guys. So it will be something like 2 into 0 plus 2 into 1 plus 3 into 2. After that it is 0 into 2 plus 2 into 2 plus 2 into 0, and then of course 0 into 0, 0 into 1 plus 1 into 2. So it will be equal to 14. Got it? You can see here, see the output is 14. Okay, so guys, I hope you now know as how to perform the convolution operation on images and how inputs are transformed based on the values in the kernel. So I think I should stop the video here because it will become very difficult if I take up every concept in the single video. So let's take up step by step. So I'll just stop the video over here, and in the next video, what we will do is we will be exploring the other parts of convolution operation like strides and padding. So guys, let's just wait and hold the excitement of learning new topics every day. And guys, as always, please do subscribe to our channel to get more such informative videos, and if you want, you can share it with your friends for spreading the knowledge. And guys, I look forward to seeing you in the next video. Till then, take care. Bye-bye. Welcome back, guys, and this is Kavya. So in the last video, we have learned to perform the convolution operation on an image, wherein we place the filter completely on an image and slide it from left to right and also from top to bottom while performing the mathematical operation. Now, if you just observe the screen, you can see that my original image is of the dimension 5 cross 5. Now, when I perform the convolution operation with a kernel size of 3 cross 3, it actually resulted in the generation of image which is of the dimension 3 cross 3. Now, why is that happening? Why are we getting such resultant image? So to understand the reason, please do observe this animation. Here, if you observe carefully, the system is actually unable to slide the kernel from the pixel points at the outer region of my input image. Just see here, if I try to place my kernel at the outer pixel points of the image, it would just go out of bounds. Hence, my system is unable to perform the convolution operation at the outer dimension, thus resulting in losing a dimension along each axis. Understood? Now, if we don't want to lose the dimension while performing the convolution operation, what we have to do? Yes, what we have to do? So what we have to do is we have to make use of the concept of padding. What it is called? It is called padding, where we add a new dimension of blank values before we perform the convolution. I repeat here. See, when we have to make use of this concept padding, what we do is we add a new dimension of blank values, that too before we perform this convolution. And guys, here this padding actually refers to the blank values, which is nothing but the pixel values which are equal to 0. So collectively I can say as by including this padding layer, we won't be losing out any dimension while performing the convolution operation. And guys, you can also observe the same in our animation. See? So guys, this time we have actually added a single layer as a padding layer, and because of this, when we are performing the convolution operation, we are still getting the output which is the same as our input dimension. And one more thing over here, that is by including this padding layer, my kernel can now move along every pixel in my original image. So guys, this is how the padding layer works in our convolution neural networks. Okay, so the next concept which we are going to explore is stride. What is it? Stride. So here stride refers to step size. Currently, if you observe the step size, the system is moving 1 pixel at a time. Correct, right? If you observe this animation, you can easily tell that the system is moving 1 pixel at a time. That means my kernel is sliding on the image by moving 1 step at a time. And of course, we can alter this by specifying the stride size. How do we do it? So just observe here. Now this animation shows the movement of kernel when I give the stride stride as 2. See, if the stride is 2, it is just changed its movement. That is, by applying the stride as 2, the kernel is now moving in a very different manner. Okay? So guys, till now we have learned about the working of convolution operation on a grayscale image, which is nothing but an image with single color channel. So the obvious question which arises in our mind is, how does this convolution work on a color image? So in the case of these color images, what we actually do is we apply a filter on each of the color channels and then we perform the aggregation of the resulting channels to get the transformed image. Got it? So guys, I really hope that this explanation gave you a clear idea about the concept of strides and padding. Okay, with this we come to the end of this video, and as always, please do subscribe to our channel to get more such informative videos, and if you want, you can share it with your friends for spreading the knowledge. And guys, I look forward to seeing you in the next video. Till then, take care, bye bye. Hello everyone, and this is Kavya from Manifold AI Learning. So guys, we now have the clear idea about the convolution operations on the images. Now, apart from performing the convolution operation on the images, other common operation we perform is pooling. What it is? Pooling. Yes, we perform this operation to reduce the spatial size of the transformed image data that we are working with. So guys, we do this by extracting the important features of the image. And we have got two types of pooling. One is max pooling and other is average pooling. So when we make use of this max pooling, it will actually return the maximum value from the portion of the image covered by the kernel. On the other hand, when we make use of this average pooling, it will actually return the average of all the values from the portion of the image covered by the kernel. So guys, this is an image which shows the result of applying the max pool operation. And if you observe this image, this actually represents the results of applying the average pool operation. See, this is the resultant of max pool operation and this is the resultant of average pool operation. Okay. Now, as you can see, the max pool has written the maximum values from each of the kernel position. So if you consider this case only, here I am using the kernel size of 2 cross 2 with the stride as 2. Okay, and here these are the highlighted parts. This actually refers to the kernel position of the image. Now, as you can see in the results of this max pooling operation, it resulted in the values like 20, 30, 112 and 37, which are the maximum of all the values present in the kernel region of the image. On the other hand, for this average pooling, when we take the average of all the values present in that kernel region of the image, then the resultant values will be like 13, 8, 79 and 20. Okay, so I hope this gave you some clarity as how the concept of max pooling and average pooling works. Fine. So we are now clear about each of the components of the convolution neural networks. Now it's time for us to get an overall understanding of the structure of convolution neural network. So here we start with the input image. Let's say image is of the shape 224 by 224. On this image, we perform the series of convolution operations with a varied kernel size with required padding, which is followed by pooling layers, which performs the aggregation of values. And after all this convolution operation, what we will do is we will flatten the resulting values from the convolution and pooling layers. And then we will connect it to a deep neural network where we will be applying the required activation and also an apt output layer. Okay, so with this, I hope you guys now have a basic understanding about these convolution layers. So in the next video, let's learn as how we can define our own convolution layers using Tensorflow. Yes, it is by using Tensorflow. And after that, let's learn more about the parameters of the convolution layers also. So guys, I highly recommend you to carefully follow the next hands-on video wherein we will be using all our theoretical understanding. So please do go through the theoretical concepts which have been already explained so that you can get the best out of the upcoming hands-on series. Okay? And guys, do consider subscribing to our channel to get the more such informative videos. And if you want, you can also share it with your friends for spreading the knowledge. And guys, I look forward to seeing you in the next video. Till then, take care, bye-bye, and have a great day ahead.
Hey everyone, welcome back. So you now have the theoretical understanding about the convolution operations in deep neural networks. And while learning the convolution operations, you have understood many concepts like kernel size, padding, strides, and many more, isn't it? So from this video, what we are going to do is we are going to use all our theoretical understanding and implement it in this TensorFlow deep learning framework so that we'll get the better understanding of all the theoretical concepts that we have learned. Okay. So to begin with, what I'm doing here is I'm importing my necessary libraries, that is I'm importing my TensorFlow, and from that TensorFlow I'm importing my layers and models as well. So let me just execute this cell. Okay. Now to apply the convolution layer, we make use of con2d function which is present in tf.keras.layers.con2d. So to understand it better, what I'll do is I'll just open the documentation of this con2d layer. So if I open the documentation of this con2d layer, see, this is how it looks like, and this con2d layer takes many arguments. So important arguments are filters, kernel size, strides, padding, and many more. So let me just come down over here. Okay, so the important arguments are filters, kernel size, strides, and padding. So the filters is nothing but an integer which represents the dimensionality of the output space. So what we'll do is, like, as we progress in this video, I'll explain in detail as what is this particular filter means. And the second important argument that we have is kernel size, which is nothing but an integer or the tuple or list of two integers which specifies the height and width of 2D convolution window. And the stride refers to the step size, and the padding we can either mention as valid or same. So when it is valid, what it means is like there won't be any padding, and if I mention as same, then what it would do is the system would add the sufficient padding so that we'll not be losing the dimension whenever we perform the convolution operation. So this is enough theory for now. What we'll do is I'll go back to my Google Colab. So let me execute this cell, but before that, let's understand as what are the things that I've written over here. As a first step, what I have written as I have specified my input shape as 1, 28, 28, 1. So why have I specified like this? See, the reason is whenever we are dealing with image data, especially in deep learning frameworks such as PyTorch or TensorFlow, we'll be sending the data in some specified format. And in case of TensorFlow, we'll be sending the data in the format of batch size, cross, height, cross width, cross number of channels. So this is the order that we are going to send the data whenever we are sending the data for deep learning framework of TensorFlow. In my case, I have specified my input shape as 1, 28, 28, 1. So that means I'm sending a single image. So this one refers to the batch size. So I'm sending a single image, and this single image is having the dimension of 28, 28, 1. So this dimension or this 28, 28 refers to the shape of my image. Okay, so this shape of the image is 28 by 28, and I'm having a single color channel. That means I'm dealing with a grayscale image. You can remember all our theoretical sections, guys. This is what I have said, right? If we are having a single channel in the input in the image means that's a grayscale. But in case of color image, I'll be having three color channels. So since I'm having the shape as 28, 28, 1, so that means it's an image which is having the dimension as 28 by 28 and color channel as 1. Okay. And here what I have done is I have created an X as a tensor object. This tensor object is nothing but tf.random.normal. That means I'm initiating this particular X to some tensor object which is having the shape of 1, 28, 1. So that is what it means. Now after creating my input X, I am sending this input X. In other words, I am applying this input X to my con2d layer. So to apply to the con2d layer, first what I have done is I have defined my con2d layer as like this. Layers.con2d of, inside the parenthesis, I have specified as filters as 1. So for now, just understand as this is just a single operation that I'm doing. So we'll come to this part of filters as we progress in this video. For now, let's see it as, okay, what happens if I use as filters as 1. Okay. So after filters, I have specified my kernel size of 3, 3. And after that, I have specified my input shape as input shape 1 colon blank. The reason because as we know already, in case of input shape, we'll be sending in the form of batch size, height, width and color channel. So the dimension of single image will be height, width by number of color channels, isn't it? And because of that reason I have specified like this. Now to apply this conv2d layer on my input x, I am multiplying with x. Got it? So let me erase everything over here. Okay, so now I have erased everything. So what it means is I'm initiating my tensor object as x and I'm applying on my convolution layer. Okay, so once I apply it on my convolution layer, I'll be getting the output. So let me write down as whatever the data that we have. So the data that we have observed is I'm having an input image which is having the shape of 28, 28 and this is having a single color channel. Okay, so this is a single data that we have, and on this input data I'm applying a kernel of 3, 3. So what does it mean by convolution operation? I'll place this kernel on top of my image and I'll place a different position to get my transformed image. So this is what we have learned, isn't it? So when I apply the filter of 3 cross 3, that is kernel of size 3 cross 3 on an image of dimension 28 by 28, if I don't use the padding, at that time I'll be losing the dimension from each axis. So my resulting image will be of the dimension 26 by 26. So this is our theoretical understanding, isn't it? Now let's do one thing, guys. Let me just execute this code cell and observe the resulting output shape. Okay, so let me just execute this. Okay, as we can see in the output, the resulting shape by applying this convolution operation is 1, 26, 26, 1. The reason we are losing a dimension because in my case, I have specified my padding as 0. In other words, if you observe it over here, I have not specified anything for padding. Hence, because of that reason, since there is no padding, I am losing a single dimension across each axis. Now observe the next cell, guys. If you observe my next cell here inside my conv2d, I am specifying one more parameter as padding. For this padding, I have set as same. So when I set it as same, what it would do is the system would add the appropriate padding for my input data such that I'll not be losing a dimension whenever I perform the convolution operation. So let me just execute this cell as well so that we'll get the clear understanding. I'll just execute this. Okay, so now if you observe the output, I am now having the shape as 28, 28, 1. Got it? So what we have learned till now? So till now we have learned as how to use the conv2d layer, and in that conv2d layer, how we can specify the kernel size as well as how to specify the padding. And while specifying my kernel size and the padding, one important thing that we have to remember is we have to specify our input shape. In my case, the input shape of individual image is 28, 28, 1. Okay. So with this, we come to the end of this video on learning the basics of using the conv2d layer. In the upcoming videos, we'll learn in detail as how the other functionality, in other words, how the other parameters in conv2d layer works. So I'll see you in the next video. In the last video, we have learnt as how to apply the kernel of a required shape and how to specify the padding. In this video, we are going to learn as how we can increase the number of filters whenever we perform the convolution operation. That means how to use the parameter of filters. So let's see how we can do that. Now moving on, observe the next cell I have written over here. Here in this cell, I have specified my filters as 3 in my conv2d layer. See, if you observe my conv2d layer, I have specified my filters as 3. And along with that, I've specified my kernel size as 3, 3, padding as same, input shape as my input image, which is nothing but the dimension of my single input image. And I'm applying this entire conv2d layer on my input x. So let me do one thing. Let's get the intuition as what is happening here whenever I make use of filter. So as we know already, I'm having an input image which is having a shape as 28, 28, 1. This is an image with single channel, and on this input image I am applying a kernel which is having the shape of 3, 3. And when I apply this kernel with the padding as same, I'll be getting my transformed image which is having the shape as 28, 28, 1. So this is what we know already. Now what is this concept of filters? Now to understand this, first let's understand this term, that is kernel. See, this kernel is also called as filters. Okay, If this kernel is also called as filter, what does this filters is equal to 3 means? See, this 3 comma 3 refers to the shape of the individual kernel or the filter, and the filters is equal to 3 refers to number of such filters, or in other words, number of such kernels. Here what it means is I am using this 3 cross 3 filter 3 times, or in other words, I am transforming my input image using this kernel of the size 3 cross 3 3 times. So if I am applying this kernel 3 times on my input image 28,28,1, then my resulting output or the resulting image will be of the dimension 28, 28 into number of kernels, that is 3. So this is the behavior whenever we apply the filters on my input image. So let me just execute this cell and then we'll take it further, guys. So I'll just execute this cell. Okay, we now have the output as 1, 28, 28, 3. I hope you now understood as how this output is getting processed. Now to get the better understanding as how this particular number of filters works is, I have written as y is equal to layers.conv2d and the filters as 256. And kernel size as 3, 3, padding as same, and the input image is also having the same shape, that is 1, 28, 28, 1. Okay. Now, using our understanding that we had just now, what do you think will be the output shape of the y? As I have said already, whenever we apply the kernel of the shape 3 cross 3 with the padding as same, I'll be getting my output which is having the same dimension as 28, 28. Now, this number of channels dimension will get changed based on the number of filters. So in my case, I have specified my number of filters as 256. So my output image will be having 256 at this last shape dimension. Okay. So since I'm having a batch size as 1, which is nothing but a single image, my total y shape will be 1, 28, 28, 256. So this will be my output shape. So let's just verify it. If I execute this cell, okay, we have the shape that says 1, 28, 28, 256. Now, to bring back the concept of padding, what I have done is in this cell, I have specified as filters is equal to 256, kernel as 3, but padding is equal to valid. That means I'm not using any padding over here. So if I don't use any padding, what do you think will be the output, guys? I'll be losing a dimension on each side. And since I'm using 256 filters, instead of single channel in the output, I'll be having 256 over here in the transformed image. And since I'm having the batch size as 1, I'll be having 1 over here. So my resulting image or the shape of my output y will be of the shape 1, 26, 26, 256. And the reason I'm losing this dimension because here I have specified my padding as valid. Valid is nothing but no padding. Okay, so let's just execute this cell and observe the output, guys. See, if you observe the output, we now have the shape as 1, 26, 26, 256. Got it? I hope this gave you a clarity as how these various arguments in conv2d operation works. Now moving on, guys, here like before I end this video, what I have written is like I'm using my input of the shape 1, 5, 5, 1. This is the same example which I have shown or which we have shown in our previous videos of theoretical section. So if you observe in a theoretical section, we had made use of the example of the input image of the shape 5 cross 5, isn't it? So what happens if I have an input image of the shape 5 cross 5 and apply on my conv2d layer? Let's see. So as a next step, I am creating my X, which is a tensor with the shape of 1, 5, 5, 1, and on this input image or this input X, I am applying my conv2d layer, and this conv2d layer has the filter as 1, which is nothing but a single kernel, and that single kernel is having the shape as 3 cross 3 and the padding is set as valid. So padding is set as valid, that means there is no padding, and since there is no padding, when I apply this conv2d layer or this conv2d operation on my input X, I'll be losing a single dimension. So let me just execute this. Okay, as you can see, we now have the Y, which is having the shape as 1 cross 3 cross 3 cross 1. Now I want to repeat it over here guys, because we'll be using this concept in our upcoming videos, and this is very important as what these each value represents in the output, because this plays a very important role whenever we are taking the baby steps and whenever we are doing everything in a hands-on manner. Okay, so this one represents the batch size, height, width, and the number of color channels. Whenever I'm inputting, it will be number of color channels, but once we transform it, then this one refers to the kernel size. Got it? I hope this gave you a clarity as how this convolution operation works. I know we haven't gone through to the mathematical concepts yet, and we'll be looking into that in the next video. But for now, I hope this gave you a clarity as how the dimensions of the input image changes based on the various parameters that we specify in this con2d layers. Okay, now what I want you to do is I want you to create a matrix which is having the shape as 25, 25, 3. Create my x like this, let's say 1, 25, 25, 3, and try applying on this con2d layer and see what is the output that you get. I want you to try it and let me know in the comment section, and we'll be looking into that in detail in our upcoming videos. But I want you to try it before you jump into my next video guys, because it will be very beneficial for you if you practice in a hands-on manner. Okay, so I hope this video has been helpful to you, and I'll see you in the next video. Hey guys, welcome back. So you are now aware as how to apply this con2d layer on an input image. And you have also observed as how to specify the number of filters and how to specify the padding and how to specify the kernel size as well whenever we specify this con2d layer. In this video, we are going to explore this in detail. When I say explore this in detail, we are going to understand as how the value changes, that is how the input value transforms to get the output value. Now here to begin with, I have defined my input shape as 1, 5, 5, 1. So 1 refers to number of images. In my case, I'm specifying my number of images as 1. 5, 5, 1 represents height into width into number of color channels. In my case, since the number of color channels is 1, I'll say this as a black and white image. And I'm creating a tensor with the shape of input shape. Okay. So this x is a tf.tensor object which contains the shape of 1, 5, 5, 1. And what I'm doing over here is I'm creating a L1 as a con2d layer. And this con2d layer contains number of filters as 1, kernel size as 3, 3, and padding is equal to valid. So that means I am not specifying any padding over here. Okay. And I'm defining my input shape as input underscore shape of 1 colon blank. So that means I'm specifying the shape of individual image. After defining my L1 layer, that is my con2d layer, I'm applying this con2d layer on my input image X, and then I'm displaying the shape of my output Y. So I'm going to execute this cell. Okay, so as a result of performing this convolution operation, the resulting shape of Y is 1, 3, 3, 1. So that means we have lost a dimension on each side of the image. Now, as I said already, we know how this shape changes. The thing that we'll be exploring is how the value of this Y changes. Now, when we say it as kernel size is 3, 3, so what it would essentially does is it would create a parameter matrix. So this parameter matrix will have the shape as 3, 3. So if I want to create a 3, 3, I'll create a box like this. You can imagine this to be 3, 3 kernel. So for this 3, 3 kernel, it would create the parameters with initialized values. So it will have the values ranging between W1, W2, W3 up to W9. So I'll be having 9 parameters for this kernel. And along with defining 9 parameters for this kernel, we will also have a single bias term. So each kernel would result in weight parameters as well as a single bias term. So if I try to get the initialized weights from this L1 layer, I'll write as L1.get underscore weights. And once I execute this, I'll get the resulting array like this. These are the initialized weights of this L1 layer, guys. Along with this initialized values of weights, we also have a initialized value of bias term as well. The initialized value of bias term is 0. Now, When we specify it as kernel size as 3, 3, this would result in initialized values of weights as 9, that is 9 weights and single bias term. Now whenever we are specifying this conv2d layer, we can also specify as we don't want to initialize the bias term itself. At that time, we can specify the parameter use_bias as false. So in this case, I am creating the same, that is x with tf.random.normal with input shape, that is 1, 5, 5, 1, and I'm applying this x on my L1 layer, and on my L1 layer, I have specified my use_bias as false. So this time if I print the shape of y, this time also I'll get the same shape, that is 1, 3, 3, 1. But if I display my x, this x will have the shape as 1, 5, 5, 1, and if I display this L1 dot get underscore weights, so this time I can only see my initialized values of weights, guys. So that is the difference. Now if I display my output y, so if I display my output y has the values as 0.5071 minus 0.399, 1.57 and so on. Now what we are going to do is we are going to test our theoretical understanding. We have understood that suppose if we have an input image like this, so I'll write it like this, I'm having an input image and this is having the dimension as 5, 5, 1. Okay, so this single input image is having the dimension as 5, 5, 1. Now, if I have a kernel of the size 3, 3, so to represent this kernel, I'll write it in a blue color. So I'm having a single kernel, and this single kernel is having the shape as 3, 3. Now what I'll be doing is I'll be placing my kernel on top of this input matrix, which is nothing but input image, and find the dot product between the images, the pixel values of that region with the weight values. So I'm going to repeat over here. What I'll be doing is I'll be placing my kernel on top of my image and find the dot product between the pixel values of the image on that region with the initialized values of this kernel. So that is what it means by performing the convolution operation. So to test this out, what I have written over here is I have written as x underscore flat, and from this I'm extracting 3 by 3. Yes, I'm extracting the dimensions of 3 by 3 from this input data x. Okay, and I'm converting into a single long vector. And I'm defining my w and w as tf.rayshape l1.get underscore weights comma -1. So that means I'm flattening out my entire w matrix. So this will have my initialized weights, and what I'm doing over here is I'm finding the dot product between this input and the weights. Now as per our theoretical understanding, when it performs the dot product between input and weights, this should result in a single output, which is nothing but transformed output of that middle pixel. So I'm going to execute this cell. So we have the output that says 0.5071, and if you observe the output in y, the first value over here, it says 0.50717896. So this confirms our theoretical understanding, guys. So with this, we come to the end of this video, guys. And in this video, we have learned as how the mathematical operation takes place whenever we perform this convolution operation. In our previous class, we have learnt as how the convolution operation works on our input image. Now in this video, let's see how the concept of pooling layer works. So to start with, let's see how does this average pooling works. Now to understand this concept of average pooling, consider the output that we have from our previous class, guys. So this is the output that I have from my previous class. And this output that we see over here, that is output of the size 1, 3, 3, 1. The one that I have highlighted over here, this is the output that we will consider it. And we are going to apply the average pooling on this layer, guys. That is the output layer. Okay. Now if I represent this output in the form of a matrix, so this looks like a 3 by 3 matrix. Do you agree with me? See, this is a 3 by 3 matrix. Now, how do we perform this average pooling? So the way we apply this pooling is we are going to mention the kernel size. So let's consider the kernel size of 2, 2. So if I consider my kernel size as 2, 2, the way this average pooling would work is I'm going to place my kernel on top of this output layer. So in my case, since the kernel size is 2 cross 2, I'll place my 2 cross 2 kernel on top of my output. So this is how my first position of my kernel would be. And then I'll also mention my stride, and based on the size of stride, so I'm going to move my kernel on top of this output layer. Now the next question is, how does this average pooling works? The way this average pooling would work is, when I place my kernel on top of this output, that is on top of the region on which I want to apply this average pooling layer, the system is going to compute the mean of every value that is present in that region. Now if I want to say it in terms of mathematics, so what it means is I'm going to select the first 2 rows in my output and first 2 columns in my output, and then I'm going to compute the mean of this region, guys. So let's do the same, guys. So here in this cell, if you observe over here, I have written as tf.math.reduce_mean. So what this will do is, this is going to take a matrix. In other words, it is going to take the tensor object and it is going to compute the mean. That's it. And it is going to return the scalar value. So for the region, I have selected as y colon, comma, colon 2, comma, colon. So that means I'm extracting the 2 by 2 region of my output y. Okay. Now if I execute this particular cell, I have the output that says as 0.30. So this is the output that I'm getting if I apply this average pooling on my output y. Now let's do the same, guys. If you observe over here, I'm applying the average pooling on top of my y. See, I have written as average pool is equal to layers.average pooling 2D. So this is the function that we use inside the TensorFlow to perform the average pooling. So average pooling 2D, I have specified my pool size as 2, 2, which is the kernel size. And I have written my strides as 2. And I have also mentioned that padding is equal to same. Now once I apply this average pooling of y, that is once I apply this average pooling layer on top of my previous output, that is y, I have the output that says as 0.3040. And if you observe over here on top, I had got the same value, guys. See? So to recall, so the way this average pooling would work is, whatever the input that I pass for this average pooling layer, depending on my kernel size, that is my pool size, the system is going to place the kernel on top of the input which I am giving for this average pooling layer, and then it is going to perform the average of every values that are present in that region. That's pretty straightforward, guys. And depending on my strides and depending on the padding, it is going to do the same operation by moving along left to right and top to bottom for each of the image input. The next concept that we have in case of pooling layers is max pooling. So in case of max pooling, the way it would work is similar to the average pooling, guys. The only difference is the system is going to return the maximum value of that particular region. So in case of average pooling, we have seen that, okay, this is going to compute the arithmetic mean. But in case of max pooling, the system is going to return the maximum value of that particular region. So in my case, the first region that I have highlighted just now, the maximum value over here is 1.42. So as a result of applying this max pooling layer on top of this input image, then as a first output, I'll have the value as 1.42. So let's observe the same in the output, guys. So if you observe over here, see, I have the output that says as 1.42 as a first output, that is the first value in my output. So this was about pooling operations on the input image, guys. So let's continue more in the next video. So you are now aware as how the concept of convolution works on the input images. Now to recall about this important concept, let's consider this example, guys. I'm having an image. Now let's say this image is having the dimension as 30 by 30. Now, if you look at the components that I'm sending for my convolution operation, so I'll be using the component of kernel size. So this kernel size is nothing but the weight matrix, which we will place on top of the input image. So in my current example, I have written as kernel of 3 by 3. So this would mean this is a kernel and this is of the shape 3 by 3. And what we will do is we will place this kernel on top of this input image, and we are going to slide from left to right and top to bottom to perform the convolution operation. And now you already have an intuition as what this convolution operation is. So this convolution operation is nothing but finding the output, which is nothing but the finding the dot product between the image pixels of that region with the weight matrix to get the required output. So that's what we know already. And along with that, you also have an intuition as what this pooling layer means as well, isn't it? So you have learned about the average pooling as well as the max pooling in your previous class. So in this video, we are going to extend this concept of convolution operation, and while performing the convolution operation, the next step that we are going to do over here in this video is we are going to apply the activation on each of the convolution operation. Now to understand the same, here I have defined my input shape as 1, 5, 5, 1, and you know already what are these individual component means as well, guys. So I'm not going to explain it. And here I have written my x as tf.random.normal of input shape. So this is generating a tensor object with the shape of input shape. And as a next step, I have defined my L1, which is a conv2D layer, which has the number of filters as 1, kernel size as 3, 3, padding as valid, and input shape as input underscore shape 1 colon blank, which is nothing but 5, 5, 1. So height, width, and this one is number of channels, guys. And here if you observe, I have written as use underscore bias as true. So this is what I have written, guys. So this would mean that if I am performing the convolution operation, what the system will do is for each of the region, the system is going to take the dot product between this weight matrix with my input image of that region. It is going to add it with bias term. So that is what it says, guys. So let me just execute this. So if I just execute this, I have the resulting output of y as 1, 3, 3, 1. So we have lost a dimension because I have mentioned my padding as valid. Okay. Now if I display my x, so this is my input which I have used actually. So this is how my input looks like, which has the shape of 1, 5, 5, 1. And if I display my y, so this is having the shape as 1, 3, 3, 1. So this is how my output y looks like. Now here in this cell, I am performing the mathematical operation in a manual manner. So I'm extracting the weights. To extract the weights, we just specify the layer name and use this get underscore weights method, guys. And I am using the 0, that is I'm mentioning the index as 0 to extract the weight terms. And here I have written as b is equal to l1.getWeights, and inside the indexing operator, I have mentioned the index as 1. So this will extract only the bias term. And after that, here I am flattening out my input. So to flatten out my input, so as a first step, I'm just extracting the first 3 by 3, guys. So if I have a matrix, so in this case, I have an image of the size 5, 5. Okay, and on this image of 5, 5, I'm extracting only 3 by 3 components. So to extract the 3 by 3 components, I have written as tf.reshape x colon, 3, colon 3, colon. So this is going to extract only 3 by 3 region of my 5 by 5 matrix, which is nothing but my input image. And here I am performing the reshape of this input -1. So this is going to flatten out my input image, guys. And this flatten out or this flattened input image will have the dimension as 9 because I'm just extracting this 3 by 3 region of my 5 by 5 image. And in the same way, I'm flattening out my W values. So I have written as tf.reshape w comma -1. After that, I am performing the dot multiplication, that is here I have written as tf.tensor.xflat comma wfat, and then I am mentioning my axis as 1. So this is going to perform the tensor dot operation, and then I'm adding the bias term, guys. So let me just execute this. So we have the output that says as minus 0.1414. And if you observe over here, in my output of y, I have the same value. Now to get the better visualization, let me display my b, guys. So if I display my b, the value of bias term will get outputted. So the value of my bias term is 0. So in my case, it is 0, but depending on the initialization that we use in our future classes, this b weights can vary, but the way this is going to work, it's just like that we are seeing over here. It is going to perform the dot product between the input image of that region with the kernel of that region, and it is going to add the bias term on top of it. Okay. Now, let's see what happens if I apply the activation on top of this output, guys. Now observe over here. Here I have used the same input image and I'm defining my x as a tensor object with those initialized values. I'm applying this conv2d operation, and this conv2d layer has filter as 1, kernel size as 3,3, padding is valid, and observe over here. Here I am performing my activation as ReLU. Okay. So along with everything that I have applied previously, I'm adding one more additional term, that is activation as ReLU. And after that, I'm applying this L1 layer on my input image X. And finally, I'm displaying my output of Y. So let me just execute this. So if I just execute this, I still have the output as 1, 3, 1. And if I display my X, this is how my X looks like. Okay. And if I display my Y, this is how my Y would look like. Okay. Now, observe this. This is very important, guys. Here in this cell, I'm just mathematically computing the output just like we did before, guys. So W, so this is going to extract my weights. B, this is going to extract the bias term. And X flat, so this is going to extract the 3x3 region of my input image, and it is going to flatten it. And W, it is going to flatten out my weights vector. And then I'm going to perform the dot product between my input region with my weights kernel along the axis as 1. And for this, I'm adding my bias term. So if I just execute this, I have the output as minus 0.68. Now, what does this activation means? So let me just show you in a visual understanding as how this activation works, and then we are going to execute this particular cell, guys. So I'm having an image, and this image is having the shape as 5x5. And on top of this image, I am placing my kernel, and this kernel is having the shape of 3x3. So what I'll do, I'll perform the dot product between the input image of that region with kernel values, that is the initialized weight terms. So I'll write it over here as dot product of input with weights term. Okay, after I perform the dot product, this is going to return me the output. But here, if you observe, I had written as activation is equal to ReLU. So that means whatever the output that I get. So let me just highlight this. So whatever the output that we get as a result of applying this dot product operation, we are going to apply the activation function on the resulting output. So my activation will be applied on top of this output. So the resulting values will be the resulting outcome of this activation layer, guys. So let's test it out. So here I'm applying my ReLU activation function on top of my previously output, that is tf.tensor.xflat, wflat, axis is equal to 1. So let me just execute this. So if I just execute this, I have the output as 0. We have the output as 0 because I am performing the, or I am applying this ReLU activation function. The way it would work is The ReLU activation function, if you remember previously in our starting classes, I had explained that the ReLU function has the function that says as max of 0, x. So if the value is less than 0, the output will be 0. And if the value is greater than 0, at that time it is going to return the x itself. Okay. In our case, since the value of my outcome or my value of my output is less than 0, this is returning the value of output as 0, guys. And we can observe the same over here as well. See, the first output as a result of applying this ReLU activation function on top of our 3x3 kernel is 0. Okay. Now for the sake of completion, here in this cell, I am performing the activation of sigmoid. So let me just execute this cell. See, instead of ReLU, I'm just applying the activation of sigmoid. So if I display my X and Y, this is how my X and Y looks like. Now here, I'm extracting my weights, bias term, I'm flattening out my input X of 3x3 region. I'm flattening out my W, that is weights kernel, and I'm performing the dot product. So if I just execute this, this is the output of the this is the output for performing the dot product, that is minus 0.03. Now on top of this, I'm applying the sigmoid function. So tf.nn.sigmoid, and I'm just inserting the previously generated output, that is tf.tensor, that is this term. So if I just execute this, I have the output as 0.490, and if you observe over here, see, that's the same value that we have as an output as a result of applying this con2d layer with kernel size of 3,3, padding as valid, bias as true, and sigmoid activation layer. I hope this entire series of classes that we have took till now gave you a clear understanding as how this convolution operation works from scratch, guys. So we started our series of this convolution layer by defining the input image from scratch. So we defined our input matrix of 5x5, and using that input image of 5x5, we have learned each and every component that we are sending inside this con2d layer. Now in our further classes, we are going to use this understanding of con2d layer and implement it for the real world data set. I hope you guys are as excited as I am, and I look forward to seeing you in the next class.
Hey guys, welcome back. Now, you are already aware as what is convolutional neural network and what are the various activities that we'll be performing inside this convolutional neural network. Now here, let's take a simple example, okay? The task that we are going to consider is image classification. Now, if I'm performing this task of image classification using this convolutional neural network, how exactly my CNN architecture would look like. Okay, now let's say this is the image that I'm dealing with. So this is the image of cat, and this will act as my input. Now if I'm using this image for my convolutional neural network, in my first layer I'll have an input layer. So I'll draw an input layer. So this will be my input layer. The expectation of this input layer is it is going to reshape my required input. So it will, sometimes it is going to reshape, or at least in an example scenario, at least it will get an input from my input data, that is images. Now, once the data reaches my input layer, the next common activities that we'll be performing inside the CNN architecture would be, we'll perform some kind of a convolution operation, and inside this convolution operation, typically we'll have some kind of an activation function. So let's say ReLU is the activation function that I'll be using, and likewise in this convolution layer I'll be specifying the number of filters and also what is the shape of each filter and so on, whether padding should be there or not. So I'll be mentioning all those things, and I'll be performing this series of convolution operation. So I'll have one CNN layer, I'll have one more CNN layer like this. So likewise I'll have multiple CNN layers. Now after multiple CNN operation, the next common thing that we will be performing is we'll perform some kind of an operation of pooling. It could be mean pooling, or sometimes it could be max pooling. So we'll have some kind of a pooling operation that would happen. So hence I have shrink the dimension, so it would become pooling. Now after the pooling, we'll again go ahead and perform some of the convolution operation.
So I'll perform continuous convolution operation, and after I've done this convolution operation, I'll again perform some kind of a pooling operation. And once I have done this series of convolution operation and pooling operation, convolution and pooling operation, on the final value that I would get, let's say this is my last layer, okay? The highlighted one is my last layer. Now on this last layer, so whatever the output that I'll be getting over here, I'll be converting it into a flattened layer. That means I'll be converting it into a single dimensional vector representation like this. Okay, so once I have done this single dimensional vector representation, I'll be connecting this particular layer into fully connected layers. So this flattened layer will be connected to a fully connected neural network, and then the output of my fully connected neural network will give me the exact output for the task that I'm looking for. Let's say if I'm using this CNN architecture for the performing of image classification, final layer of this fully connected neural network will have a single neuron, and that single neuron will have the activation of sigmoid, and using that sigmoid activation, I'll be deciding whether I should classify that given input, whether it belongs to the class of cat or whether it belongs to the class of dog. So I'll have a single neuron over there, and that will have the activation of sigmoid. Now this is how we'll be performing the task of binary classification here in this scenario, specifically for the images, that is image classification using this convolutional neural network. Now to put it short, so I'll have a input layer. Now here this input layer takes the input images. After I get the image, I'll be performing the series of convolution operation, and I'll be using respective activation function over there. After I perform series of convolution operation, I'll perform the pooling layer over here. That means I'll reduce the dimension. Okay, so I'll be going into this pooling layer, and after this pooling, I'll again perform series of convolution operation here, and whatever the final output that I would get as a result of this series of CNN and the pooling operation, I'll be converting into a flattened layer. So this is a flattened layer. So I'll convert this into a flattened layer, and this flattened layer will be converting my multi-dimensional array into a single dimensional vector representation, and this single dimensional vector representation will be connected to my fully connected neural network, and in the output layer of this fully connected neural network, I'll have the required number of neurons which are suited for my specific task. Now here in the example, I've taken the example for binary classification. So in the output layer, I'll have a single neuron, and this single neuron will have the sigmoid activation function. Now based on the output that I'll be getting over here from the sigmoid neuron, I'll be deciding as which class my given input would belong to. Okay, so I hope this video has been helpful to you, and do subscribe to our channel for more such updates, and I look forward to seeing you in the next class.
Hey guys, welcome back to the video series on deep learning. Now today we are going to perform the task of binary classification on the image data. Now to do this, I'm going to make use of special images that is called as cats and dogs, guys. So I'll make use of the images of cats and dogs to perform this task of binary classification to tell, okay, given an image, whether it contains an image of cat or whether it contains the image of dog. That's a simple binary classification task that we are going to do. Now to do this, we'll make use of convolutional neural network, which we have studied till now. So let's see how we can do that. Now to get started, I'll just connect to my Google Colab instance. So this would connect to the backend server. In the meantime, I'll write the code to get the data from my Dropbox. So I have saved my code, or I've saved my data set in the Dropbox. So I'll just download that file from the Dropbox. So this will take care of downloading the file from my Dropbox. And once it's downloaded, okay, that was very fast. I'm going to perform unzip activity. So unzip, I'll say cat dog dot zip, and after that I'm going to remove as well. I don't want to keep it in the memory. So cat dog dot zip. So I'll just execute this. So this would unzip it, and this would also remove my zip file. Okay, this has been completed. Now I'll just clear out this output, and let's display our file explorer. So I have two folders as of now. So there is one test set, another one that is called as training set. Okay, that's great. So if I expand this training set, it also talks, there is one more subfolder that's called as training set. And if I expand this, I'm having the images of cats and dogs. Now let's keep it very simple, guys. Okay, so we'll keep it very simple. What we're gonna do is we'll just select this training set and we'll create it into three parts. We'll simply use this training set itself and we'll create it into three parts, and this time we are going to manually create the split. So I'm not going to make use of any library. I'll show you how we can actually do this split, create some subfolders itself using the inbuilt Python OS library. So let me just show you how we can do that. Now before we get started, what I'll do is I'll just copy this path. So this let's say this is where I'm having the folder slide. So I'll just copy this path and I'll create it as a constant. So I'll say training directory, okay, or I'll keep everything uppercase, okay, training directory, and I'll set it to be equal to this complete path. Okay, now what I'm going to do is I'm going to create three folders, and those three folders that I'm going to call it as dir, okay, and I'll call it inside my Python list. And I'm going to say the three folders that I'm going to create is training folder, test folder, as well as my validation folder. Okay, three folders that I'm creating. Now where am I going to place this particular folder? I'm going to place this particular folder in a root place. So I'm going to say root directory. So my root directory will be in my current working directory. Okay, so dot represents my current working directory. In my current working directory, I'm going to create a folder that's called as data directory. Okay, I'm just defining the constants, guys. So once I execute the code, you'll understand what is happening in the backend. Next, I'm going to create some directory. So I'm going to say that if not os.path exists. Okay, so this is going to check whether I'm having the path which is already defined, which is present inside in my working directory or not. So I'm checking os.path exists, and I'm going to check whether this root directory is already defined. Now before we do that, I'll have to do one important thing. I'll have to import this OS library, or else I'll get an error. So import OS. Okay, so I'm checking if the path does not exist. If it does not exist, then I'll do it like this. I'll say for, let's say, d in dirs, that is the directories that I've mentioned. So I'm going to make sure that os dot make directories. Okay, I'll specify my path like this. So I'll say os.path.join. Okay, I'm going to say root directory, and I'll be joining the name of D. So this means that if I do not have the root directory present, the folder name as data directory present, then I'm going to create a folder that is called as data directory. And the special thing is, inside this data directory, I'm creating one more subfolder that's called as train, and along with that I'm creating test folder, and along with that I'm also creating a validation folder. So I'll just execute this, guys. Okay, we've got an error. I think this is related to the parenthesis, so let me just correct it. Okay, so this has been executed. Now let's explore our folder structure. We can clearly see that this is a folder. Okay, so this is a folder. Now I'll expand this folder. Now inside this folder of data directory, I can see three subfolders: test, train, and valid, just like we have specified over here. Okay, so what I have currently done is I have created three folders called test, train, and valid. Now what I'll be doing is, moving forward, I'll get all the images that are present in training set folder into copying all those images to test set, training set, and the validation set. So I am performing the split manually, guys. The reason that we are doing over here is I want to have more control on the data. So that's the only reason that I'm doing this.
Okay, now in order to do this, that means if I want to move something out from one folder to another folder when I'm moving the files, I'll obviously require to shutil library. Okay, so I'll import this shutil library as well, and I'll keep it ready. Now I'll write the code. So I'll write something like this. I'll say for directories that are present in list of directories in the folder of training directory. Okay, remember my training directory is my original training directory, that is this. So if I simply expand this, you can see there are actually two subfolders that are cats and dogs. Okay, now what I'm telling over here is I'm going to say that, okay, I'll say os.path.join. Okay, get this root directory, and then get something called as train. Okay, so create a inside my root directory, go to the train folder and then create a directory over there. Okay, and then os.mkdir de. So this de, what it actually does is, say I'm going to explain you step by step. Here I'm displaying all the folders that are present in my original training directory. So in my original training directory, if you have already seen, I'm having cats and dogs. Let's say I'll get the first time I'm getting the output as cat, then I'll use that cat value and I'm joining that inside my training directory. So I'll say train, inside my train subfolder, create another folder called cat with the help of mkdir command. Okay, now once I do that, so what I'm going to do is I'm going to select random images of cats, and once I select the random images of cat, I'll transfer it to my training site. So I'll say for image in np.random.choice. Okay, I'll just select some images in a random manner. And once I am selecting the images in a random manner, the way that I'm selecting is something like this. I'll say os.list directories, and where I want to list the directories which are in the path of os.path.join, and I'm actually inside my training directory. Okay, and dir. Got it? So I'm iterating over every element. It's not every element, I'm iterating in a random manner for the files that are present in the cat subfolder. I'm just giving an example. Okay, for image in this, so what should be the choice? I mean, how much that I should return? So I should return something like this. I should return the length of os.list directories of os.path.join. So where should I get the number of directories, guys? Yes, I should get the number of directories from here. Okay, so I'll use the same directories, train directory, comma, dir. Okay, once that is done, I think it should be over here. So I'll get 0.7. Okay, and I'm going to mention that replace is equal to false. So what it clearly says over here is, let me just close this and I'll explain what is happening over here. Now I'm getting some random values from the OS list directories path. Now let's do one thing. I'll just take this code, okay, and I'll paste it over here, and instead of dir I'm going to say cats. Okay, and I'll simply execute this. Okay, it is expecting some parentheses. Let's keep that. See, this is returning me the list of cat images that I'm having in this cats subfolder of my training directory. Now what I'm telling to my system is, okay, let's do one thing. I'll save this in a specific variable itself, cat.list. Now I'll say cat_list. So this contains the images of cats.
which is present inside my Python list. Now I'm telling as, okay, np.random.choice. Now inside this np.random.choice, I'm specifying this thing. So we know what this thing is. So I'll show you what it means. So before that, I'll have to import my NumPy library. So I'll add it in the above cell. So I'll say np.random.choice. And then, so this thing that we have, that is OS list directories and getting this path join and everything. So this would actually mean the cat list, which we have just created. So I'll say cat_list. And from this cat_list, I am specifying the second argument. So the second argument is the size. Okay. So if you look at the documentation of np.random.choice, it actually generates the random sample from a given one-dimensional array data. So in my scenario, the one-dimensional array data is the list of images that I'm having in this cats folder. So that is the one-dimensional array. And how much that I should return? I should return 70% of the data from this cat list. Now, in order to get that, I have mentioned something like this. I have mentioned as int length of cat_list. And not just cat_list, I'll have to get 70% out of it. So length of cat_list multiplied with 0.7. Okay, whatever the value that I'm going to get, once I multiply this length with 0.7, I'm converting into integers, because like when I'm getting the images, I cannot get 4.5 images. I have to make sure that I'm sending the integer values. Hence, I have mentioned like this as int of length. Okay. And then I've also mentioned one more parameter, that is replace. And I've mentioned that replace as false. The reason, because once I have selected that item or once I have selected that image, I should not select that image again. And that won't, if I'm selecting the same images in training set and test set, it doesn't make sense for me for creating 3 splits. I could have used something else itself. Like there was no need for splitting itself, isn't it, guys? Hence, I'm specifying that replace as false. Now, if I just execute this, okay, it says keyword cannot be an expression. Okay, this is actually not an expression. See, there was a typo error, guys. Now it has been fixed. So this has returned a NumPy array object where it contains the image names of the cats. And what I have done is I have selected random images and the length is 70% of my data set. So if I write something over here inside this for loop, so what it actually is going to do is it's going to extract the images of cats. First, it's going to extract the images of cats, and then it selects 70% images, or the 70% of the image that is currently present there. And once it gets that 70% of images, what we would do is we are going to copy these images to the original folder. Okay, so that is what we are going to do. Now, in order to complete it, I'll write the command, guys. I'll say org, okay, and I'll simply say os.path.join. Okay, I want to join train directory, comma dir, comma img, okay, the image name that I'm getting over here. So, and then I'll say destination. So that destination is something like this. I'll say os.path.join, and the destination is D and image name. All right. Then in order to copy this, I'll say shuttle.copy. This time I'll say copy file, specifically copy the file which is in original and copy to the destination, and then remove my original. So os.remove Now instead of copy file, I would have used move file, but in case if there is any error in copying or any other activity, I was not interested in moving completely, hence I am removing after copying. So what this is going to do is, this is going to select 70% of images in both cat folder as well as docs folder, and once it does that, it goes inside each folder and selects 70% of images from that subfolder and transfer it to the another folder which I have created earlier, that is data directory train subfolder, and places it over there. So inside my train, I'll create two subfolders. This time I'll say cats and dogs, and in cats I'll have 70% images from my original data, and in dogs I'll have the same 70% images from my original images. So I'll just execute this. Okay, so this activity has been completed. Now let me expand our train folder. So if we expand our train folder, I have two subfolders, cats and dogs. Now if I expand cats, I'll have 70% of images that has been copied from my training set, and 70% of dogs images that has been copied from my test set for the dog subfolder. Alright guys, so what we have done in this video is, we have actually downloaded the data from a Dropbox, and we have done some pre-processing activity, that is performing the split between my data set into training set, test set and the validation set. Currently we have seen how we can split the data from my training set into the training set itself, that is training subfolder. And let's continue in the next video. In the next video, we'll continue doing the activity and we'll move our data set to the test folder as well as the validation folder. So the strategy that we are going to keep is, I'll keep 70% of data for training purpose, and then I'll keep 15% for testing, and I'll keep another 15% for validation. Okay, so this is the plan of action when we are writing this program, guys. So I'll stop the video over here and let's continue in the next video. Hey guys, welcome back. Now in the last video, we have downloaded the dataset from the Dropbox, and after we downloaded the dataset, we have unzipped it and we have imported necessary libraries. In our case, we have just imported OS, SHUTIL and the NumPy library. Now along with that, what we have done in last session is, we have created our own data set. That means we have split the data set into one part. For now, what we have done is, okay, we have said we are going to make use of training data, and using that training data, I'm going to create into three separate parts. Now, in order to do that, I have mentioned that, okay, first I'll extract the data. So if you look at it, currently all my data are present inside my subfolder of training set. Okay, so if I expand my training set over here, I'm having the images of cats and dogs. So from this training set, we are going to split into three parts, that is train, test and valid. Now to do that, we are actually making use of OS library. So this is going to create some root directory. I'm going to put all our data in the root directory, which is called as in my current directory, I'm creating a folder called data directory. So inside this, I'm going to put everything. Okay, so if you look at it, in my data directory, I'm actually having three subfolders, test, train and valid. And what I'm going to do is, I'm just going to use all the data which is in my training set, get 70% out of it, and I'll send it inside my training data, and 15% into my test data, and another 15% to the validation data. So what we have done in last session is, okay, we have extracted 70% of the data. Now once we extract the 70% of the data, let's do one thing. Let's count the number of images that we have inside our directory. Okay, now let's assume I'll run this code. Okay, I'll just run this code to measure as how many number of images that we have over here after we have done this activity of removal. Okay, so now instead of dir, I'll just say cats as an example. Okay, so I'm just having left out with 1201 images. So if I'm trying to extract the images, so what it actually means is, see, if you look at my previous code, I have actually removed it once I have separated my data set. So what I should be doing is, when I'm specifying this for loop again, I have to mention it like this. So I'll say using the data in the training directory, and I'll have to extract 50% of it. Okay, because I have already extracted 70% out of it. So whatever the value that is left over there in my training directory, those are all the 30% of the data. Now in that 30% of the data, I want to get 15%. So it will be a 50% of the existing data. Okay, now I'm extracting it and I'm sending it over here. So this would extract 50% of the remaining data into my test directory. Okay, so here I mentioned destination as test directory, and I'm getting everything guys. I'll just execute this. So this would extract 50% of my remaining previous data back into my test directory. Now if I simply copy and find the length, so if I find the length, I am now left out with 601 images. Now what I'll be doing is I'll use this complete 601 images into my validation data. So while specifying the number, I'll just remove this into 0.50, and I'll just use everything that is present over there. Now I don't have to use the int as well, because length will obviously is going to return me the integers. So now I'll just execute this. Okay, so I'll have to mention it as valid. Great. So what I have done right now is I have moved all the images that are present inside my original training data. So this is my original training set. Now if I expand this, see, currently it is empty. The reason because I have moved all the data which was actually present in this folder into my test, train and valid. So we can verify the same. I'll expand my train. See, I have two subfolders, cats and dogs. Okay, so it's taking a while to load because there are so many images. See, you can see the various images of cats. I'll do one thing. I'll just download an example image of cat. So if I download an example image of cat, so this is how an example image of cat looks like. Okay, so we are using this collection of cats and dogs, and we are going to build the classifier on top of it. Now we can explore the test directory as well. If I expand my test directory, see, I will be having the images of cats and dogs over here as well. Okay, so what we have done right now is we have moved all the data set into three subfolders: test, train and validation data. Now let's do one thing. Let's see how the data is distributed into all of these subdirectories. So in order to do that, what I'll do is, let me check if I already have my root directory defined. Yes. So this is what my root directory looks like. Okay, so my root directory is my data directory. Let's do one thing. I'll write a code that would look like this, and then I'm going to explain. I'm going to create a X and Y as a blank Python list. Now after this, I'm going to write something like this. I'll say for folder which is present inside my directory of root directory. Okay, and then I'm going to say that I'm going to create a dictionary. I'll call it as D, and in this dictionary I'll create a key as cats, and I'm going to initialize to be equal to 0, and I'll create one more thing called dogs, and I'll initialize to be equal to 0. Then I'm going to create as class underscore dir, and I'm going to say that os dot path dot join, and I'm going to say root directory comma folder. Okay, and then I'm going to say that, okay, for class I'll say cls in os dot list directory of class underscore directory, and I'm going to mention that images is equal to os dot path dot join, and I'm going to get class dir comma class. Okay, now after this I'm going to say that, okay, for d cls is equal to length os dot list directory of images. Okay, x dot append, and I'm going to append dcls, and I'll also do the same. So I'll also say y dot append, and I'm going to append the folder name. Okay, so I'm using my F formatting, guys. So folder, and I'll write as class. Okay, let's invert it. I'll say y dot append values, and for x I'm going to store the folder names. So let me just execute this, and then I'll explain what is happening in this code. Now here in this code, to begin with, I have created a blank Python list called x and y. Now after I created this x and y as a blank Python list, I'm going through every directory which is present inside my root directory. So this is my root directory, and I'm going through every folders that are present inside this root directory. And inside that, I have defined a dictionary as D. Okay, and I have mentioned that, okay, for each folder, let's say I'm going inside my test folder. So in the first iteration, I'll have the folder is equal to test. So that is the name that it is going to get. And then I'm saying as, okay, for class in os.list directory. Now to make it very easier for you to understand, I'll copy this code and I'll explain in my OneNote. That will be easier for you to understand, guys. So I have mentioned that for folder in os.list directory, that means each time when I'm running this iteration, this folder will get the folder name of either test, train or valid. Let's assume it takes the folder is equal to test in the first iteration. Now once it gets the folder is equal to test, I'm saying as, okay, create a Python dictionary which is called as D, and the keys are cats and dogs, and I'm initializing the value to be equal to 0. Now on top of this, I'm getting class directory and I'm joining this root directory. The root directory is data.directory. I'm joining this. That means I'm going inside a subfolder of this root directory. That means I'm going inside this test folder because that is what is present in this first iteration. And I'm storing that complete path like data directory and the test inside my class directory variable. Now after this, I'm going inside the subdirectories of this class directory. That means I'll highlight it. So I'm now going inside this test folder. So the subdirectories are cats and dogs. So cats and dogs. Now in first iteration, CLS will take the cat. Okay. Now I'm checking as how many number of cats images are present in this subfolder of cats. In order to do that, first I'm getting that complete path by saying as, okay, join my test with this cat subfolder name, and then I'm calling the len on top of it. So this is going to give me the number of images that contains the images of cat in this test subdirectory, which means that, okay, in my test folder, how many images of cat that I'm having. And once I do that, I'm appending that value into my Y Python list, and I'm also storing inside my original Python dictionary, guys. And then in my X, I'm just storing the folder name, that is the in this scenario the folder is the test, and test underscore the class that is cat, and that is what will be stored in the first iteration. And then it goes ahead and for CLS it picks dogs, and it does the similar activity and checks how many images of dogs that I'm having over here, and adds it in my Python dictionary and get that value in y.append. Okay, and it also appends that folder as well as its class name to this X as well. Now once I've done that, I'll go up, and this time I'll pick the next directory, that is train. So once I pick the train, I'll go inside the train. I'll have another subfolders of cats and dogs. In the same way, I'll see how many number of images of cats and dogs are present. I'll get that number and I'll proceed ahead with the validation data, that is valid folder as well. Now in this way, I'm iterating over every subfolder inside another folder. And in final, I'm checking as how many number of images that I'm having with me. Now once that is done, I can create a visualization to see as, okay, how I have the data that is present with me. So if I want to create a visualization, obviously I'll have to import Seaborn library. I'll use Seaborn, guys, okay, and I'll say sns.set_style, and I'll use the style of dark grid. It will be nice to see, and I'll say import matplotlib.pyplot as plt, and I'm going to say plt.figure, and I'm going to set my fig size to be equal to, let's say, 12,5. okay, and I'm going to create a Seaborn object, so sns.barplot, and I'll say x, y, and I'm going to set the title. So title is data distribution, and finally I'm going to show my image, plt.show. So this is going to give me the visualization as how many number of images that I am having in my training set, as well as my test set, as well as my validation set. So 70% of data is in my training set, 15% each in my test as well as my validation set. Okay, so now that we have done all the activity, in the next video, let's see and let's print some of the sample images that we have for cats and dogs, and then take our analysis further. So I'll see you next time, guys.
Hey guys, welcome back. So welcome back to our deep learning series. Now here in this video, we are going to perform the data visualization. Now I know we should have done this a long time ago. That means just like when we download the data set, we should have done that. But we were actually focused on splitting the data set into 3 parts: training set, test set, and the validation set from our own using the OS library. And that is the reason we lost the concentration on visualizing the data. So let's do one thing. Let's do that analysis now. So let's visualize the data and see how the data looks like. So I'll download the data set from my Dropbox, and once it's done, I'll unzip it and I'll remove the files and I'll import the necessary libraries. In this scenario, I'm just importing 3 important libraries: OS, SHUTIL, and the NumPy library. Since I'm interested in creating the visualization, it's very important that I'll be importing my Seaborn library as well. And along with that, obviously, I'll also import matplotlib library, that is pyplot module. So I'll say import Seaborn as SNS, and I think we have already done that. So instead of doing it again, I'll just cut this page thing. Okay, now I'll add it over here so that we have all the imports in one place. So once this has been imported, now let's do the visualization on our data. Now, in order to do the visualization, let's do the visualization on our existing training data, and let's count as how many number of images that we have for each of the class. So that one thing we haven't done till now, isn't it? So let's do that. I'm going to mention what is my training directory. So I'll specify my training directory as training directory. Okay. And where is this training directory is present? This training directory is this. Okay, my training set is my training directory, and inside this training set we have the necessary images. So I'll copy this path. Okay, so this will set the constant of training set, and once I have got the data from this folder, what I should be doing is I should count it. Now in order to do that counting, I'll create a Python dictionary as D, and I'll specify the classes of the data that I'm having. So I'm having the images of cats. Initially I'll set it equal to 0, and I'll have the images of dogs, and the number of dogs is 0. So this is what I'm initializing to get started. Now once this dictionary has been created, I'm going to go through every directory that is present over there in this training set, and after I go inside that particular directory, I'll do the iteration. That means I'll go inside this subdirectory of cats and I'll count as how many number of files are present, and I'll do the same thing for the dogs as well. Now in order to do that, I'll say that okay, for D in os dot, where is the directory? I'll have to list the directories. So list directories of the folder of my training directory. And once we go inside this, what I should be doing, I have to get that particular subdirectory and attach it to my training directory. In order to do that, I'll say path is equal to os dot path dot
join, and what are the values that I'm joining? I'm joining my training directory and its subdirectory, that is D. And after I get this path, next thing that I'm going to do is I'm going to say that D, okay, and D, I think it's little confusing. So this is actually dictionary and this is actually D itself, right? So I'll say dir, okay, and I'll also say this to be dir, and this would actually make more sense. D dir, and I'll set it equal to length of os dot list directory of P, okay, which is my path. Now after I've done this, I'll say that, okay, print. So I'll make use of F formatting of my string. I'm going to say that, okay, for class dir, the number of images are, then for this I'm going to say that, okay, D dir, all right, and I'll specify it like this. Observe guys what I'm doing over here. Okay, so this is what we are doing. We are going inside every subdirectory that is present in my training set. So in my case, I'm having cats and dogs, and after I select each and every subdirectory, let's say this cats over here in this example, in place of dir in the first iteration, I'm joining this path. That means I'm getting this complete path, and I'm counting how many number of images that I'm having for that specific class, that is cats, and I'm storing inside my Python dictionary of D. And once I have done that, that means once I have my dictionary ready, I'm just printing out saying it as, okay, for this class, and I'm specifying my folder name. Remember guys, I'm making use of f-string formatting. Now if this f-string formatting is very new to you, do let me know. I'll give you a video as how we can actually do the string formatting using this f-string formatting technique, and it's very easy and it's very intuitive. Now coming back to the topic, so I'm saying it as, okay, for this class, these are the number of images. All right, so let me just execute this cell. Okay, so we have the output that says as for class dogs, the number of images are 4006, and for class cats, I'm having 4001 images. Okay, so this is how the data is distributed, and as we can clearly see, at least we have the equal number, almost equal. It's not 100% equal, it's almost equal. Now in order to visualize this, let's create a bar chart. Now to create a bar chart, I'll say x is equal to, what are the classes that we have? So the classes are d.keys. Okay, so these are the classes that I'm having. For the values, I'll say d.values. So this is going to get the values of my Python dictionary, and once I've done that, I can just create a bar chart. So I'll say sns.barplot x comma y plt.show. Okay, so we are getting error. Let's do one thing, since to avoid the complication, I'm just keeping it simple. So let's execute this. So this is how our plot looks like. So we are able to create a bar chart, and we can clearly see the class distribution for images that we are having. It's pretty good. I mean, it's almost the same. Now let's display some of the sample images that we have in our data set. I'm going to create a function. I'm going to call it as, okay, display data, and this actually takes the image directory. So image directory is what it takes as an input, and inside this I'm going to specify how it has to behave. I'm going to initialize my I to be equal to 1. Then I'm going to set that, okay, plt.figure, and I'll set my fix size to be equal to, this time 20, okay, let's say 10 comma 15. Now I'm going to say that, okay, for image in image directory, and how it should behave is, I'll specify that plt.subplot, and then I'm going to say 1 comma 3 comma I, okay, and then plt.axis, I'll say it as false because I don't want to specify the axis while I'm printing the images of cats and dogs. And I'm going to say that we'll do one thing, we'll import a function which is present inside the sklearn library. It is actually helpful for us to display the images. Now in order to do that, I'll first import it like this. I'll say import
skimage.io import imread comma imshow. Okay, now what does this function would mean? So let's do one thing. Let's open up the documentation in order to get the better understanding of this particular imread and imshow. So I'm now in the official documentation page of scikit-image. So this is the library that we would use if you want to process the images in Python programming language, guys. Now from this scikit-image module, so we are importing the imread and we are also importing this something called as imshow. So this is the one where we have just imported. So what it does is this imshow is a function that we were going to use to display an image. So each and every image that I'm getting over here from my folders, so I'm displaying it with the help of this module of scikit-learn, that is scikit-image. Okay, so this is going to display an image and the parameter it takes is the ARR, which is an image data or the name of the image file. Okay, so the benefit of this is if I'm using this imshow function which is present inside this skimage.io, I don't have to read it first and then I'll have to send it inside this imshow. I can just specify where exactly is my image file is present and I can directly read it from that particular file. If you are using the OpenCV or any other library, first you have to read that file, convert into an array format, and then you'll actually display the images. Now, because of this image or because of this library of scikit-image, I don't have to do that. I can just specify where exactly my file is present. And that is what I'm doing over here. I'll say that, okay, imshow. And I'm going to specify where is my image. So this is my image. So this will take care of displaying the images. And after I display the images, I'll say I is equal to I plus 1. And once it's done, finally, I'm going to say plt.show. So let's execute this. And once I have done this, let's create some visualization. Now to create the visualization, I'm going to say something like this. I'll say that, okay, for directories in os.list directories of my training directory. Now inside this training directory, I'm going to say my image path. So I'll say im path and I'm going to set it equal to os.path.join my training directory comma dir. Okay, where is my image path? And then I'm going to specify a new variable called count, which is equal to 0, and I'm going to say image directories as a blank Python list, and I'm going to mention something like this. I'll say for I comma img in enumerate, and I'm going to mention that os.list directories of image path. Alright, now once I go inside this, I'm going to mention that, okay, my image path, which is where my actually image is present, I'm going to mention that image, that is os.path.join, and my previous im path, okay, the folder path comma my individual image. And once I have got that, I'll say image.directories dot append, and I'm going to append this path of img path, which is my specific image path, and I'll just get only 3 images, guys, because if you look at my previous code of displaying the images, I have mentioned only 3. Okay, so I'll say I equal to 2 brick. All right, and once I have done this, I'm going to call display data, and I'm going to specify the data. In this scenario, I have to specify the directories. The directories is dir. Okay, so this specific directory which we are actually checking is this, guys. So img dir, yes. Okay, so I'm just specifying over here. So I'll do one thing. I think I'll have to, yeah, let it be like this. I'll just execute this. Okay, so we have the visualization as how the data looks like. As you can clearly see, these are some of the example images of dogs and images of cats. So it's very straightforward code, guys. So first I have written a function to display the images. So this takes the image directories, and what I'm doing over here is I'm going to every file that is present in that image directory. Let's say I'm going inside the cats, so I'm going inside every file that is present in cat directory. I'm plotting with the help of imshow, which is present inside this sk image library. So I'm just specifying where exactly that file is present, and once I have done that, I'm just creating a plot. So I'm actually creating 3 plots, guys. So one next to each other, so that means 1 row and 3 columns. In that way I'm creating actually 3 files or 3 plots. And once I have done that, so I'm just displaying the plot with the help of plt.show. Now here in the below code, this would actually take care of creating the image visualization from both the subparts of cats and dogs. So for directories in my original training directory, and I'm going inside every subdirectory, and this im path refers to my cats subdirectory. And then these are 2 values that I've specified: count is equal to 0 and image directories as a blank Python list. Now here I have mentioned that for I comma img in enumerate list directory of im path. So inside this cat subfolder, I'm doing the enumerate operation. So this would create a counter as well as my original file, that is original file name. And once I'm getting that, I'm storing this I, which is the counter, and img will have the file name. So I'm joining that file name with that subdirectory which I've got from my im path, and I'm getting that complete path. And once I get that complete path, I'm storing inside my image directories. So this image directories Python list contains 3 files, and not only just 3 files, it has the complete path, guys, where exactly that particular image file is present. And once I have got 3 image files, I'm breaking this. So that means I'm coming out of this for loop, and then I'm calling this displayed data, and I'm sending 3 complete path of where exactly those images are present. And then I'm executing this display data, and this would take care of displaying those 3 images. Now to get the complete clarity, suppose if I call as img underscore dirs, so this is a Python list, and this should have 3 images where we have created the visualization. See, that is how it is working. Alright, so we have done the visualization of our data set in this video. So let's continue more of our analysis in the next video. I'll see you next time. Till then, take care and subscribe to our channel. Hey guys, welcome back. Now continuing in our deep learning journey. Now here, what we are going to do is we are going to create the objects that is called as train data generator and test data generator. Now I have talked about this concept of train data generator and test data generator already in my previous video. I'll share the link in the below description, and we are going to make use of that concept over here in this video. Now while explaining, I'm going to give you a quick overview as what it does, but if you need more information, I highly recommend you to check out that video, guys. Alright, so let's get started. Now what we have done till now in our deep learning journey, so we were trying to build the classifier. So here we are just getting the data from my Dropbox, and once it's done, I'm just going to perform the unzipping, removing that zip file to save the memory, then importing the necessary libraries, followed by visualization of our data set. So in our data set, so in our previous session, we have seen how we can visualize the data set, and we have observed how many number of images that we have for each class. And this is followed by creating a function which will actually help us in visualizing the random data that is present in my data set. Okay, so we have just displayed 3 random images of cats and dogs, and this is how the random images that has been picked from my training directory look like. Okay, and this is followed by splitting our data set into 2 parts. Okay, I think it's 3 parts, isn't it? So we have split our data set into 3 parts. One is my training data, which will have 70% of my entire data set, and 15% for my validation data, and another 15% for my test data. So that is the split that we have looked at. So here I'm just going to specify and create some folders, and this is followed by learning all the various logics that we have learned till now. Okay, and after that, so we have actually performed the split using the code that we have written from scratch. And then yes, so we have performed the split into train, test and valid data. And once everything is done, so we have seen how the distribution of data is present. So we could see that so 70% of the data is over here in my training data and 15% each on my validation data as well as my test data. Alright, so this is how our learning journey was. Now let's continue and let's make sure that the data that we have, it is ready to apply on a deep learning neural network. Now as you clearly see, the data set that I'm having, it is in my hard disk. So even though it's not in my physical hard disk, it is in a hard disk space which has been allocated for me. Okay, it's in a disk space that has been allocated for me from my Google server. Now, one common scenario that I could do is I could load everything into my RAM and then perform the training on the dataset that is present on the RAM. But as you can clearly see, I have more than 4,000 images that I have in my dataset. Now, if I load all those 4,000 images over here into my RAM, so most of my RAM space will be consumed, and obviously during the training, so if my model requires the RAM, it will not have the sufficient RAM left, and obviously I'm going to get an error. That means the runtime will get restarted. Now, in order to avoid such errors when we are working with images data, especially with convolutional neural network, we'll make use of data generator which is present inside our TensorFlow. More specifically, we are going to make use of image data generator. Now, if I open up the documentation for this image data generator, so this is the official documentation page of image data generator which is present inside tf.krs.preprocessing.image. So this will help us in pre-processing our image. The best part is it will help us in pre-processing our dataset as per our requirement. Now, while doing the pre-processing, I can perform the rescaling as per my own scale, because as you already know, when I'm dealing with the images, I'll be having the pixel values in the range of 0 to 255. So if I want to scale it down in the range of 0 to 1, obviously I have to perform the rescale, and one of the common way that we can do the rescale is divide everything by 255, and I can write it over here inside this image data generator, which will automatically perform the rescaling as per my requirement. Not only that, so when I'm performing the training, if I want to perform data augmentation as well, when I say augmentation, it's about artificially creating the data using my existing training data. So if I want to perform that augmentation as well, in such scenarios, I can make use of various functions. So I can make use of rotation range, I can make use of zoom range, I can make use of shear range, I can make use of horizontal flip, I can also make use of vertical flip. See, you can clearly see we have various options that are actually available for me to perform this data augmentation. And that is what this image data generator is written or it's here for, guys. So it will help me in generating the batches of tensor image data with real-time data augmentation. So while loading the data in terms of batches, it will perform this data augmentation real time, and that's the best part, guys. Now the requirement that we have is I want to load the images from my directory. So what we normally do is we create the object using this image data generator. And once we create the object with the required parameter values that we specify inside this image data generator, we are going to call the method of flow from directory, because I have all the images present in my directory. So I'll use this method and I'll specify flow from directory, and then here inside this flow from directory, I'll specify my training directory. That means where exactly that I have these images are present in my hard drive. So I have to mention my complete path. And this is followed by target size. That means while loading the data in terms of batches, what is the resize operation that I want to do over there? Okay. And this is followed by classes. So here I can specify, I can manually give what are the classes that is present, and normally we'll leave it to default because it will actually load the classes by looking into the class folders that we have. And we have something called as a class mode. Now by specifying the class mode, we can control how the classes to be determined. So in our example, we are working with the task of binary classification. So I can say class mode as binary classification, that is binary. By default, it has been read as a categorical data.
Okay, now if it is being read as a categorical data, that means by default it is being read as the task of multi-class classification. Now even in this scenario it can be read as multi-class classification, but in such scenarios I'll have to make use of the activation which is suited for this multi-class classification, because obviously in such scenarios I'll be required to have two neurons. But in my example I want to do the binary classification, so I can specify it as class mode as binary and specify the last neuron with the sigmoid activation function. Alright, so these are all things that we can do, and we can also specify the batch size. Now by specifying the batch size, what it does is while loading the images, it just loads only that part. An example can be, it can load 32 random images from my training dataset, and while loading those 32 images, so it will resize that images into the required shape, and it will be read from the folders in the class mode which I specify. And once the images are loaded, so whatever the document or the commands that I'll be specifying over here inside this image data generator, so those will be executed. That means if I'm performing the rescale, it will do the rescale, and if I mentioned horizontal flip and a vertical flip, it will perform horizontal flip or the vertical flip in a random manner, and it will also apply shear range, zoom range, and so on. So this is how that data gets loaded, guys. So let's do one thing. Let's implement it for our data set as well. I'm going to create my training data generator. So training data generator, and this is equal to, we have to first import it. I'll specify my imports in the same cell so that it is easier for you to refer. So I'm going to say it as from tensorflow dot keras dot preprocessing dot image import image data generator. Okay, so this will take care of the import, and now I'm going to call this image data generator. So image data generator, and inside the parenthesis first, and the important thing, I want to rescale. So I'll say rescale is equal to 1.0 divided by 255. All right, and then let's do one thing. Let's apply some rotation as well. So rotation range 0.3, and let's apply some horizontal flip as well. So horizontal flip as true, and vertical flip as well. So vertical flip as true, and I can also specify some zoom range as well. Zoom range as 0.4. okay, and yeah, so I'll keep it like this, and I'm going to execute this image data generator. All right, so this object has been defined. Now I have to mention as where exactly I have my images and how it has to load. For that, I'm going to say it as, okay, my training data, and then train data generator, which is the operation, which is the object that I have created earlier, and on top of this I'm going to specify as flow from directory, and my directory name is, this is my training directory, so data dir, and under this train, so this is my training data. So I'm going to copy that path and I'll paste it over here. So this is my training directory, and I have the class mode as binary. Okay, and in my scenario, I'm going to resize the image. So to resize the image, I'm going to specify my target size as 224, 224. So this is going to define my training data. Now when I've run this, so it says it has actually found 5603 images for my training data, and it belongs to two classes. All right, now if I want to display the class indices in such scenarios, I can say it as train data dot class indices, and this is going to return me a Python dictionary which says as, okay, for which label what is the value that I'm going to refer to. Okay, Catsville is 0, docs is 1. Next, I'm going to create the object for validation data as well. So I'm going to say valid data generator. Okay, now for this valid data generator, I don't have to do this like horizontal flip and vertical flip and all those things, guys. I just want to perform only the rescale That's it. The reason because, see, while performing the validation, I want to load the data as it is. I don't want to do the augmentation over there because it's just a validation that I'm performing over there. All right. And then I'm going to specify as valid data, and this valid data, I'll just copy my previous code. Okay. And I'm going to modify it. So valid data path is this copy path. So I'll define my path where exactly my validation data is present, and even this validation data should be resized to the shape of 224, 224. And similarly, I'll perform the activity for my test data. So I'll say test data generator, test underscore data, and instead of valid, it will be actually test. So we have created three objects. One is for training data, another is for validation data, and then the last one is for test data. Now that we have created the objects for training data, validation data, and the test data, in the next video, let's build the convolutional neural network model, and then let's apply this data set and see how our model is performing. So I'll see you next time, guys.
Hey guys, welcome back. Now continuing in our deep learning journey, in this video, let's build the model and perform the fit on our dataset. Now to build the model, I'm just going to build my model as a sequential model. But again, hey guys, you're free to use functional API, or you can also create your own model as a class as well with the help of subclassing API. Now, if you're new to these concepts, you can check out our other videos where we have explained about the various ways of creating the neural networks from scratch. All right, so let's start building. I'm going to say that model is equal to TF Tensorflow dot keras dot models dot sequential. Okay, now once I build this model as sequential, I'm just going to add the various layers. Let's do one thing. I'll take care of imports at the start itself so that I can just mention my only layers over here, guys. Okay, so here in the imports, import TensorFlow as TF. All right, and from TensorFlow dot keras dot models import sequential, and this is followed by I'll also import the individual layers as well from TensorFlow dot keras dot layers. From the layers, I want to import input layer, con2d layer, and then I'll import my flattening layer, dense layer, and I'll also import dropout layer as well if I want to use it at a later point. And let me just use this max pool 2d as well. Okay, so these are the various layers that I can use, and I'll also import some data pre-processing from my keras. So I'll say from TensorFlow dot keras dot preprocessing dot image import load img comma img2 array. Okay, so this will take care of necessary imports, and now we can start building the model without worrying, guys. Okay, so I'll say model is equal to sequential, and after defining my model as a sequential model, I can just go ahead and add the various layers. So I'll say model dot add con2d. all right, and the filters is, let's assume I'll have the 16 filters over here, and I'm going to specify my kernel size to be equal to 3,3, and I'll use my activation is equal to ReLU. And once the activation is specified, this is followed up by input shape, because this is my first layer. So input shape is equal to 224, 224, 3. Okay, so this is going to add our first convolution layer. Now, one thing that you always have to notice, when we are working with convolution layers, we don't have to perform the flattening operation.
we will send the image data as it is when we are sending it to the convolution layer. But if I'm sending the data for my dense layer, in such scenarios, I'll have to do the flattening operation. Now in this scenario, this is a convolution layer, hence I'm just specifying my input shape as it is 224, 224, 3. And in this first layer, there are 16 filters, and each filter is of the shape 3, 3, and the activation of such filters is ReLU activation function. Now I'm going to add my second layer, and for the second layer I'll also have another convolution layers, and this will have some 32 filters, okay, and the activation, let it be ReLU itself, and I'll use the same kernel size, so I don't have to specify my input shape because that will be determined from my previous layer. And once these two convolution operations are complete, I'm going to perform pooling operation. So I'm going to say it as model.add max pool 2D. So I'm applying the max pooling operation on the output that I'm getting from my convolution layer, and I'll specify my pool size is equal to 2, 2. Okay, once this is done, I'm just going to again perform another convolution operation followed by max pooling. So this time I'll have 62 filters, and I'll use the same kernel size of 3, 3 with the ReLU activation function, followed by a max pool 2D layer, and I'll have one more layer of convolution layer which has 128 filters and activation as ReLU. Now once this is complete, the next thing will be is, once the series of convolution operations are complete, I'll be connecting to a dense neural network. Now to connect it to a dense layer, I have to make sure that I am performing the flattening operation. So I'm going to say it as model.add flatten. So this will take care of flattening operation. And then I'm going to convert this flattened output into a dense layer. So dense, and I'll have, let's assume 64 neurons, and I'll use the activation as ReLU. And this is followed up by, let me add a last neuron. Okay, so since this is a simple binary classification, I'll say model.add dense 1 activation is equal to sigmoid. And once this is done, I'm just going to display the model summary. Okay, so this is how the model would look like. So my input is of the shape 224, 224, 3. Now as a result of applying my first convolution layer, the shapes have been transformed, and the resulting shape is 222, 222, 16. That means I have lost a dimension along each axis, which means that I am losing the dimension because of performing this convolution layer, because I'm not using any padding. And the third dimension has been changed to be 16. This is because there are 16 filters. In the next layer, we have 32 filters. And after this second convolution layer, this is followed up by max pooling layer. See, when I perform this max pooling operation, I have reduced the size by half. This is followed up by another convolution layer, then followed up by max pooling layer, convolution, max pooling. So here the output of max pooling is being sent to flattening layer. Now by sending to flattening layer, I'll be actually converting into a single dimensional vector. And this flattened input is sent to my dense layer. And in my output layer, I'm having a single neuron with sigmoid activation function because I'm performing the task of binary classification. Alright, now once this is complete, I'll go ahead and compile the model. Now to compile the model, I just have to specify my loss function, optimizer, and the metrics. So model.compile loss is equal to tf.krs.binary cross entropy. Alright, and I'm going to use my optimizer as Adam. Now you're free to use any optimizer, guys, but this is what I'll be using, which I found to be performing well compared to others. So metrics is accuracy. Okay, now this is going to perform the compile operation. Now this is followed by performing the fit. Okay, now before we perform the fit, we also have the option to specify our model checkpoint. So let's add the same thing, guys. I'm going to import my keras callback. I'm going to say it as from tensorflow.keras.callbacks. I'm going to import model checkpoint as well as early stopping. Now I'm going to define how the early stopping and the model checkpoint should work. Hey guys, if you're new to this, please check out our other videos as how to make use of keras callbacks. So I'm going to specify it as early stopping, and inside the parenthesis I want to monitor my validation accuracy. Okay, and I'm going to say it as minimum delta is equal to 0.01 and patience is equal to 5, verbose is equal to 1. Now this means that monitor my validation accuracy, okay, and wait for 5 epochs. If the improvement doesn't, if there is no improvement in validation accuracy even after 5 epochs, just stop the training. Okay, so that is what my keras callback is specifying over here. Now along with this, I'm also going to create my model checkpoint. So I'll say it as model checkpoint is equal to model checkpoint, and here I'm going to specify my model. Okay, my best model.h5, and I want to monitor the same validation accuracy, and then I want to say it as save best only true because I want to save the best models only. Okay, and along with this I'll also specify verbose is equal to 1 because I want to display what is happening over there. Alright, so this is going to take care of creation of model callbacks. Now I'll use these callbacks when I'm performing the fit. So I'll say history is equal to model.fit, and inside the parenthesis it's train data followed by validation data is equal to val data. Alright, I'm going to reduce the number of validation steps, because I'll say validation steps is equal to 16. Okay, steps per epoch is equal to 16. Okay, I'll say epochs is equal to 30, verbose is equal to 1, and for the callbacks this is consist of my early stopping and model checkpoint. Okay, now observe closely here. I'm using a different terminologies over here. So model.fit, I'm specifying my training data. Now if you observe, this training data is nothing but the data that I have created earlier which flows from directory. Okay, this you are at least a straightforward one, and this is a validation data. Now along with these two, there's an additional argument that I have used that is called as validation steps and steps per epoch. Now let me do one thing. Let me just execute this cell. Let it start executing in the backend, and then I'm going to explain about these two steps. Okay. Okay. So the training of my model has been started. Now here I have mentioned my validation steps is equal to 16. So, and also if you remember, I have specified my batch size to be equal to 32. Now if you remember, what happens when there is an update? So whenever there is an update, it loads 32 images, and after it loads this 32 images, it is going to update my parameters. Okay, so after loading the batch size of 32 images, it is going to update the parameters of my deep learning model. Now observe what am I specifying over here. I'm saying it as steps per epoch is equal to 16, which means load 32 images 16 times. Okay, And once you load the 32 images 16 times, and once you update it 16 times, count it as a one epoch. Okay, and likewise do it for 30 epochs. So that is what this steps per epoch would mean. So if I have 100, or let's assume 6,000 images, from this 1000 images, each time I'm going to load 32 images, and I load this 32 images. Using this 32 images, I'm going to do the update on my parameters, and after this thing, I'm going to obviously load another 32 images. Now here I've done the update once, then I'll load the 32 images and I'll do the second update. Likewise, I'm telling my system as do 16 updates to count it as one epoch. Now if I don't specify this as do it as 16 steps, it is going to load as many number of images that I'm having. Now let's assume in my training data I'm having 4000 images. Then if I want to count it to be as one epoch, I'll have to process all these 4000 images. But instead I'm saying it as just load 32 into 16 images for each epoch. So that is what I'm telling for my system. The reason that I'm taking this approach, because as you know, there is lots of data over here with me and I don't want to wait for too long. Hence I have used this concept. I've just simply mentioned as steps per epoch as 16, and you are free to remove this parameter and train it on your entire data set. All right. So let's see the training progress. See, it's still getting trained, guys. It's still taking a lot of time to train. So what I'll do is I'll let it train like this, and I'll see you in the next video where we explore more about how the training is performing and what we can do to improve this training. So I'll see you in the next video, guys.
Hey guys, in the last video we have performed the fit on our data set. So we have did as model.fit, and we have specified the training data, validation data, and we had specified the validation steps and the steps per epoch. And we have done all this activity and we were able to perform the fit. Now if I just come down on the results that we have got from the last session, so this is the result that I have got over here, guys. So it says by the end of 11th epoch, so the validation accuracy was 0.51, and I have a message that says as validation accuracy did not improve from 53%, which I had got at the 6th epoch. And because it did not improve for 5 epochs continuously, it is performing the early stopping. Okay, so why is it happening? The reason it is happening because observe over here, guys, I have specified my callback as monitor my validation accuracy and have patience till 5 epochs. If the validation accuracy did not improve after 5 epochs, then just stop the training over there, because I don't want to use the resources. And we could observe over here as the training proceeds and it actually performed even worse as well. So because of this reason, the system found out that okay, even after 5 epochs the accuracy is not improving, let me just stop the training over there. So this is the working of this TensorFlow callback early stopping. And if you look at it, there are some logs which says as validation accuracy improved from this to this, and there is a saving a model, and it is happening at the end of each epoch. And if you look at it, it just saved the best model. So at the 7th epoch, when the accuracy was lesser than the previous model, it did not save. So my model which is already there, that is inside this best underscore model, this has the best model for me. Alright guys, so this is the importance of using TensorFlow callbacks while performing the deep learning training. And we could observe that the maximum accuracy that have reached for this model fit is 53%. Obviously, it's not so great, isn't it? So I still have a lot of things to do. Now, before we look at its working, before we look at the strategies of improving, let's do one thing. Let's perform the validation on this best model that we have got. Now, as I mentioned already, this will have our model over here. So this is our best model. So let me load this model from this file. So I'll say it as from tensorflow.keras.models import load underscore model. And I'm going to load the model. I'll say it as model is equal to load underscore model, and inside the parenthesis I'll specify the complete path. So I'll just copy the path and I'll paste it over here. So I'll just execute this. So this model will have the best model parameters. Now if I want to perform the evaluation on my test data, that means how it is performing on my test data, I can just say it as model.evaluate, and I can just specify my test data. Okay, so the accuracy that I'm getting on my test data is 50%. That's okay. So that's the accuracy that I'm able to get on my test data. Okay, now let's do one thing. Let's analyze our history object. So history is something which has all the information from my training. So history.history. So I have loss, accuracy, validation loss, and validation accuracy. So let me just create a plot. I'll say it as import matplot lib.pyplot as plt. All right, plt.show and plt.plot, and I'll say history, well, accuracy. Okay, and then I'm going to say it as color is equal to yellow, and then I'm going to print this against validation accuracy. So I'll say val_accuracy, I'll say color is equal to red. So this is how our training has happened. So this is where my validation accuracy was, and this is how it is getting changed, guys. So my validation accuracy is like this, and the yellow one talks about my training accuracy. Okay, and we can create a similar plot for loss as well, loss and validation loss, to get the visualization as how the loss is being changed as the training proceeds. Okay, so now that we have seen how to train our deep learning model, now let's look at the ways that we can improve our model. So one of the important ways that we could improve the model that we have just trained is, one, we can add a dropout layer. So in case of dropout layer, what it does is it just removes some neurons. That means it is going to zero out some values, guys. It is going to zero out some neurons, and it does it in a random manner, and it has been found that it will help us in performing the fit. Okay, one, we can add a dropout layer on our model, and the another strategy that we could use is increase number of layers and number of neurons in each layer. So this is another strategy that we could use. The next strategy that we could use is train on entire data set instead of loading part by part. So we have to train on our entire data set itself, and obviously when I train on my entire data set, it will definitely be able to learn better and better from the data set that we have. And also use the batch size, which can be accommodated maximum on my RAM that we have. Okay, so this is another thing that we have. Now let me just show an example as how you can add a dropout layer. Okay, so I'll do one thing. I'll copy this model definition and I'll paste it over here. Now for the example purpose, I'm going to add a dropout layer for this. Now to add this dropout layer, I'll simply add a dropout layer, guys. So I'll say it as, so let's assume after maxpool 2D, I'll apply a dropout layer over here. So I'll say it as model.add dropout. Okay, so this is the dropout layer, and I'll specify the rate. I can specify a rate. In this example, I'm saying it as dropout as 0.3. Okay, now I'll add one more dropout layer after this dense layer. Okay, and then I'm sending it to my output layer. So if we do it like this, and we can also further increase another, we can add one more dense layer. So let's say 32, and then we can just
try out and see whether it would actually help us or not. So I'll do one thing, I'll compile my model again. And after the model compilation, I'll perform the fit. Now this time, while performing the fit, I'll specify the steps per epoch as 32. That means I'm doubling, which means I'm running for more number of times. Okay, so I'm using more data for training. Okay, and validation steps as 32. So I'll just execute this. Okay, so the training is already started, and we can observe this one important thing, guys. See, at the end of first epoch, so I have reached the accuracy of 53%. Wow, that's a good sign, isn't it? So yes, now by the end of third epoch, I've reached the accuracy as 57%, and it's still going on. So even though it is taking more time to train, but still it's worth it, isn't it? So I'm getting more and more accuracy from the model that we are training. And thanks to the more data that my model is able to consume, and along with that, like by adding the dropout layer and as well as other techniques that we have just applied. Alright guys, so this is how we can further improve the model as well. And apart from this, you can check out with various optimizers. Currently I've used the optimizer as Adam, and you can check out with various other optimizers and see how it is working with other optimizers as well. So these are the common steps that we would do once the training is complete for any deep learning model. Okay, so with this, we come to the end of this video on how to perform the training on convolutional neural network. And from the next video, so we are going to look into the new topic that is called as transfer learning. So transfer learning is one of the advanced topic when it comes to deep learning. So we'll make use of already trained model and use that model to make our life simple. That means we'll use the learnings from the previous data, and on top of that model, we are going to retrain on our data set, and to make sure that we are getting the best results with just little amount of training. So that's the benefit of using transfer learning, and we are going to explore from the further videos of this section. So I'll see you next time. Thank you guys, take care, and if you are new to us, please subscribe to us. Okay, so thank you, I'll see you next time.
Hey guys, now continuing in a learning journey of deep learning, we are going to understand about the transfer learning. Till now, we have been training a deep learning model on our own. That means we started to build our own individual layers, and after we built our individual layers, we started adding neurons to it, and we specified the activation function, we specified the loss function, and we trained this model from scratch. That means we have actually trained our model from nothing. That means we started the initializing our deep learning model with random parameters, and then we made sure that as the training progresses, we are reaching towards the solution. So that is what we have done over here. But in case of transfer learning, we are not going to train our deep learning model from scratch, guys. That means I'll make use of a pre-trained model, and then on that pre-trained model, I'm going to start it as a starting point. And there's a saying in deep learning, guys. So with the help of transfer learning, we can actually increase the productivity of our deep learning model training, guys. Okay, so it will actually help us in increasing the productivity of our deep learning model training. Now, as I mentioned already, I spoke about one important term that is called as pre-trained model. So let's see, what does it mean? A pre-trained model, it's a model which has been already trained by someone to solve a similar problem. Now, what we are going to do in case of the transfer learning is, instead of training our model from scratch, observe this. Instead of training my model from scratch, I'm going to use that model which has been trained on a similar problem, and I'm going to use it as a starting point, and that is what is called as transfer learning. Okay, so that is a transfer learning, guys. Now let me just give an example to give you more intuition as what is happening in case of this transfer learning. Let's assume you are building a classifier, and this classifier is a binary classifier to detect whether a person is wearing a mask or not. Okay, wearing a mask or no mask. So this is a simple classifier that you're trying to build, guys, to check whether a person is wearing a mask or not. Now, as you can clearly see, this is a task, and this is a unique task which I have come up to say, okay, whether this person, given this person's image, that is person's portrait, to say whether this person is wearing a mask or not. Now, obviously, in order to do this, I can train my neural network from scratch and then make sure that I'm training everything. I have all the required data and I'm going over it. And let's assume I have millions of parameters. I'm training all those millions of parameters using my laptop, or it could be EC2 instance that I have, which has a powerful CPU and the GPU. And let's assume I took 5 days to train my model to get a decent accuracy of 60%. Okay, so this is the progress that I have got after training for 5 days, and the accuracy that I've got is only 60%. Now, there is another alternative approach, guys. The alternative approach is with the help of transfer learning. Now, let's see how does that alternative approach would look like. Now, in case of transfer learning, what we would do is we are going to make use of the model which has been trained on a similar task. Now, in my example, I'm performing the task of image classification. It's a plain simple image classification. So do you agree with me, guys? Yes, isn't it? I'm performing a basic image classification to check whether a particular person is wearing a mask or not. Now, what I can do is, in case of transfer learning, I'll look into the model repositories which are available, whether it could be Tensorflow or PyTorch, and see whether I already have a pre-trained model where someone has already trained a model on the task of image classification. Now, when I look into the model repositories, I get to know that, hey, there is a model that's called as VGG16, and this VGG16 model is also based on convolutional neural network, and this has been trained on a different dataset which is called as ImageNet dataset. Okay, and this ImageNet dataset has actually 1000 classes, and this model has been trained on that complex dataset which can classify a single image to whether it belongs to one of 1000 classes. Okay, so you have found a model which has been trained for a similar task. In this scenario, it's a image classification. So what you will do in such scenario is in case of transfer learning, you'll make use of the feature learning part, that is the CNN layers. So you'll extract the CNN layers because that is where the learning of the image features would happen. So you'll extract the features, that is feature learning part of my VGG16, and then you are going to modify the last layer in your VGG16 model. The reason because, as I mentioned already, this VGG16 model has the 1000 classes. So as a general rule, what we would do is we'll just extract only the CNN layers part, and we are going to add our own custom dense layers, so that it is going to learn something which are specific to our business problem as well. So I'll use CNN layers from VGG16. I'll add a box over here. So this is my pre-trained models box, guys. Okay, I'll say pre-trained model. So these are the pre-trained model box which contains my pre-trained layers of VGG16, and this is with my other dense layers. Okay, so my pre-trained layers are placed next to my dense layers. Now what I'll do during the training is, during the training, I'm going to set my deep learning model condition very strictly, guys. I'll say it as, okay, you don't have to learn anything new. Just use whatever you have learned from your VGG16 model at the convolution neural network layers, which means while collecting the important features from the image, please don't go for an adventure and start from scratch. So just use whatever the learnings that you may have. And it turns out, so this model is able to give me better accuracy than what I had got from the model which was trained for 5 days. An example is, let's say I have trained this model for 15 minutes by adding 2 dense layers which has 32 neurons and one last layer which has a single neuron for an output layer. And I have trained for 15 minutes, and at the end of my 15 minutes, I'm getting the accuracy of 85%. Now, why am I getting this much of accuracy? The reason is simple, guys. One of the complex thing that we will be having when we are working with deep learning neural network, especially while working with image data, is extraction of important features of an image. So that's a complex task that we'll be having. Now, in case of VGG16, this has been already trained on a very big data set. Just to give an example, let's say I have a class in my VGG16 to detect whether cat is present in this image or not. I'm just coming up with my own example, whether this cat image is present in this VGG16 or not. Now, to identify the cat in a given image, my VGG16 layer or this VGG16 model has been trained to detect, okay, what is cat and what is not cat as well. Because let's say I have a cat and this cat is next to a TV, or this cat is present in an outside environment. So it should be able to identify where that cat is, isn't it? So it is able to identify the important features that are present in the image and distinguish what are all not the important ones. Now, when I give my model, that is this VGG16 model, with my similar task, okay? So in my similar task, let's assume I have a person image. And let's assume it has also learned some data about person as well in VGG16. In such scenarios, when I send that person's face or that person's image to this pre-trained model, so at least the expectation is, or the assumption is, it will be able to identify the important features of the newly given image as well. Now that is the assumption that we are going to make. And along with that, that means after it gives us the output from this feature extraction layer, that is from my CNN layers, we still have the trainable layers, that is two dense layers, which will be suitable for our task. Now the challenge is always how to find those similar trained models. Now that we have the open source, so we can just Google out and look for the developers who are already trained on different models, and use those models and see whether we have the required permission so that we can use it for our commercial projects. Alright folks, so always the key challenge is finding the right models. But as you clearly see, if I can find such models which has been already trained on a similar task, it will be a easier task for me. Okay, so with my CNN layers, I'll have my pre-trained model layers, and along with that I'll add some dense layers. Now during the training, I'm going to switch off the training for the CNN layers and I'll just train on my dense layers, which means I'll have less number of parameters to train, and I'll also have less number of layers to train. So this will help me to faster training as well. And to name a few of the pre-trained models, so we have something called as AlexNet, we have something called as VGGNet, GoogleNet, ResNet, DenseNet, ShuffleNet v2 and MobileNet v2. So these are some of the examples for pre-trained model. Now if I'm implementing any of this pre-trained model, the way that I would do is, I'm going to first import that model as a whole, and I'll just extract the feature extraction layer for each of this convolutional neural network. Now let's assume it's a VGG16, so I'll extract the convolutional neural network layers of this VGG16, and before I start training, I'm going to freeze these layers. Okay, I'm going to freeze these layers. And once I freeze these layers, I'll concatenate, or I'm going to add some dense layers along with my VGG16 layers. And for these two dense layers, let's assume I'll say no freeze. That means trainable. And in my output layer, I'll have the required number of neurons as per my problem statement. Okay, now during the training, you can clearly see that the entire image, the feature engineering branch or this feature extraction branch, so this entire feature extraction layers are frozen, which means it's not being trained. It means it is just performing the prediction during the training. So as a result of this, I'll have only fewer neurons to train. Since I have very fewer neurons to train, obviously I can progress faster, and I'll be able to get the better accuracy on the basis of learning that I already have with the help of transfer learning. Okay guys, So in the next video, we are going to look into the implementation of VG16 model as a pre-trained model, and we'll implement it in a hands-on way. Now, before we do that, in the next video, first we have to go in depth and understand what are all these individual layers are present in this VG16 model. Okay, so I hope you like this video, and I hope you now understood as what is happening in case of transfer learning. Now, if you are new to us, please consider subscribing, and I look forward to seeing you next time. Thank you guys.
So from the last video of our deep learning series, you now know what is transfer learning. So transfer learning means using the already trained model to do the similar task. Now in this video, we are going to look into a model that is called as VGG16 model, which is one of the famous convolutional neural network model. Now, as we progress in our learning journey, we are going to use this VGG16 as a model for transfer learning purpose. So it's very important that you understand how this VGG16 model is built, so that when we utilize it in our application, you know what to change. Okay, so let's get started, guys. Now here, if you look at it, this VG16 model expects my input, which is of the shape 224, 224, 3. Now this is very important. Whenever we have, or whenever we are using a neural network, which is a pre-trained neural network, we have to make sure that the input shape that we have is matching the expectation of these neural networks. As you can clearly see in this example neural network of VG16, it is expecting with the shape as 224, 224. Now let's suppose if I do not have an image which is in this dimension, in such scenarios, I'll have to make sure that while I'm loading that image, I'm transforming it to this required shape of 224, 224, 3. If I don't specify this in this shape, then I will be ending up with an error, guys. So please make sure that you process the image to match the input dimension expectation from my deep learning model. Now, after that, if you look at it, when I give an input over here, it is being sent to the series of convolution operation. And at the end, here the dimension here says 224, 224, 64, which means my original dimensions were 224 by 224. Now, as a result of performing my convolution operation, I'm getting the size of 224, 224, 64. Now, this means that at least by the end of this last, that is the second convolution layer, I have total of 64 filters. So there are total of 64 such filters, and I'm making sure that I'm adding the padding. Because of this padding, the same dimensions is being retained over here. Now once that is done, here I'm performing the operation of pooling. So the first pooling over here, the red box. So this red box talks about pooling, and in this scenario, the pooling operation is max pooling operation. Now this max pooling operation, obviously it is going to result in the shape as 112, 112 by 64. That will be the shape over here. Okay, so I'll say 112, 112 by 64. Now the output of this pooling layer is being sent to the series of convolution operation, and as a result of this series of convolution operation, I can say that there are 128 filters. So as a result of this, in this layer, okay, the shape is 112 by 128. Now this is followed by another max pooling operation. Since it's a max pooling operation, the resulting shape would be 64 by 128 such filters, and this is being sent to my convolution layers. Okay, now once I perform pooling, so this will be actually 56 by 128, and this is being sent to the series of convolution operation. So 56, 128 is being sent to my convolution layers, and here I'm having 256 such filters. So as a result of this, the shape of this convolution layer will be 56, 256. That is same for all these three convolution layers, and this is followed by another max pooling operation. As a result of this, 28, 256 will be the shape. And now this is followed by another set of convolution operation. So convolution operation is 28, 256. So let's see what is the status. Yeah, 28, 512 filters. Okay, and this is followed by one more pooling, 14, 14, 512, and this is being sent to another set of convolution operation. And so here I'm using the same number of filters, that is 512. So this 14, 14, 512 is being used over here. Okay, 512 filters is being used, and then after this would result in 7, 7, 512, and this 7, 7, 512, the output that we would get over here as a result of this pooling operation, we are performing a flattening operation. So I'll perform flattening operation. So 7 into 7 into 512, let's see what will be the output. 7 into 7 into 512, so this is going to result in 25088. So those 25088 neurons is being connected to my dense layer. Okay, so each of this dense layer will have their respective outputs. So I'll connect to my dense layer. So in my first dense layer, I'm having 4096 neurons, I believe, and in my last layer, I'm having my output layer. So this is what my neural network is telling me. Okay, so we are having series of convolution operation, pooling, convolution operation, pooling, convolution, pooling, and so on. We can see that as the dimension of image decreases, we are increasing the number of filters as we progress in our convolution operations. And by the time we reach the pooling output is 7 by 7 into 512. I'm going to convert it into the fully connected neural network. In this scenario, it is 4096 neurons. And in my next layer, I think I have the same number of neurons of 4096. So there are two fully connected neural networks with 4096 neurons. And in my final output layer, I am having 1000 neurons with softmax as activation function. Let's do one thing. Let's look at the activation function that we have on other layers. So for the other layers, for normal layers, we have convolution plus ReLU activation function. Okay, and in my output layer, we have the softmax. Now, if I'm using this for my benefit, that is to perform the cat-dog classification, then one of the things that I have to do is, instead of having 1000 neurons over here, I need to have only one neuron with sigmoid activation function. So this is one change that I can clearly see that I have to do if I'm using this VGG16 architecture. So 1000 neurons will be replaced with one neuron, and I'll be replacing that softmax activation with sigmoid activation function. And here we have some dense layers. Now for the benefit of training, what we can do is, instead of training everything, we can just freeze these layers, which are my convolution layers. I'm going to perform the activity of freezing, and I'm just going to train my dense layers. So I can do this activity for, let's say, n number of epochs, and once I'm satisfied with the outputs that I'm getting, at the end I can train on entire neural network. So that is the approach that we can take. Okay, so at the start of the training, we are going to freeze our convolution layers, and then we can train only on my dense layers, and as the training progresses, I can switch on the training and train on my entire neural network. Now to load this VGG16, we can make use of Tensorflow Model Hub. Okay, so we are going to do the hands-on in the next session, guys. I look forward to seeing you in the hands-on session. See you, take care, and if you're new to us, please consider subscribing.
Hey everyone, welcome back. Now in the last video, we have learned about the VGG16 network. We looked at the architecture, we saw how each and every layer is present in the VGG16 architecture. Now in this video, we'll use the same VGG16 architecture and perform the transfer learning on the task. In our case, it's a binary classification task, which will help us to determine whether a given input image belongs to the class of cat or whether it belongs to the class of dog. So let's get started. Now here, as a first step, I have to import my model. Now this model is called as VGG16, and this is present inside my tensorflow.keras.applications, and inside it there is a module called VG16, and from there we are going to import it. So let me just show you how it would look like. Now I am loading my VG16 over here.
see there is something called as VGG16, and it says this is going to instantiate my VGG16 model. So it is present as TF-KRS application VG16.VGG16. Okay, and these are all the various arguments that we have. Now here, if you look at it, we talk about include top is equal to true, which means when I simply instantiate my VG16, it's going to include my top layers as well. Now here, the top layers refer to my fully connected layers. So that's what it means. And then we have the weights. So here we can specify as what are the weights that I have to load when I'm instantiating my model. Now we'll just come down and let's explore about this weights parameter. Now for this weights parameter, see, so one of non-random initialization, ImageNet pre-training on ImageNet, or the path to the weights of the file to be loaded. That means I can specify if I do not want to load any weights as well, or I can also specify whether I should load a pre-trained weights which has been trained on a ImageNet challenge, or whether I should load my custom weights. So I have all the options are available with me. Next, here we have mentioned as input tensor is equal to none. Okay, so this is just an optional, so we can add it as well. And here we have to specify the input shape. Okay, so this is also an optional shape. So if I don't specify anything over here, by default input has to be in the shape of 224, 224, 3. Okay, and then classifier activation is softmax and number of classes is 1000. So these are the default values that we will have. So this will get loaded when I'm loading this, especially when I'm loading my full model, that is include top is equal to true. So let's go ahead and import the same as well. So here I'm importing my VGG16, and then I'm creating my model as VGG16, and inside the parenthesis I want to load my ImageNet weights and include top is equal to false, which means I don't want the fully connected layers. I just want the layers till it performs my convolution operation. And then I have specified my input shape. This is 224, 224, 3. Now once that is done, I am setting up attribute that's called as trainable that is equal to false. I want to freeze them while I'm performing the training. And because of that reason, I have mentioned as base model dot trainable is equal to true. So I'll just execute this. So this is going to instantiate my VGG16 model. If I represent this as my VGG16 model, hey, inside this big box, I'll have various layers inside this. And what I'm saying over here is make this entire layers as a non-trainable. Okay, it's a non-trainable layers. And I've also mentioned that include top is equal to false. That means I'll only load my convolution layers. I'll not be loading the dense layers. That means I'll have a series of convolution and the pooling operation which will be performed on my input data. Now let's see and let's validate what are the various layers that has been loaded for us. Now to display the same, here I have mentioned as base model dot summary, which will help me in displaying the summary of the model that we have just loaded. So here in the first layer, I have an input layer, and this input layer takes the shape as 224, 224, 3. And this is followed by two convolution layers, followed by a max pooling layer, convolution layer, followed by another convolution layer, max pool layer. And here there are three convolution layers followed by a max pool layer, three convolution layers followed by a max pool layer, three convolution layers followed by my final max pooling layer. And at the end, my max pooling layer output is of the shape 7, 7, 512. So I have loaded only my feature learning part. That means where I'm interested in performing convolution as well as my pooling. Now for my current model, I'm going to use these layers, that is the layers for my VG16 which has the pre-trained weights, where I have set my trainable as false. I'll use this model, and on top of it, I'm going to add my individual layers. Now to build the same, here I'm importing layers and models so that it is easier for me while specifying my individual layers. I am defining my model as models.sequential, And here at the start, I'm specifying my base model, that is the VGG16 model, which I've just loaded. And this is followed by flattening operation. The reason because if you remember, at the end of my convolution, I have the max pooling layer. So at the end of my VGG16, I'm having this max pooling layer. Now, if I want to connect this to my fully connected neural network, I'll have to first flatten it. Hence, I'm calling this flattening layer. And the output from this flattening layer is connected to my dense layer, which has 50 neurons. And this is again connected to 20 neurons, which is a dense layer. And in my final output layer, I'm having a single neuron, which has the activation of sigmoid. Okay, so let's define this model as well. And on top of it, I'm going to display the summary, model.summary, to validate whether we have the model as per our requirement. Okay, so we have the output. Now here it says VGG16, and this is the final output that I'm going to get from my VGG16 model, 7,7,512. That is my output shape. And this is performing the flattening operation. This is connected to a dense layer which has 50 neurons, connected to another dense layer which has 20 neurons, and in my final output layer I have a single neuron with the activation of sigmoid. Now this is followed by a common operation, that's compile. So optimizer is my Adam optimizer, loss is my categorical cross entropy loss, and the metrics that I want to use over here is accuracy. Okay, so I think I'll have to change my loss as well, because in my example, it should be binary cross entropy. So let me just change the same over here. Okay, so I have corrected my loss. My loss is binary cross entropy loss, and my metrics is my accuracy. Now, once the compile operation is complete, we can go ahead and perform the fit. Now, while calling the fit, it's the same method. We'll call model.fit. We'll specify training data. We'll specify the validation data. Now this time I'm not specifying the number of epochs or number of steps per epoch. I've removed everything. I want to see how my model would perform at the best. So I want to train on my entire data in each epoch. So I want to learn as much as possible from the model, and I'm going to start performing the training. So here I've used the same callbacks which we had defined earlier. So early stopping as well as model checkpointing, and I'm running it for 30 epochs. So I'll just execute this. Okay, so this has started the training. Now I'll pause the video over here, and once the training is complete, I'm going to show how the training has performed, and then we'll analyze our training fit that has been performed by this VGG16 model. Okay, we now have the training completed, and the maximum accuracy that has been reached from this model is 90.820. That's amazing, isn't it, guys? So this approximately took around 10 minutes. Now by training 10 minutes, it has actually given me 91% of accuracy. That's pretty amazing with the computation speed and with just random parameters that I gave, guys. So this clearly means that my model is capable of identifying whether my given image contains a cat or dog with 90% accuracy. Now if I want to improve more further, so I have more options as well. So I'll have to I'll have to again retrain my model. Now this time if I want to retrain, I can switch on the training for my entire neural network, and let's see how it performs. Obviously it will take more time, but that's one of the activity that you can try out. All right, so in this way we can make use of transfer learning and get a kickstart while performing the training on a deep learning model. I hope you enjoyed this section on convolutional neural networks. In the next video, I'm going to give you a summary as what are all the things that you have actually learned in this entire section, and what your learning journey will be as we progress in this deep learning course. So I look forward to seeing you next time. If you're new to us, please consider subscribing, and if you require the code files that we are currently going through, so my code files is already uploaded in my website of Manifold AI Learning. Please go over here, click on the courses, so you can see the course of deep learning with TensorFlow. Please click on this and register over here, enroll for free, and
just enroll and you will be getting the access to the learning management system, and along with that you'll also get the source code which we have used in this section and also in the other sections as well. Now if in case any of the source code is missing, do let us know by writing an email support@manifoldailearning.in and we'll be able to help you. Thank you so much, and I look forward to seeing you next time. Hey everyone, thank you so much for being with us till the end of our convolutional neural network. Now it's been a great learning journey, at least for me, and I hope you had a good learning journey from your end as well. If you have any feedback or if you have any suggestions, do let me know in the comment section, and I'll do my best to incorporate in the upcoming sections of these videos. Now in this section of convolutional neural network, to give you a quick overview as what we have done till now, on the class 13, we started with introduction to convolutional neural network. Now before this introduction to convolutional neural network, I think in the class 12, we had an introduction to the computer vision and what exactly is computer vision is about, and how to go about in identifying the objects in the images, and what exactly is this important term of computer vision. And from that introduction, we started from class 13 about convolutional neural network and how it actually works. And we also got to know about as what is a convolution operation and what happens inside that convolution operation. And we learned about the important parts of the convolution operation, that is padding and strides, and this is followed by various layers that we have inside our convolution layers, pooling layers, or it could be any other layers as well as we have in our convolutional neural networks. And you have also looked into the structure of this convolutional neural networks. And in the class 16, we had the hands-on of this convolutional neural network with the help of Tensorflow framework. And as you progressed from the class 16, you might have understood about the depth that we went through to learn this convolutional neural network. I mean, we started initializing each and every parameter, and we have seen, okay, what is happening when I apply this convolution operation? Whether is it matching a theoretical understanding or not? And what happens if I apply any activation function over there? So we initialized each layers, we initialized the parameters over there, and we got an intuition as what is happening in the real time. So we are not just bluffing over there. We were just seeing everything in the action, and we had values to prove to say it as, hey, this is how the data is being analyzed, or this is how the data is being processed. And we took a very deep dive. I think I can say about 4 to 5 sessions was about deep dive into this convolution operation. So we looked into the mathematical working, we looked into the pooling layers, and then post that we looked into the activation function, and then we defined about a typical convolutional neural network architecture when it comes to deep learning. Now by the time of class 21, you had a great and in-depth understanding about various layers that we will have inside convolutional neural network, and also how it actually works individually as well as together. And from the class 22, so we picked up a pace, and we started building our own classifier, which is called as cat dog classifier, where we have made use of images of cats and dogs to say what is present in that given image, whether it contains cat or whether it contains dog. And in order to do that, we have built this convolutional neural network from scratch. So we defined the individual layers, and during that time, so we have also explored about how to split the data set from ourselves, and to do it, we have made use of OS library to make sure everything is in place. And we have created the 3 parts: train, test, validation part. And we have also looked into the concept of data loaders, which will actually help us in pre-processing the data and help us in data augmentation during the training. We looked into those scenarios as well. We have visualized the data, and once that is done, we have performed the fit on our Conv2D neural network, and we have seen how we can improve the neural network that we have built using various techniques that I have explained in the videos. And after that, so we looked into the advanced concept of transfer learning. Now this transfer learning, we have made use of VGG16, which is a neural network, which is a pre-trained neural network. So we have first understood what is transfer learning and how it can benefit us, and that is followed by understanding how the VGG16 looks like. And we have used that VGG16 into our same data set that we are working with, that is cat dog classifier, and we have implemented that as well. And we found that we have been able to reach better accuracy compared to the model that has been trained from scratch. Now if you want to go about and improving that model as well, yes, so after training for few epochs, so we can just train our entire data set on my entire deep learning neural network that has this VG16, and see whether it will actually help us in getting the better accuracy as well. So this brings us to the end of this topic of convolutional neural network along with the learning of transfer learning. So this just marks the end of this section, but not the end of our learning journey. Now in the upcoming module, we'll be looking into the concept of object detection, which is one of the exciting topic, guys. So object detection. So in case of object detection, we are not only going to identify who is present in the image, but also where. So that is an exciting thing when it comes to object detection. So we'll do that from the next videos of this video series of Tensorflow. So if you're new to us, please consider subscribing, and if you want the source code, please visit our website manifoldailearning.in, and from there click on courses and you'll be able to see the course of deep learning with Tensorflow. Just click over there, click on enroll for free button and enroll in our website, and you'll be getting the access to all the source codes that we have discussed in the videos. If you have any feedback and suggestion, do let us know in the comment section. And thank you so much again for watching, and I look forward to seeing you next time. Take care.